Testing mic test, YouTube mic test. Mic test. Raj, can you hear me in the live stream? On your phone. Yeah, maybe you should go outside. You want increase the volume? So that we will have to do for the room. Yeah. Okay. Audio good, Raj? Audio check. Raj, can you hear me from the back? Is the audio good? Good.
Signage.
Huh?
This is EMC2.
Yeah. Let's take that's one thing. Let's take two. Do you have a paper we can just put it? They have this open name. I also feel it on and for the website that they have given the name, that's all we do. Or we just took this. Yeah. I think people will do it first stage of breakfast. Okay, Satyam, I think we'll get started. Hello, can you guys hear me? Um, Hello, thank you everyone for 11th EMC2 Workshop Edition. I'm Raj. A little bit of history about our workshop. We started 9 years back here in East Coast at Williamsburg. First version was in ASPLOS. And back in the day, our understanding was that as machine learning becomes important, energy efficiency issues and power will show up. And now even more at every level. We started with embedded systems and on the edge sort of focus. But every edition we try to pivot to what is more consequential, how the overall hardware software co-design is moving. This year our focus is more on large scale infra and AI spending companies and industries are doing to run their workload training inference side. So we'll have a lot of talks focused around those areas. And hopefully this is worth your time. It's first day of the workshop, but we have a very good lineup of speakers from industry and academia. This forum, we have always tried to balance where we have perspective from both sides. On the second half, we have also panel and bunch of other talks. Prior edition of EMC2 have been with ASPLOS, ISCA, and SPCA, like architecture conferences, as well as in machine learning, NIPS, CVPR, IIII, and a couple of times we also hosted itself as an event. So as I said, the theme of our workshop is what technological advancement happening, what sort of disruption we saw in the computing. Of course, when we actually started at that time, the CNN were the main workload, but we saw through the transformers, and now agentic AI and so forth. And our goal is always to get perspective from both sides to understand how, what are the big challenges and how do they evolve. We built up a broader umbrella organization called Sustainable Computing Foundation. This was started last year, and EMC2 is part of it. And our goal again here is to sort of broaden the scope and have competitions, collaborative sessions, and some kind of a research-based relationship. So the mission was this again. Now the SCF is in full flow. Our main goal was to how do we foster the collaborative AI research between industry and academia. There are some short and mid-term, long-term goals. I don't want to bore you. Today we have a very good, but think about EMC just as being one part of it. And this is the organizing committee. We have been for a long time. Satyam and me founded this workshop 9 years back. Sushant and Ananya helped us over the year, and we are thankful to have Prashant and Neil to help us this time. D-Matrix has sponsored this in last 4 or 5 years. We had other sponsorship, but we are looking for a sponsorship if your company wants to get associated. And we thank the audience and supporters. So I'll come back to this later. So without further ado, we have the first keynote speaker from Google, Partha, and Satyam will introduce him.
It's my pleasure to introduce Parthasarathy Ranganathan, commonly referred to as Partha. Partha is an engineering fellow and VP at Google, where he's also the area lead for hardware and data centers, designing systems at data center scales. Prior to this, he was at HP as a fellow and chief technologist at HP Labs. He has extensive publication record, including the famous Data Center as a Computer textbook. He's a co-inventor of more than 100 patents, and his work has been featured in very popular publications, including New York Times, Wall Street Journal, San Francisco Chronicle, and many more. He's been named, among many other accolades, a top 15 enterprise technology rockstar by Business Insider, one of the top 35 young innovators in the world by MIT Tech Review, and many more. He is a fellow of the IEEE and ACM, and is on the board of director of Open Compute. Welcome, Partha.
Thank you, Satyam. Okay. Everyone can hear me okay? Cool. Thanks a lot for the introduction, and thank you for having me here. So I know it's very early, it's 5 a.m. in where I come from, so appreciate all of you coming in bright and early. So my talk is titled A 6-Word Story on Sentient Systems and Sustainability. And so I thought I'd begin with, so how many people know what this line is? Electricity. So it's arguably one of the best opening lines of any book here. It's from Electricity by Charith. And I usually use it as a way to get a sense of the audience as well. So some people usually know that, like one or two people like Satyam who actually know it's Electricity. And then I have to ask how many people know who Charles Dickens is. And I have to go like how many people know what a book is, how many people know what reading is. So I think you can see that each generation of advances there. But if you think about Charles Dickens, it was the best of times, just the worst of times. It actually has a whole bunch of stuff after that. It's Spring of Hope, Winter of Despair, and it really talks about polarities. And so if I want to introduce this talk, I would say, can you complete the following paragraph in a way that talks about EMC squared? I would say it's the epoch of AI. It was the time of degrowth. And if I want to kind of go a little bit more fancy, I would say it was an era of change of eras, innovative efficiency, innovation. And so that kind of thing outline for the talk, and talk about an era of change, and talk about change of eras, and then talk about what it means for all of us in the community as well. Okay, so let's jump right into the part one, which is change of eras. And I want to talk about AI. I think you're going to hear a lot about AI in the next few days. But really, I think it's very clear we are at a once-in-a-generation point, inflection point in terms of computing. And what I wanted to do was to kind of talk a little bit about what does it mean for us as computer scientists. So at Google, my role is to design the planet-scale computing that powers all of Google services, Google Cloud, and how do you deliver services at scale with good efficiency, good reliability, with good scalability, and so on. And we've done that for about 25 years or so. But if you think about how the 25-year journey has gone, computing has kept evolving. And so if I start off with like something we use every day, Google Maps, we initially started off with a very, very static web serving model. And then on top of that, we started adding a whole bunch of multiple data sources, 3D models, satellite imagery, visualizers, synthetic data. We then added real-time stuff, weather, live videos, live traffic, personalization, context, collaborative filtering, social ads, instances, live translate. And then, of course, most recently, we added AI as well. And so the key technical concept I want to kind of highlight here is we started off with simple web search and serving, and we have progressively added more meaning extraction, multiple data repositories, more complex I/O movements, more complex cross-correlation. And so if you look at the continuum of microkernels that we look at, we started with simple ingress egress, went to more search, OLTP workloads, read, modify, write, and all the way down to queuing, classification, prediction, tensor analysis, and so on. And so that's fundamentally how we are evolving, and we'll continue to keep evolving as AI workloads continue as well. Now there's, you can see the same thing in search, you can see the same thing in photos, you can see the same thing in Gmail, enterprises, science, but rather than kind of go through stuff that most of you know about, I thought I would basically also, as a good wake up in the morning, introduce my special guest. Okay, so you know what's going on. That's pretty much the key takeaway from the first part of the talk. So what I thought we would do this is, what does it have to do with rethinking infrastructure? And so if you look at this picture here, what this shows is basically the number of parameters growing over time for the past 5 years or so. And how many people here have read the original Transformer paper? Raj just mentioned this as well. So from the original transformer paper to where we are with Gemini 3.1, we have gone from models which were millions of parameters to now trillions of parameters. And so if you extrapolate the growth rate of models over the last just 5 years alone, models have been doubling every 2 to 3 months. So 10x every year. So if you think about our classic definition of Moore's law, compute doubles every 2 to 3 years. And so what we have is this divergence in terms of how supply is scaling versus how demand is scaling. And you can see the same thing on the picture on the right as well. It's again another proxy where we basically have the growth of data and the growth of computing. And the high order bit really is that exponentials are diverging. And when exponentials diverge, you always pay attention because it tells you that there is a very interesting trend coming in. So that is in some respects the first problem that we have. AI is a fundamental platform enabler, it's a fundamental platform shift, and it requires a huge amount of computing, more than what we can provide and supply. But then we also have some challenges as well. And I talked about Moore's law earlier, but Moore's law as a construct is dead. And we see this whether it is in compute performance or DRAM dollar per byte or storage dollar per byte, or more importantly to this conference, the energy efficiency, power efficiency, and so on. And so on one hand, we have computing demand exploding, and on the other hand, we have supply starting to slow down. So that's a problem. But then we have additional problems as well. So if you think about some of the security challenges we've seen in the past few years, things like Spectre and Meltdown and so on, one of the interesting things to note there is whenever we have had these security problems, the mitigation has often involved rolling back some performance optimization. So we get a regression in performance. So not only do we have Moore's law slowing down, we actually have almost a negative Moore's law in terms of some of these security fixes. Same thing with silent data corruptions. So we published a paper at Google that's called Cores That Don't Count. And the idea really is we all expect 1 plus 1 to add up to 2 in your computer, right? And then it happens most of the time, 1 in a million times. Sometimes you have a bit flip, something error happens. But increasingly, as technology scaling has gotten more and more complicated, we are finding that the number of silent data corruptions is increasing exponentially, 1 in 1,000. And that is completely unacceptable. And again, the fix for silent data corruption oftentimes ends up with performance regression as well. So this notion that on one hand you have this growing demand, on the other hand you have all the supply side challenges, is really what we want to talk about. And what that means is we need to think about Moore's law, we need to think about compute scaling in a pretty fundamentally different manner. So with that as the context, I want to jump into the main part of the talk, which is how are we thinking about systems design, and how are we thinking about how we approach this problem. So if you think about how we want to think about systems for this new era of cognitive computing, machine learning, AI, really there's only two major concepts that you think about. How can I more efficiently design my hardware? And I'll talk about accelerators and velocity there. And then once I have the hardware, how can I more efficiently use the hardware that I have? And then we have scale and cloud, and we have amplified by machine learning and so on. But really, those are the two big components, and I'll talk about each of those next. So when we think about efficient design of hardware, what we've as a community embraced is custom silicon accelerators. And the idea really is if you can take your algorithm and implement it in hardware, because you have such specialization, you get very efficient performance per transistor, performance per area, performance per watt, and therefore performance per cost. And so we have CPUs and GPUs, of course, but how many people here know about the TPUs? Okay, everyone who's awake, good. And then video, how many people know about the VCU? One person, Sihang. Okay, so what Satya didn't mention is I'm also an Emmy Award winner, and the Emmy was for, technical Emmy was for the video accelerator. So we have built a video accelerator at Google that runs every YouTube workload, every Google Meet workload, and so on. So VCUs, we have accelerators for networking, we have accelerators for security, and so on. And each one of these accelerators is worthy of a deep dive. But rather than go into any one of them, I thought I would up-level it and say, what are we learning as a community in terms of some of the lessons from accelerator design? And I want to talk about 4 vignettes here. The first vignette I want to talk about is, even though we kind of tend to focus on custom silicon accelerators as a hardware component, we really need to start thinking about software systems co-design across the entire ecosystem. And again, ASPLOS, that's one of the key highlights of ASPLOS is the co-design aspect here. And so what we want to think about is how do we go not just chips, but think about chips to systems, systems to clusters. How do we think about scaling? How do we think about virtualization? How do we think about quality of service? How do we go think about the next level in terms of the compilers, the tools, and so on? And in particular, how do we think about manageability as a first order construct? I often joke that if an accelerator lands in the fleet and nobody uses it, did it really land? Kind of philosophical, if a tree fell in the forest and nobody heard it, did it really fall? And so it's really important to be thinking about manageability, test and deployment. How do we think about all of that for ML workloads as well? And then finally, when you think about co-design as a problem itself, it's fairly challenging because you're thinking about how do I design accelerators for big code bases? Often these are code bases that have been tuned for decades. There is no single hotspot. If you draw a pie chart of everything, there's slivers of workloads spent across various kernels, no single hotspot, pre-accelerator era API, very complex multi-threaded workloads. Thinking about accelerator design for those is fairly complicated. So the first thing really is this notion that you want to think about systems level co-design. And that's very challenging, but that's one of the important lessons you learn. The second, and likely very non-intuitive lesson here, is that capabilities are dramatically more important than efficiency. So what do I mean by that? So oftentimes when we are thinking about designing accelerators, we draw a pie chart of where the cycles go, and then we take the biggest cycles, and then we say, okay, I'm going to build an accelerator for that. But every single accelerator I have designed at Google, and any accelerator that has been successful at Google, has been successful not because it focused on efficiency, it's been successful because it focused on capability. And what I mean by capability is what are the new features that it allows. And so a great example is the quote here. When you look at AI accelerators, when we built our first CPU, the fraction of cycles that were used by machine workloads in the fleet was single-digit percentages. But the reason we built that was because one of our colleagues, he basically did this thought experiment where he said if every Android user in the world used 3 minutes of voice recognition, we would have to triple, quadruple the amount of capacity Google had at that time. And we needed to enable that new capability. Same thing with video. The video accelerator that I just talked about is pretty amazing. It saves hundreds of millions of dollars, billions of dollars in terms of cycles saved for transcoding. More importantly, it enables new capabilities, enables 8K videos, enables live videos, enables immersive videos, enables cloud gaming. So the capabilities that you enable that are currently not possible are more important than accelerating the current capabilities that you want. So paraphrasing a famous American president, ask not what you can do to reduce cycles, ask what the reduced cycles can do to improve functionality. So very, very important one. The third point, and this is something that I often get asked, is this notion of continuum of acceleration. And people ask, like, hey, you're in your 8th generation of your CPUs, are we done? Is there an opportunity for more accelerators? And oftentimes I point to this picture here, and this dinosaur picture, we tend to focus a lot on the head of the dinosaur, which are these big applications that we can accelerate. But there are also other parts of the dinosaur, the libraries, the systems infrastructure, and so on. And in particular, the long tail, and you can see that on the picture on the right, which is the picture on the right basically shows Google as an entire computer. And you can see that 1 out of 3 cycles at Google are spent on 5 functions or 6 functions: memcopy, malloc, protocol buffer, RPC, compression. And so how do we start thinking about these fine-grained accelerators? In the context of ML, how do we think about CPU and accelerators, and how do we closely couple them? What is the right architecture for how we do things? When we think about things like RAG, and when we think about infinite context, when we think about diffusion models, how do we start thinking about accelerators in the context of these more complex stuff? When we think about databases interacting with machine learning workloads, how do we think about the coupling of accelerators and so on? So there's a lot of opportunities still available for accelerators, both big accelerators, small accelerators, closely coupled, finely coupled as well. And And then the last point I want to make in this section is really this notion that deployment velocity is very important as well. So when I talked about Moore's law really has three variables. Performance doubles every 3 years for the same cost. Performance, cost, time. And if performance and cost are not scaling as well, maybe we can kind of optimize the time variable. And so that's what the picture on the right shows as various exponentials, where instead of getting 40% every 24 months, maybe you get 5% every 6 months or 10% every 6 months. And that's a good exponential as well. However, hardware design at this point is incredibly long. So at Google, when I talk to my software colleagues, they have like models. We've had huge model updates every 6 months. So Gemini 1 to 2 to 3 to 3.1 and so on. Hardware, on the other hand, takes years. How can we get to a place where hardware is also fast? And that is the way you rediscover Moore's law. You optimize the area under the curve by doing more faster hardware. And to do faster hardware, how do you kind of get to this release early and often, similar to big software releases? How do we think about co-design, modeling, testing, silicon debug, all at the same speed that we do software design? And one of the ways we do that is to think about architecture, think about systems design as a very modular, standards-based option. So what we want to do is to say, can I have modularity? Can I have fungibility, interoperability between how we think about systems? And so again, there's a lot of standards bodies that we invest in, mainly to get that interoperability and fungibility. And a lot of times people ask me like, hey, if you standardize, how can I differentiate? And you can still differentiate as long as you have a modular architecture where you can take individual pieces and then put your own piece in. And so deployment velocity and what I call innovation ecosystems, not just standards-based ecosystems, but innovation ecosystems based on modularity and fungibility are super critical stuff. Okay, so that was kind of the accelerator side of things. But we also have this notion of software-defined infrastructure. And the idea really behind software-defined infrastructure is very simple. What we are trying to do is to think about system design in a more disaggregated manner. And what we're doing is taking a traditional system and we are breaking it apart into its individual components. And so we have pools of compute, pools of memory, pools of flash, pools of power. And then what that does is, because you now have these individual building blocks that are very, very efficient, you get this efficiency through simplicity because you have multiple building blocks, simple and scalable. You take these building blocks and you combine them, and that composability gives you capability. So simplicity gives you efficiency and composability gives capability. And so you get this really nice option where you can both get high-level abstraction and you can get differentiation as well. And so we have applied this notion of software-defined infrastructure across Google, all the way from software-defined power, software-defined memory, software-defined servers at the node level, at the platform level, at the cluster level, at the data center level. And it's been phenomenal. So we've gotten multiple generations of Moore's law improvement by just focusing on software-defined infrastructure as a construct and optimizing what we call the efficiency layer in addition to the productivity layer. So now that brings us to kind of thinking about distributed systems as a whole as well. And again, if you think about distributed systems, you can break it into multiple epochs. You can think about the very first epoch of the birth of the internet. It was all sequential, bytes on the wire, relatively low concurrency. And then we went to client server, and then we went into the I/O era where we were thinking about things like remote SQL, concurrency, multi-threading. And then we went into what I would call the Google era, which is the massive scale out, no fault tolerance, sometimes in the hardware, fault tolerance and load balancing and NUMA and software, and focus a lot on multi-threading for performance as well. And now we are in the fifth epoch, which is all about accelerators. It's about tail latency. It's about how do you think about distributed runtimes? How do you think about multi-server and multi-threaded concurrency? And there's a lot of really open issues here in terms of designing the systems infrastructure of the future. How do we think about large-scale, tightly coupled, distributed, easy-to-program systems? How do you think about interactive serving, interactive batch processing, interactive query processing? And so in the ML world, again, there's a lot of concepts on classic distributed systems that need to be rethought, especially when you think about the stochastic nature of some of these AI ML workloads, how do we start thinking about managing those? How do we think about fault tolerance in the context of large-scale distributed systems? Because these ML workloads are bulk synchronous, they all come in at the same time, go down at the same time, they create a whole bunch of new problems. One of the problems we talked about in a blog post a year back was the problem with power management. And so when you think about power management and how you can look at huge bulk synchronous workloads, you often have hundreds of megawatts of spikes and shocks. Hundreds of megawatts is the power consumption of entire cities. And so the grid suffers when you have hundreds of megawatts. Thermal, the glue in your thermal packaging melts when you have these kind of thermal variations. The reliability in your servers get impacted pretty dramatically when you have these kind of thermal variations. So distributed systems, you could kind of think about hardware software co-design and manage that. And what our blog talked about is how we manage to smoothen out all of these loads here. Same thing with reliability. When you have silent data corruptions and one single server can bring down the entire bulk synchronous workload, that's a problem. And so again, there's a lot of things you can do at the distributed systems level as well. So Epoch 5 is going to raise a whole bunch of new challenges in terms of how we think about large-scale distributed systems in the context of AI ML workloads and what we do here as well. So the key theme I want you to take back from all of this is this notion that rewriting the rules of hardware software innovation means you need to think about hardware software co-design as a first-class citizen, and you need to start thinking about what that means for us as a community in terms of how we do things as well. And then on top of that, I want to kind of end with three other things as well. So when you think about trend number one, cloud, what does it mean to have AI ML workloads on the cloud? And if you think about the data that is getting digitized, most enterprises are in their very early stages of their AI ML journey. And what does it mean when you start thinking about AI ML workloads in the cloud? And in fact, interesting observation we had when I talked to a lot of customers, people usually ask me, hey, where are cloud customers using AI? And last year was particularly pivotal. Till then, I would usually say, well, they're kicking the tires, they're still kind of trying to dabble in what's going on and so forth. But there are four key themes that are emerging in terms of how customers are using AI in cloud. Number one, they're using AI to consolidate multiple data sources. So when you need to have very complex data processing and you need to look across multiple data sources, they're using AI for that. Number two, they're using AI for natural user interfaces. So when you want to have a customer chatbot or a sales chatbot and so on. Number three, they're using AI to kind of focus on the generative aspects of generative AI. How do you do marketing? How do you do sales collateral and so on? And number four, they're using AI for agentic AI. And oftentimes one of the biggest use cases is coding agents, but you also have data science agents, security agents, sales agents, and so on and so forth as well. And so this notion of thinking about AI plus cloud offers a whole bunch of new challenges and opportunities that we can be looking at as well. Second, on data, how do we think about storage and storage architectures for AI ML workloads? Again, at ASPLOS, I looked through the program, and we do tend to spend a lot of time on compute. We are starting to spend more time on memory as well, but we don't spend enough time on the storage hierarchy of AI ML workloads. And how many people here are students? Okay, few. So again, as students, as you start thinking about PhD topics and so on, I think this is an important area that is often underemphasized in our community that we should be looking at. And then finally, trust. Trust is always a big problem, safety and security. But in the context of AI ML workloads, you have a whole bunch of new challenges. How do you think about digital sovereignty? Last month, I was in India for the Global AI Summit. We had 250,000 people attend, which was pretty amazing. But one of the key things that kept coming over and over again is how do you think about sovereignty? How do you think about safety? How do you think about the right data that you train on? Because that introduces the appropriate biases in your models and so on. So digital transformation, data management, trust, all three fairly significant challenges that I think we need to be focused on. Okay, so you might be wondering, the title of my talk said a 6-word story on sentient systems and sustainability. So I've definitely been talking about sentience, I've been talking about systems as well. And so the reason I called it a 6-word story was basically, how many people have heard of Ernest Hemingway? How many people have heard of the 6-word story from Ernest Hemingway? One. So Ernest Hemingway was once asked as a challenge to write the shortest story possible. And he wrote the story in 6 words: for sale, baby shoes, never used. And so if you think about it, it's a very poignant, very powerful story in 6 words. And that's kind of become a meme, and there's a lot of people try to summarize movies in 6 words, people try to summarize their biography in 6 words, and so on. And so if I were to talk about everything that I said in 6 words, the 6-word story on the future of infrastructure for AI, AI-driven, software-defined, uncomfortably exciting. AI-driven because I talk about how AI workloads cause exploding demand and supply is not keeping up. Software-defined, the era of custom silicon and software-defined hardware, both of which needs very, very fine-tuned hardware-software co-design. And uncomfortably exciting. So the challenges we talked about with trust, with data, with cloud, and so on, tremendous opportunities ahead for us as well. So far we talked about systems for machine learning and cognitive computing, but the title has energy efficient machine learning and cognitive computing. And as Raj mentioned earlier on in the introduction, power and energy is a pretty big thing, right? And so if you think about some of the headlines, you find like, oh, we are going to run out of power in the grid. Oh, we are going to run out of carbon and we're going to blow up the earth. So there's a whole bunch of work around power and energy are key challenges and opportunities for how we think about future cognitive systems. So in the last 10 minutes, I want to spend a little bit of time talking about power and energy efficiency. And so I'm again going to use the same 6-word story, but I'm going to kind of go backwards this time. I'm going to talk about uncomfortably exciting, software-defined, AI-driven, and then I'm going to end with some key takeaways for us. Okay, so uncomfortably exciting. So I think the big challenge we have as a community in terms of looking at power and energy is this notion of sustainability. By sustainability here, I'm talking about a very specific environmental sustainability. And so this is not just how much power and energy we use, but also how much carbon, how much water, how much precious metals we use. And all of these become incredibly constrained resources that we as a community need to be. And so if you think about sustainability, this the Urban House Accord basically talks about 3 parts of sustainability. There's scope 1, scope 2, and scope 3. Scope 1 emissions are emissions that you burn at a company. Like if I have a diesel generator in my data center, the diesel that I burn is scope 1 emissions. Scope 2 emissions is the electricity that we consume and the carbon footprint of the electricity that we consume. So if you have a non-renewable source of energy in the grid, those are all scope 2 emissions. And scope 3 emissions, often called embodied carbon, are the emissions, the taxes that you associate with everything else in your manufacturing. If I buy a processor from a supplier, their energy consumption and carbon footprint shows up as scope 3 emissions. Now within Google, scope 1 is relatively small, and so we have that under control. Scope 2 is the electricity, and that's where all the work we've done on power and energy efficiency. Every TPU is like 10 to 50 times more energy efficient than using the conventional CPU, so we save a lot of electricity there. We have a lot of energy efficiency at the model level. One thing that many people may not know is when Google first introduced generative AI summary, so when you go to Google and you do a search, you get an AI summary at the top. In 12 months, we optimized the model to reduce the energy footprint by 95%. So 20x improvement in energy by just fine-tuning the model. And then we also have energy efficiency at the data center level. How many people have heard of the COE? 1, 2. Esha should know, obviously. So COE is what we use to kind of measure the energy efficiency of the cooling and power in our data center. So those are important as well. And then we also look at scheduling. Going back to what I talked about, the scheduling opportunities. We schedule power to go where the carbon intensity is the lowest. So we literally follow the sun, follow the wind. And we try to schedule workloads where there is more non-renewable power at any point in time. So scope 3 emission is often, if you look at every hyperscaler, whether it's Google or Microsoft or Amazon or Meta, all of them in their environmental report highlight semiconductor emissions and scope 3 emissions as one of their biggest components of emissions. And so we have some really interesting challenges for us to be thinking about. And so how do we think about reduced transportation, improved water utilization, minimizing hazardous materials, circular economy, and how do we think about cloud as an interesting way to optimize for environmental sustainability? So I think super important challenge that we should be looking at, and that's why it's very uncomfortably exciting. So by the way, how many people know the reference to uncomfortably exciting here? Nobody? So at Google, we use this term quite often, and it's attributed to one of our founders, Larry Page, and he talks about 10x moonshot projects, and he says, you know, a project is like an ambitious project when it is exciting, but it's also uncomfortably exciting because it makes you a little bit nervous as well. So definitely sustainability falls into that category. The second point I wanted to make was around software defined. And the point here I wanted to talk about is this notion of co-design for oversubscription and co-design for hardware software design of models for energy efficiency. So oversubscription, so how many people have heard of power oversubscription, power capping? Okay, a good chunk here. So power oversubscription, the concept is very simple, right? So it's the same thing that airline industry uses as well. So you oversell more than you actually have. And the reason you do that is you assume statistics is your friend, because across a large scale cluster of millions of servers, how likely is it that everybody is going to spike at the same time and everybody is going to not spike at the same time? So statistical multiplexing across nodes, across clusters, across data centers, oftentimes shows that you can over provision and get away with it. And so this is by far the most efficient way to get energy efficiency, is to basically oversubscribe. And at Google, we have a ton of oversubscription. We do oversubscription of power, we do oversubscription of thermal, we do it at the cluster level, we do it at the node level, we do it at the temporal level, and there's an entire series of oversubscription. But it is by far a very important area. And one of the things that we now see is that there is still a lot more opportunity as we go into the AI workload, but also opportunities to rethink what oversubscription means for these complex AI workloads as well. So oversubscription is a very important area. And then the second, we had a paper at ASPLOS a few years back called H2O NAS, and H2O NAS stands for Hyperscale Hardware Optimized Neural Architecture Search. And the idea really is, can I do the design space exploration of the model with an awareness of hardware? And of course, like any other co-design, it came up with a much better optimal point. But interestingly enough, the energy efficiency of this new point was 20 to 30% better than the energy efficiency of the old design. And so co-design is again a very powerful tool to get better energy efficiency even at ISO performance. And so it's something we should all be looking at more. And then the last bit, and if any of you come to my keynote on Tuesday, you'll hear a lot more about how we use AI for systems stuff. And it's a completely different keynote, completely different set of bad jokes as well. But if you look at how we use AI for systems, one of the really interesting observations is how we use AI for energy efficiency. And so earlier I talked about PUE, which is the energy efficiency of our cooling systems. And it's a metric that has been optimized pretty dramatically. So PUE of 1.0 is perfect, and we used to have PUEs of 2 and 3, and we have optimized it all the way from 2 to 1.2, 1.1 these days. And so we took an area that has been optimized so mature, and then by applying AI to think about cooling management, we were able to optimize it by an additional 20-30%. So the power of AI to do systems co-design, systems tuning for improved energy efficiency is pretty profound, and I think it's something for all of us to think more about as well. So there's tons and tons of opportunities in energy and power. And as part of putting together this keynote, I went and looked at my publications, and I've been incredibly lucky that I've focused on energy efficiency for a really long time. And I can spend an entire hour talking about all the techniques there. But I wanted to end with one of my favorite papers, and this is a paper from 2012, and it's called A Recipe for Efficiency. And I wrote it when I was fairly young, and very naive, and I was very thrilled today morning when I came into the casino. The guy asked me for my age, and I was like, oh my god, that's pretty cool. But anyway, back when I was young, I used to kind of think I knew all about energy efficiency, and so I wrote this paper where I said every paper on energy efficiency ever published in the world can be broken down into these 10 categories. So every idea that you have on energy efficiency, I challenge you, falls into one of these 10 techniques. And I told you I was young at the time. And so it is a really nice framework, and I still kind of go back and look at this quite often. And I'd encourage all of you, if you haven't read the paper, to look at that, because the paper systematically breaks down where does energy inefficiency come from and what are the techniques to do that. And so the top 5 techniques here, using a more power efficient alternative, scaling power to consumption, matching tasks to resources, piggybacking energy events to amortize, all of those are relatively straightforward, and we use that as a community pretty extensively. But what we don't do is the last 6 of those, this notion of matching design to actual intent. Thinking about high-level SLOs and how do we cut slack to be able to optimize for these higher-level SLOs. We see this particularly in AI/ML workloads, where they have fundamentally different SLOs. Training has different SLOs than traditional hyperscale workloads. And being able to be aware of these higher-level SLOs and think about how we optimize them gives tremendous opportunities for energy efficiency. At Google, that single line that I have alone has been responsible for a huge fraction of our energy efficiency improvements, is to fundamentally go and revisit your SLOs and think about what it means for them. Similarly, we talked about ensemble level holistic power optimization with power over subscription. But the other 4, trading off some other metric for power, trading off the uncommon case for the common case, spending power to save power, I think is something we don't do as much. And then finally, this notion of spending somebody else's power. All of those are very interesting ideas that, again, I can go into details on how we have been using that at Google. But again, if I look at the disproportionality across papers in the top 4 and papers in the bottom 6, we have tremendous opportunities. So with that, I wanted to conclude. So again, the key takeaway for all of you folks should be, we are at a very, very pivotal moment in systems, maybe even as a society. AI is transforming everything that we do, everything from consumer enterprise, science, education, creativity, productivity, entertainment, whatever, right? And computing is the oxygen that powers all of this huge advances in AI. And so if you think about computing, we need to really be thinking about computing from mud to cloud, and think about AI-driven innovations on computing, all the way from the silicon to the systems to the software systems to the cloud, effectively. And so we talked about custom silicon accelerators and software-defined infrastructure. Co-design and cross-stack collaboration will be key. And power and energy and sustainability will be super important. The good news is we have tons and tons of opportunities for us to still optimize. So if anybody tells you the earth is going to blow up tomorrow because of AI, you now know the answer. You can tell them, read Partha's paper, there are 10 techniques and there's lots of opportunity. So the earth is not going to blow up, we'll be fine. So the 6-word story, AI-driven, software-defined, and comfortably exciting. So let's write this story together. So thank you for your time. I think I left time for a few questions.
So exactly. Thank you, Partha, for really amazing talk. We have time. Actually, we have not. Since we might, I myself have a few questions. I'll kick off by asking, at Google's scale, we talk about SNO, different use cases and matching. Magically, if they have to, let's say, make 1 or 2 things disappear in terms of infrared efficiencies, what would they be? And the follow-up on that is, you saw Jensen talk about low and health periods. Is that kind of use case where there is low latency, assembly accessibility? Is Google also thinking about something along those lines?
Okay, so let's go to the second question first. So are we thinking about low latency inference stuff? The answer is yes. So we actually, so there are a couple of really major trends that I think as a systems community, we have all been adapting as well. So the first one is agentic. And are we responding to the agentic era of systems? And it turns out that actually needs a whole bunch of changes in terms of how we think about computing. So we have been pivoting to that. You heard Jensen talk about it as well. He talked about how Ruben is an agentic first architecture or whatever the marketing folks use there in NVIDIA. But it is an important thing, and so we are all looking at agentic stuff. And the second is inference. And so earlier it used to be that we just had training was our most important workload. And then we went into training and post-training. And then we went to training and post-training and inference. And now we have training, post-training, inference, and inference time thinking. And so the workloads will constantly keep evolving. And so the short answer is yes, absolutely. So one of the nice advantages we have at Google is that we get to work very closely with the model designer. So I know not just what Gemini 3 is today. I know what Gemini 4 is going to be. I know what Gemini 5 is going to be. And I know what 6, 7, and 8 are thinking about. And so we do factor all of that into our thinking. And so you've already seen us announce things about low latency inference, but you'll see us announce a lot more as well. So in terms of your first question, the first question was, given that I have visibility across Google scale, are there one or two low-hanging fruit in terms of inefficiencies that I would want to address? And I think I alluded to that very briefly. The notion of matching SLOs to the actual system, I think is the place where I would really look at. So we spend a lot of time looking at workloads and matching them to accelerators, like what you asked about inference and so on. But if you think about what do these workloads need, what is the fundamental SLOs that the SLOs stands for service level objectives, right? So it's what a customer might say, I need only 2 nines availability for my training workload. Why? Because I can restart and do all of that. Google workloads are optimized, Google systems are optimized for 6 nines of availability. So when you think about 5 or 6 nines of availabilities versus 2 nines of availabilities, that is a huge difference, and that opens up a lot of opportunities. So the low-hanging fruit to me really is understanding the SLOs and then trying to bring it back to system. Okay. Any other questions?
Thank you. Yeah, people have questions from over here.
Okay. Again, the students here, can you raise your hands? Okay, there are fewer hands from earlier that I asked. So, okay, so I do have a banquet reception drink ticket that I can give out for free. So anybody wants to ask a question, I will make sure. I'm not going to be around for the banquet. So how about that as an incentive? So any questions from the students? Yeah, go ahead. Thank you. That's a really good question. So, so the question really was, what do we think about cost efficiency? And there are two conflicting trends here. Cost per dollar, which is kind of traditional Moore's law stuff, is going down because hardware is getting more and more optimal. But also cost per token is going up because our software models are getting more and more compute intensive. And going back to what I said about compute is the oxygen that powers AI workloads. The more compute you throw at something, the more you get better. So there is this tension between the two. And honestly, I think it's a tension that's been around in computer architecture forever. I remember back when I started, I would always go to my software people and say like, hey, look, the more and more aggressive and compute efficient I make, the more and more software gets bloated, right? And so I think there is obviously this polarity, but one of the interesting observations to make here is that we are in the very early stages of kind of how we are thinking about AI models. And historically, software complexity and to some extent software bloat increases at the beginning when you're kind of letting 1,000 flowers bloom and experimenting, and then it kind of starts.
Anyway, you can see it in nearly doubled in 4 years, and we expect the blue part, which is the AI data centers, to increase dramatically in the next few years. Just as a data point, training a single model already takes more than 100 megawatts over many months in a cluster of 100,000 GPUs. So this is really sobering and really points out the scale of the problem that we have. Now, of course, ML workloads come in all sizes and shapes. Not all of them are big training problems. There are some that are compute bound, memory bound, network bound. There are different types of inference, combinations of inference and training. But I think that there are several principles that we need to listen to address this problem. These are not very deep principles, but they're obvious ones. So we need to leverage hardware accelerators to manage this energy boom, because hardware accelerators is the way in which we compute the most efficient, and also hardware integration, of course. We need to minimize data movement across the data center because that's where most of the energy goes, in moving data across the data center. We need to conserve costly memory. Now it's becoming very expensive and it will continue to do so. And we should not leave the hardware unused because that's a way to waste energy. And this happens very often, that the hardware is unused. So how do we make progress in this big multidimensional problem, which is to save energy at the data center scale? I'm going to talk about two aspects of the problem: compute and then communication. And this work is done in the context of the ACE Center for Evolvable Computing, which is an SRC DARPA Jump 2.0 center across the whole nation, but it's led from UIUC. So what about compute? What is the vision of compute? We will be seeing more and more hardware accelerators in data centers. The vision is to have many heterogeneous accelerators in the data centers. At the same time, we need to have new methodologies to generate, deploy, and reconfigure accelerators automatically. I'm going to talk about this because this is a key part of the solution. And we need smart compilers and runtime systems to program automatically these accelerators. On the communication side, we're going to need to have reconfigurable network topologies because the workloads are just too dynamic, efficient algorithms and collective communications, accelerators not just for the main parts of the compute engines, but also in network switches and smart NICs, and energy management frameworks that are able to understand the whole data set. And this will be the source, this will be the material of the rest of the talk. First, let me talk a little bit about the compute aspect and then the communication. So we are moving into many, many accelerators, and there is more to come, no doubt about this. Eventually, we're going to move into an environment where all the accelerators will be chiplets, and there'll be multiple of these chiplets in one big package, and multiple accelerators within the same chiplet. So this is what I call an ensemble of accelerators. A large package that contains multiple chiplets and then HBMs around it. And we're going to have multiple of those distributed across the whole data center. So that's the vision of lots of accelerators in the data center. Our goal is to have automatic generation of hardware accelerators. We want to have a design, domain-specific language that is probably Pythonic, where you specify the accelerator structure that you want, all the details that you want, and then a tool that generates from here an application-specific accelerator, which could be an FPGA, or also a programmable accelerator. This is what we call the evolvable accelerator generation. You have a company that in one quarter has a certain accelerator, and then the next quarter wants to design a slightly different accelerator. Rather than having a multiple year lead time, the goal would be to have a tool that is able to generate an accelerator automatically. And we have such a tool, and I'm going to put here in the right corner the PI that is working on this area. This is a work by Zhang at Cornell. The tool is called Allo, which is a framework to design programmable accelerators. It takes a Python description and it generates a high-performance programmable accelerator. So currently it works mostly on systolic arrays. So you specify the algorithm here, and then you augment the code with some customization code that specifies where the buffers are, how deep they are, how do you partition the computation, and many other several details here. And from there, it's able to perform the generation of an accelerator. And the accelerator is very efficient for this particular computation, very performant and energy efficient. But that's not enough. At the same time, you want to be able to automatically generate a backend compiler given an accelerator. So given an accelerator ISA, we don't want to have a team of tens of compiler engineers that work for multiple years. Instead, at the same time as we design the accelerator, we want to be able to design a compiler for this accelerator. Okay? This is a tool that we call ACT, Accelerator Compilation Toolkit, that given the ISA and the interface of the accelerator, it generates a compiler, a backend compiler. This is work, and this is what we call the evolvable compiler generation. This is work done by Charith Mendis, and the idea is that ACT takes an ISA description of the accelerator. It generates a backend compiler for the accelerator, which can be progressively more and more detailed depending on what is the detail of the hardware accelerator. So as the designers refine the accelerator, we can also refine the compiler for the accelerator. It currently works for tensor accelerators, meaning only ML accelerators. I think he's going to tell us more this afternoon about this. He designed a language called Tidal, which is a way to define the ISA of the accelerator. And from there, you can design a backend accelerator, backend compiler for the accelerator. The vision is to have an open source software framework to program multiple accelerators. So suppose that you have multiple accelerators, some coming from startups, some coming from established companies, and each of them can generate easily a backend compiler quickly for their own accelerators, starting from the same intermediate representation. And then, of course, on top of this, we have a compiler that takes a high-level language that generates this intermediate language. So much for the computation. What about the communication? This is crucial part of where the energy goes. A data center you can think of as a big system, excuse me, a big system that takes the data set and models. And it has many pieces. It has storage, right? SSDs distributed across the whole system. It has checkpointing, possibly. It has accelerators, CPUs, memory for the computation. It has a fabric composed of programmable switches, optical switches, and then smart NICs that connect the system. Well, energy leaks across the whole system. There is leakage of energy all over the place, places where we can improve the energy efficiency. So for example, we can have intelligent adaptive storage to improve the way we use data, taking data from the storage, improve data ingestion and pre-processing of the data. A runtime system that manages the diverse accelerators in an efficient manner and keeps them busy. Optimizations for computing collectives, communication collectives, very important. In-network optimizations such as compression and aggregation, reconfigurable topologies of the network, and adaptive smart NICs. I'm going to talk about some of these issues, but you can see that it's a humongous puzzle. It's very crucial to have efficient communication in a data center. As you know, you can think of at a high level that the operation of a DNN is composed of multiple compute and communication phases. So at the compute phase, the different accelerators work on their own different components, right? Different chunks of computation. Then there is a communication step, typically using collective communication, collective primitives such as all reduce and all gather, and then back to computation, communication, and so on. It's very important to have collective communication. So this is an example where we have 4 accelerators that generate their own data. Say each of them generates data that puts in this precondition buffer. Suppose that we have 4 accelerators, as I said, we divide the data into 4 chunks, and then we have an exchange and all reduce. And that means that at every accelerator, we need to get in the first chunk the sum of all the first chunks of all the other accelerators. In the second chunk, again, we have the sum of all the second chunks of all the accelerators and so on. It is important to have a most efficient communication framework so that we have spent the least time doing the communication and, if possible, overlap this completely with computation. There are many design choices in the network fabrics. There is the scale-up network inside the server and the scale-out across the servers. So different companies have different designs. I would say these are the classic technologies. For example, NVIDIA uses NVSwitch inside the server, InfiniBand across the servers, different variations of this. And then there are other companies that use more, I would say, more emerging technologies, including Google 3D electrical tori inside the server and optical switches across the servers. One very promising technology is programmable photonics, both inside the servers and across the servers. And this is work done by my colleague, Rachi Singh from Cornell. What's the idea here? Even within a server, as we connect the different GPUs or accelerators within the server, we have the ability to reconfigure the fabric inside the server in microsecond, in order of microseconds. This is very important because by reconfiguring this network, we can design the network or focus on the links that has the most need for bandwidth and disable those that are not needed for this particular computation. This is obvious for multi-tenant scenarios where obviously some of the connections are useless because you don't communicate between the different tenants. But even within an application, the different stages behave differently, and sometimes you need more bandwidth for some parts of the machine and some other times for different parts. So with this programmability, we're able to focus the bandwidth on the most important parts of the computation. Not only that, but as Partha said early on in the talk, there are more and more failures where one of the nodes, one of the GPUs disappears, right? So we can do in-place replacement of a failed accelerator in the order of seconds, within a second, by reorganizing, reconfiguring the link that communicates between 2 different accelerators. And in fact, what we do is not only change the links, but also reorganize the collective, the state of the collectives, to discard the state that was lost with the GPU that was lost and reuse whatever is left from the collectives. Anyway, this is very, very efficient and very energy efficient, which is the important thing here. And if we go one step further, as we have the different servers, they are connected through rails of optical routing switching, and we can enable or disable these links across the different servers, again, based on the needs of the application. So that's a very important part. The second thing that we need to do is, of course, improve the algorithms. And here there are many, many proposals. I'm going to talk about one example where we improve the parallelization of some of the algorithms. So as you know, we have multiple levels of parallelism for DNNs. We train them using data parallelism, pipeline parallelism, tensor parallelism. And one of the most challenging ones is the tensor parallelism, because it requires a lot of communication. Now, NVIDIA uses 1D tensor parallelism, while Google uses 2D tensor parallelism, as far as I understand. So 2D tensor parallelism is superior to 1D tensor parallelism, because 1D tensor parallelism requires a communication sending a shard from one node to all the other nodes. So the communication is order of P. While 2D tensor parallelism requires to send the shard only through your column, and through your row. So basically, you have less communication. The problem is that we want to be able to support this communication and overlap it with computation. That's what we want to do. So for this, we're going to use 2D matrix multiplication. Okay? So we have a set of TPUs or accelerators this way, and we have an interchip interconnect. This case is a Torrellas, 2 dimensions, right? And as you know, what we need to do is we need to partition all the 3 matrices. If we do A or C is equal A times B, we need to shard the 3 matrices across all the chips. And then we have different data flows. One of the matrices is going to flow vertically, another matrix will flow horizontally, and another one will remain statically. Right? So the way it's currently done is we have 3 steps. We have the first step where we do the computation vertically, the communication vertically. Then we do the computation, and then we do the communication horizontally. Right? So first, we do this, we all gather vertically. This is the collective communication. Then we do the computation, and then we do the horizontal reduce scatter at the end. But as you can see here, if we look at the time, we see that first we do the all gather, then we do the compute, and there's a dependence between it. And then there's a dependence to the reduce scatter. And that means that we don't overlap communication with computation. So last year, we introduced a new algorithm that we call mesh slice. And the idea here is to try to overlap communication with computation. And the idea is very simple. Instead of operating on the whole shard at a time, we slice the shard. So that instead of doing a all gather once, we do 3 all gathers. And we do 3 computations, and we do 3 reduced scatters. And then we do software pipelining. So first, we do, say, a third of all the all gathers, a third of them, using, say, 1/3 of the slices, the blue ones. We do the computation, and then we do the reduced scatter. But then we work on the second third of the slices, and we do the all gather, computation, and the reduced scatter. And then we software pipeline this, and you can see that in the same cycle, we do the reduced scatter of the first iteration, the computation of the second iteration, and the all gather of the third iteration. And this is a way to overlap most of, or completely, the computation with the communication. So this, we have overlapped the communication and the computation. So this is an example of an optimization that, by eliminating the stall time of the accelerators, reduces the energy. Big issue is the collective communications. There is a rich design space of network topologies that exists nowadays, and it's becoming more and more sophisticated. And there is the emergence of new collective algorithms that are topology aware. What's the idea here? Based on the topology of the network that I have, I designed the collective communication to be most efficiently for this topology. For example, if I have switches or hierarchical things, I use Blue Connect, I use Themis, and other things. The problem with this is that all these topology-aware collective algorithms are designed manually. And that means a lot of engineering effort to bring them up. And it's hard to adapt to changing topologies because errors, faults, and multi-tenancy, and so on. So my colleague, Tushar Krishna, from Georgia Tech has developed something called Thakker, which automatically synthesizes the collective communication without the need for user interaction. So given the topology that the machine has, he expands the network and then maps the collective in the most efficient manner in this model of the network. And based on that, it comes up with a collective algorithm. And with this, the idea is that we have a very efficient way of doing the collective communication that saves a lot of energy. A variation of this is the variation that Mohammed Shabazz from Michigan is looking at, which is handling the tail latency. It turns out that whenever you have a collective communication, the last message, the tail message, determines the execution time of the collective. And that's a problem. It slows down the collective communication. For example, we have a slow node, or we have a link that is particularly congested, and then at the end of the day, the message at the tail delays the already used communication collective. Currently, we're waiting until the last packet arrives. Let's ignore the slow arriving data. The last tail message, we ignore it. And that's okay, because machine learning models are resilient against some gradient loss. We don't need to be 100% reliable. So that's opti-reduce, eliminating the tail message of the reduction. But by doing this, we also have to change the algorithm of the reduction, because we cannot have, for example, the ring all reduce, which passes the data between the different nodes using a ring. Because if we end up losing the last message, we end up losing the 4 gradients. So what we do is we change the algorithm so that all the nodes talk to each other together at the same time. Basically, this sends X, sends Y, and this sends Z. And if we have a loss for the last one, we only lose the last data. All right, and finally, I want to talk about orchestrators, which is a very important part of the energy savings puzzle. Have a framework for energy efficiency that encompasses the whole data center. The problem here is that there are many dimensions. We have many knobs here. For example, we can tweak the model size, we can tweak the quantization, we can tweak the parallelism, type of parallelism, degree of parallelism, combination of parallelism. We can tweak the frequency of the accelerators, the batch size, and each of them affects the energy, the power, the performance, and the quality. So if we reduce the problem size or the model size, the energy improves, we save energy, we save power, we save performance, we improve performance because it takes less time to execute the model, but we lose quality. So we need to handle all these variations and all these dimensions. At the same time, there are many challenges in managing these data centers, these large language models efficiently. First, we have request heterogeneity. We have long inputs, long outputs, short outputs. There is workload dynamics. It's well known that the load varies with time. Anything that we do takes a long time. Any reconfiguration takes minutes. If we want to change the frequency, we want to change the way we scale in or scale out, the way we shot. So this is a big problem with potentially big gains. One of the projects I've been involved with, it's called Dynamo LLM. It appeared in HPCA last year. It's a framework for energy management. Here is the main idea of this framework. As we receive the requests, we examine what is the input size. We have a model that predicts the output size, and based on the input size, the output size, and the load prediction, we send the request to different instance pools. So we have an instance pools that has short input, short output. We have an instance pool that has long input, long output, and so on. And then inside each of these pools, we have a pool manager that has a model of a profile, really, that has profiled the model of the performance energy consumption for this particular type of request and knows the SLO of this request. And based on that, it decides what's the optimal frequency it should run on without violating the SLO. And then it sends the request to one of the queues that contains a set of accelerators that run at a fixed frequency. So we have here a pool that runs at low frequency, medium frequency, high frequency. And we send the request to the frequency level that's closest to its optimum, so that we don't have to change the frequency. So this is very effective. So the principles are profile-driven decisions, different instance pools for different types of requests, and hierarchical control of dynamic load. And with this, we're able to save substantial energy for the whole data center, 35%. This is a Microsoft data center. And the carbon emissions by 38%. So to conclude here, the community has developed many effective techniques for energy efficiency. This is a big puzzle, but we know a lot of the techniques. And I haven't even talked about all the changes that people are doing at the software level to optimize the particular algorithm, including scheduling algorithms, LoRa algorithms, and so on. So there's lots of things going on. The challenge here is, with all this, will industry adopt all these technologies? And if it does, will they do it in time to make an impact, given the crazy course that we're following now, with building such humongous data centers with huge energy consumption and problems with consumption of electricity and water and resources, without worrying about all the things that we can do. So this is all I have to say here. Thanks to many contributors that contributed to this work. Thank you.
We have time for the group questions. We'll pass the mic around. So I have one question. It's very interesting. You kind of, in the past, people looked at applications, and they said, let's design the hardware for it. Now you're saying, whatever the hardware is, you can do a better kernel, communication kernel. Have you come across a minimum communication substrate? Because rather than building all to all and so forth, is mesh enough where you can map all kind of kernels and you still gain the performance on that specific level?
So the reconfigurable networks is key to that, right? We don't want to have wasted links, necessary congestions, right? If we understand what are the communication needs, and we have a reconfigurable network, then we can design the system so that we use the resources most efficiently.
One question related to the optimization of the order reduce case that you mentioned, tripping out the last message. I assume that was for training all these you mentioned.
You suppose what?
I was assuming it's only meant for training because you mentioned gradients. Inference may not be that tolerant to accuracy loss. But even in case of training, yes, there is some built-in resilience in those models for accuracy loss, but doesn't it affect convergence time? And we are kicking the can down the road a little.
Well, okay, so there's a trade-off, right? So I think the consensus is that you can lose some of the messages without affecting the accuracy or the convergence significantly, right? So there is a tail on this thing.
Okay, any more questions? Let's thank our speaker one more time. We have a break aligned with hang on, socialize, network. We also have evening e-social, EMC2 organized e-social in the lobby from 6:15 to 8:30. So please come out for that. And we thank our sponsor, T-Matrix, who have some words here. Feel free to pick up as you kind of want. Yeah, looking forward to you on after this break session and then the evening session. So it would be, we will resume in 30 minutes.
Nice talk, Joseph. Did you notice something?
Oh yeah, like 10 people in the world knows about. Now the question is, how do you have an impact?
Hello.
Yeah, we can test out your.
Yeah, let's test out. Thanks for accommodating the timing.
Yeah, no
Otherwise,
worries.
I wouldn't have made it, you know.
So the good thing was we had paper system. It was easy to swap.
Oh, okay, yeah.
So not really
Okay.
kind of
Hopefully it didn't
big
short
deal.
anyone's
Yeah.
timing.
But yeah, thanks for taking the.
Very last minute. Yeah, sure, of course.
So
Yeah.
we thought it's a great way.
Sure.
Okay, let's test out
I'll need
Satyam. Do you have your laptop?
Let me. I have the laptop, but I need.
No, we
is
have
there
it
an
after
HDMI?
everything. No, we will do it.
Okay.
So me, let me.
Yeah.
Hey, Satyam. Can we give me your laptop? Right.
Okay, I'll take it next.
No, not that. Not the one.
Can I just put it?
Yeah, here.
Okay. Oh, this is better probably.
Okay.
Because Mac, is a bit
Let's see.
peculiar about.
Apparently today will not have any hiccups. It just
Yeah,
works right away. So let's.
So do you have a Zoom link or? Because they're gonna record my
handle
call.
that. I'll be on site preparing slides.
Yeah, sure. That's good for you. Just a second. I have a Zoom link also actually, but you prefer your Zoom link, I see. Okay, I'll send it to you. WhatsApp is good. Is there a network here?
There is this ASPLOS.
ASPLOS. Okay, thanks.
Yeah, this the password is capital ACM
ACM. Okay.
2026
2026.
exclamation.
Okay. I don't want the.
So they had two networks I was trying to get. One was unsecure, and then I was not able to run any of the cloud or chatbot.
Oh, okay.
on
Really?
unsecure.
Unsecure one. Okay.
Yeah, and then ask where is the secure one? These guys say secure is for internal. Don't we don't share that.
You don't
So
say it.
then I had to open my phone
Yeah.
and then kind of do the like hotspot or then any work.
Oh no. Yeah.
But hopefully this works.
Yeah. Sure. Let me see. Send it to Zoom. EMC2 Zoom forward. I guess I'll send it to Parthasarathy also. I'll send it to all of you guys just in case. Is this supposed to work right away?
Yeah, let's try it.
Just a second. So I have only 30 minutes.
Yeah.
Okay, I don't have a lot of time. I'll skip a lot of slides. Waiting for the host to start. I'm the host.
This break is also that we have to align what their guideline is so that
Okay.
we can start 2 minutes early. So we start at 10:30.
Sure, yeah. Yeah, I can adapt, don't worry. Yeah. Let's see, sign out.
Because we have 2 other talk guidelines.
Okay. Is Partha here also?
Say that again.
Is Partha here?
Yeah, Partha gave a keynote.
Yeah, I saw that.
Yeah, he is here.
Okay.
Probably be around as well.
Okay. It's a bit slow.
So we started this workshop about 8-9 years ago.
Yeah.
And this is the 11th edition, and that time we were thinking energy efficiency on embedded side and
Sure.
more on-device kind of thing. Now it has become so pervasive. Everyone is sort of the company securing the power.
Yeah, makes sense.
First thing. So it's sort of kind of good to have some time.
Yeah, it's a great topic, I think.
Yeah.
Yeah,
And every year we kind of kept changing how things are evolving. This year is more on infra-centric,
Okay.
large scale and so forth.
Okay. Secure connection. So that's what you meant. No security. That's okay. Who needs security anyway?
When did you arrive?
Oh, yesterday.
Oh.
Was it yesterday?
You used
or
to
the
be at
previous day?
CMU, right?
Yeah, yesterday.
So
This is
you're-
home,
this area is
home for me.
yeah. Second home. Now you're in ETS. So.
Yeah. But this feels more like home for me, you know?
Yeah.
Okay, let's see. I'm going to turn this on. So are you the host? I sent it to you just now. Otherwise, I'm going to go into your Zoom. Let's see if this works first.
Yeah,
Yeah.
it's ASPLOS.
Oh, it's good. Let's see if I can allow. Okay.
So I was at Rochester. And Engen was my in committee. You know,
Okay, yeah, of course I know Engen.
And Michael was my advisor.
Okay.
Yeah, Michael.
Michael.
Wong.
Wong, okay, yeah. Because there's this. Okay,
Michael
so you're
Scott,
not,
yeah,
there's Michael Scott also, right?
So
Yeah,
he was on system Sunday and Michael Scott was on the other side.
Sure.
And I was in ECE, so Michael Wong and I worked with Engen also. Engen was my not co-advisor. I worked with Chending. Chending was
Yeah, I know
on
all
the
those
compiler
guys.
side.
I've never been to Rochester, but I know those guys.
Yeah.
Yeah.
So that's 2008 to 2013.
Okay. You did your PhD.
Yeah.
And then you moved to.
So then I went to industry. So I was at Microsoft, Meta, I was at a startup now. I work on my own startup.
Okay, this is yours right now. Okay.
Yeah.
Nice to meet you.
Renara.
Okay.
So we are in kind of a more infra optimizing for cost and power.
Okay.
So aggregating a lot of hardware, building really better schedulers. So anything in software can improve performance. We are interested in.
Sure.
Because a lot of people are getting into the deployment aspect and they deploy, but it's easy to deploy, but as it goes on, they spend too much money.
Yeah, exactly.
So wherever we can save 10, 20, 30%, it makes huge difference. So we're kind of targeting that.
Okay.
And we are very early, but we are kind of right now self-funded. We got good interest from VCs. So yeah, very soon we will be collaborating. And so the goal was really to come here and see who we can collaborate.
Sure, yeah. I'll try to. Okay. Yeah. Okay. Yeah, we met last year, right? Good to meet you again. Yeah.
Yeah, Satyam and I were a team.
Let me see how I can do that. If you know how to do it, you can come in. Okay. How do I make you host? Which one? Okay, go ahead. You handle it. Where from this call?
So it's good, really good. Weather is nice now. Yeah. 2 days. I was Okay. Yeah, I'm here with some. Which are not here? All about it. Exactly. I think the 8 to 10 billion dollars will go in the next year. It's going somewhere, doing something, but then where is the other one? It is hard to do now. And what we've seen is that.
Just a second. I'll go back to the previous slide. Okay.
So they see this as a sort of a future booking or some kind of insurance chip. So let's just get at the rest of the weekend. We'll figure out what to do with it.
Yeah.
Because right now, exactly like almost selling, upselling. A lot of memory centric. I need to running the whole thing end to end is hard. Not anymore. And whenever you can do the command, it's sort of stupid.
Yes.
Let me see if this is. Should I turn? Did you set this up correctly, or this says muted now? It's okay. 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 I can stay muted then.
How are you? I didn't know you were presenting this. When I looked this morning, I see your name.
I didn't know I was until a few days ago, you know.
Nice, that's great.
Yeah, we have a workshop in the afternoon.
Yeah, it's something I think I might have found it. Congrats, final pass.
Oh, okay, yeah. Probably not myself because it's too much travel, you know. If it was actually the previous week, I'll be in Japan, so I could help out in Korea, but it's hard to find a week.
Yeah, good.
Nissan, she maybe help from it. It's Andreas.
Hey, I'm Randy. Nice to meet you. You're, what do you work on?
Mutlu. Why am I not surprised by the title of your talk?
I wonder why.
Looking forward to it. How are you? Haven't seen you in a while.
Good, good. Yeah, it's been a while, right?
Yeah, it's been coming to many conferences, very busy.
Are you staying for the entire conference?
First, yeah. I'm coming early. I have like a quota. Four days is all I can spare. Even that, I have a lot of help. You still travel a lot?
I travel a lot, but
I noticed you were the only talk that didn't have an abstract, so Satyam, he didn't twist your arms as bad as you twisted mine.
well, it was more last minute, or maybe I may have missed some emails. That's not saying,
I'm sure you guys are giving enough talks to this week.
hours notice. Yeah, I'm going to reconfigure the talk online. We're going to skip
It's
some
funny, I
slides.
actually asked, like a year back, I asked you, I said, you know what Parthasarathy does? And he said, I don't Parthasarathy marketing. And I said, can you write a Keynote Parthasarathy abstract? And it said, designing disaggregated data-centric data center. And then it said, Partha has a technique when he gives a keynote. First, he comes up with an alliterative title, and then his talk is always structured into three parts. His first part says, end of Mutlu, the world is falling apart. And then he has a hero's journey, and he always ends with go to that. Like, I'm very predictable. And I actually use that designing disaggregated data-centric data center. Cute title, I'm probably
I've seen it before, I think. I think mine will be pretty predictable by AI also.
Yeah, we have like Onur GPT.
I didn't try it, but I don't want to try it. I'll be back. Are we starting? Okay.
Okay, shall we start? I think we can start. Right? Hello everyone. So welcome back in the post-break session. It's my pleasure to introduce Professor Onur Mutlu, who is a professor at computer science at ETS Zurich in the Information Technology and Electrical Engineering Department. He's also affiliated with the Computer Science Department, and he was in the past a professor at Carnegie Mellon. His research in computer architecture and system and security, bioinformatics, his work expands and stretches between boundaries of application system, languages, and hardware. And his research tackles many issues in high performance, energy efficiency, memory subsystem, fault tolerance. So it's my pleasure again to welcome Professor Mutlu for his talk. Thank you.
Thank you very much, Raj, for the nice introduction. It's nice to be back in Pittsburgh. I used to live here. I still call this place home, actually. But I think ASPLOS managed a new height, which is, it took me to a place I've never been in Pittsburgh. I've definitely tried to avoid, but unfortunately, it didn't let us avoid the ID business getting into a conference. It's the first time I'm getting into a conference showing an ID. Although they didn't ask me because I look more than 40 years old, apparently. So I feel discriminated against right now. And also, some other people could not come in because they forgot their ID. So I think we should rethink how we hold our conferences. Anyway, with that, we should also rethink how we build our computers. I'm going to talk about memory-centric computing today. And since it's kind of a last-minute talk, I'm going to skip a lot of slides, but hopefully I'll summarize the major points. So this is the summary, actually. You can read this and then watch the video somewhere. There's a lot of data movement. This caused a lot of energy waste. This also caused a lot of performance loss because data movement is expensive in terms of latency as well. And we realize this performance loss a lot, and we complicate our systems to overcome this performance loss. We add a lot of techniques into software and hardware to complicate our systems, like out-of-order execution, many levels of multi-threading, many levels of prefetching, caching, and all of these are actually across our systems. This complicates the hardware, this complicates the software. Maybe there's a better way of designing systems if we actually didn't move the data as much. So basically, the processing of data comes at great system cost today. And if you look at a modern system today, a single node, most of a single node is dedicated to storing and moving data, more than 90%. It's good to question this, I think, and sometimes it's good to have a blank slate when questioning things. If you're a 10-year-old kid, and if you're designing a system, or if someone threw you how they designed the system, what would that 10-year-old kid think about that system? So if I gave this picture to a 10-year-old kid and asked the question, I'm designing this system, more than 95% of my hardware real estate is dedicated to memory, storage, and interconnect. What should be my bottleneck? They will probably tell you that since you're putting all of your resources over there, that should not be your bottleneck. Unfortunately, that is still our bottleneck in most systems. So it's good to have this mindset of a 10-year-old kid, in my opinion, especially if you want to fundamentally improve things. So I can give you a lot of data on this topic, but I'll pick one of these works that Partha
was part of at Google, and this is a beautiful paper they published in ISCA 2015, where they show that most of the time in essentially all of their data center workloads, a cutting-edge processor is waiting for data. It's doing what it's supposed to be doing, which is finishing instructions only 10 to 20% of the time. Again, be that 10-year-old kid, ask the question, I'm designing the system. The sole goal of the system for performance is to finish instructions, and it's doing that only 10% of the time. Am I designing a good system? This 10-year-old kid, without having any vested interest in anything, they would tell you, go design something else, because this is not doing what you're supposed to be doing. So that was performance. Energy is even worse. I borrowed this slide from Bill Daly, and this picture, you can argue with all of the numbers, but the disparity remains. Essentially, a memory access is much more costly in terms of energy compared to a complicated arithmetic operation. In this particular case, 800x more costly. Then the question is, do we want to move data to actually perform computation? Of course, it's an optimization problem. It's not dogma. In the end, it's a science, and you can figure out how many times you need to reuse the data so that you can amortize the cost of this energy differential. And if you actually do that, you will see that you need to reuse the data thousands of times. And many applications today that don't have that levels of reuse, and people have tried to design compilers for many years to get locality to that levels, but it's very difficult in many applications to get to those levels. And if you actually make the computation cheaper, which is what a lot of us trying to do by reducing the complexity of the computation, the disparity between memory and computation becomes even higher. So you get 6400x differential according to those numbers. And we're not even talking about storage over here. If the data is in storage, multiply that differential by another 10x. So 64,000x differential in terms of energy cost of memory access versus computation. This is a 32-bit edition. Today, people don't want 32-bit editions. They want 4-bit, 2-bit, 3-bit, or 1-bit ideally, right? Or less than 1-bit, if possible, in machine learning especially, right? So again, take that hat of a 10-year-old kid, show them these numbers, and probably the 10-year-old kid would go crazy. Why are you moving the data with that 64,000x differential? Right? Okay, so we did a lot of studies to understand the effect of data movement on performance as well as energy efficiency. This is one work that we did with Partha over here also. It's a bit old, but we looked at workloads that were used at Google at the time. These are TensorFlow inference, video encoding and decoding, and also Chrome browsing. And we analyzed the energy and performance that is essentially wasted on data movement. And we found out that on average use cases in mobile systems, more than 60% of the energy is spent on data movement. And if your workload is more intensive and if you accelerate the computation, this becomes much larger. So more recently, we repeated the study. Again, with Google, we looked at the commercial Google Edge neural networks executed on Google Edge TPU type of devices. And we figured out that more than 90% of the total system energy in those devices on commercial edge neural networks is spent on memory, especially in large machine learning models. So this is just an example. At the time, this is before LLMs. LLMs actually make things worse. I will show you with some data. This is with LSTMs and transducers. You can see that most of the energy is spent on DRAM and off-chip interconnect. And moving computation to the memory side reduces this significantly, as I will discuss later. So we have a fundamental problem. We're moving data a lot. We're processing data far away from the data. And to solve this fundamental problem, we need to enable mechanisms such that we can do computation without data movement or as much data movement, with minimal data movement. We want to compute where it makes sense, where data resides. And this requires us to think about computing architectures to be more data-centric or memory-centric. I'm not suggesting we should eliminate what we have done today, but this could be this is something that's missing. We don't have this data-centric paradigm in our computing systems today. And we have a lot of places where we can do computation. A lot of them are dark. So we're limiting our computation to a very small fraction of this SRAM-dominated chip. We can do the computation in most of the SRAM over here. And we can do the computation DRAM, computation storage, and computation sensors. And we can distribute that computation. And as long as we can actually manage the complexity, we can get much better energy efficiency and performance. And we're actually used to distributing computation. We're distributing computation across many accelerators today in a compute-centric manner. Why not actually have accelerators that are more data-centric as well, that are sitting next to large amounts of data, whether it's SRAM, DRAM, flash, or some interconnect. So we want to actually look at an accelerator-based model where we can program this more easily, like we've been doing today in the compute-centric domains. Okay, so this is a longer talk. I'm not going to talk about everything over here, but there's a lot to do over here, clearly. We want to enable memory to actually respond to us and execute parts of an application, an instruction, or function, So there's actually a granularity issue that needs to be discussed. How do you program this? How do you design the compute-capable memory and the controllers? How do you design the processor and communication units? Once you have computation capability on the memory side, how do you actually redesign, rethink how you design the computation accelerators? How do you design the software and hardware interfaces? How do you design the system software compilers and languages to take advantage of this? And how do you rethink our algorithms to actually match the computation capability that's there in the different memory devices? I think one of my favorites, which I'm not working on, but I would encourage people who do theory to work on, is how do we build a theory of computing that's more data-centric? Because the theory of computation today is very processor-centric also. We do big O notation, for example, that is essentially counting operations. But according to everything that I've said over here, everything points to the fact that counting operations is probably not the right thing to optimize. We want to optimize for something that, plus maybe data movement and data analysis. And that theory doesn't exist today. So it cuts across very deeply, I think, this processor-centric thinking. So this is not a new idea. People in the 1960s started thinking about it. Maybe there are older papers also, but these are some seminal old papers that talked about logic in memory or processing in memory. This is near memory processing. I will discuss that. What has changed today, I think, is we have nowhere to escape. We're basically pushed by applications and systems, and also requirements. Like we want to be much more energy efficient than we wanted to be in 1960s. We want to be much more sustainable. And I think we can improve all of the metrics we're interested by minimizing data. On the other end, from the lower levels, which is device and technology levels, we're having huge problems with memory technology that we've never had before in DRAM, especially today, like scaling issues like Rowhammer. I'll briefly talk about that. And these actually require intelligence and computation capability on the memory side to solve all. So we're kind of squeezed in the middle. We want computation for multiple different reasons. I will start with the technology scaling, but I'm not going to focus on this since we don't have a lot of time. I just want to point this out because I think this is really important. And this is an area where DRAM manufacturers are already adding computation inside the DRAM chips to protect against some of these scaling issues. So very quickly, we've been working on understanding memory scaling issues. We built a lot of infrastructure, FPGA-based infrastructure, to test main memory, different types of memory, DDR4, DDR3, LPDDR, HBM. And this is our laboratory at ETH. This is the older version. We actually have a lot more FPGAs doing testing right now, more than 100, 150 right now maybe. Well, my students probably know the number better. But basically, with this infrastructure, we did a lot of testing, and we open source these infrastructures to understand some of these technology scaling issues. This is the open source. We actually have a workshop on this or tutorial on this in the afternoon if people are interested in coming. We will cover how to actually do this testing, and we're happy to help anyone who's interested in doing testing. So one of the things that we studied with this is Rowhammer. I will not go through this in detail, but basically by repeatedly activating a row many times, enough times before the cells are refreshed, you can induce a bit flip in physically adjacent rows. Now this should not be happening. You should not get a bit flip. And this problem happens because cells are too small and cells are too close to each other. And as technology scales, we want more capacity. We want more cells per area. These cells become smaller and closer to each other. As a result, this problem becomes much worse over time. We have shown that the vulnerability of Rowhammer has increased by more than 100x over the course of 10 years, etc. So we wrote a lot of papers on it. I will not bore you with these because we don't have a lot of time. You can read these papers. There are other read disturbance issues that we discovered, like row press, which is different fundamentally in terms of the type of read disturbance. Basically, instead of keeping a row activated as frequently as possible, as allowed by the standard, you keep a row active for longer. And this turns out it actually induces a lot more bit flips earlier. So this increased the vulnerability significantly. And we keep discovering new things using this infrastructure. So why am I telling you all of this? Basically, to solve this problem, we've always argued that you need intelligence on the memory controller side or the memory side. I think controller, where does the controller belong is an interesting question to think about. Essentially, you need some intelligent control to fix these issues in memory. And we've written papers about it. And industry has picked this up. This is a paper from SK Hynix in 2023, where they showed that by having activation counters associated with each row in memory, you can count the activations that happen to each row. And if that activation count is greater than some threshold, internally the DRAM chip can take some mitigating action, like refreshing rows that are potentially victims. And this is implemented in real DRAM chips. It's a prototype from SK Hynix. It's essentially intelligence inside the DRAM, right? You have computation capability inside the DRAM. This is something that manufacturers did not want to do for many years, but they're doing it for technology scaling reasons. And I think you can argue about the goodness of this particular solution, but I think it's a solution in the right direction. It's pushing some computation capabilities into the DRAM to fix the problem. And this is standardized in JEDEC finally in 2024 in the DDR5 standard. And as far as we know, going forward, all the DRAM types will implement this sort of standard. Now, you could argue, of course, our solution is good, and we do a lot of research on understanding whether these solutions are good or bad, good in terms of performance, efficiency, security. And if you really want to make a solution strong, you want an even more intelligent memory controller. Basically, the complexity that you want to add in terms of computation to the DRAM chip or the memory controller increases so that you want to actually be safe and also low performance overhead in these solutions. Again, I'm not going into a lot of detail. I'd be happy to talk about these. The question always is, can we do better in these? And I think one of the things that's limiting us, both in terms of enabling DRAM to do this sort of maintenance task, as well as computation, is the interface that we have between memory and the processor, especially DRAM today. Flash is also bad, but I'm not going to talk about flash. In DRAM, unfortunately, we have an interface that doesn't allow DRAM to do operations by itself. So even refresh, for example, refresh is a very fundamental maintenance operation in DRAM. The memory controller, which sits on the processor side, needs to tell DRAM every 7.8 microseconds, or 3.9 microseconds if you're using HBM, refresh yourself, refresh yourself, refresh yourself. So I think we need to rethink the interface between processor and memory. This is one proposal. This is a slightly memory-centric proposal. It doesn't change the interface completely. But the idea is, if you can allow the DRAM chip to tell the memory controller, please stop. I'm doing something in this particular area that you're trying to access. And that could be a very fine-grained area. Try again later. So give a negative acknowledgement. This enables the DRAM chip to do many, many optimizations. It can optimize refresh internally. It doesn't need to get commands to do refresh. It can optimize row hammer protection. It can optimize computation, etc. So we believe that by changing the interface once with this sort of negative acknowledgement signal, you can enable a lot of optimizations. And also you can enable independent progress on the memory domain as well as the processor domain. This way, memory manufacturers can implement a lot of things without requiring any change in the standard interface or the memory controller. And that enables actually a huge breathing room so that the memory can progress. So I believe that interface needs to be rethought. This is one way of rethinking it. Okay, so there's more to come in this area. I can talk more about this, but let me see how much time we have. Okay, we have 12 minutes. I'll dedicate 12 minutes for the remaining part. It's fascinating that there's still a whole lot we don't know about DRAM. This technology has been around for 60 plus years, and we're discovering new things, like aging, I think is interesting. We've discovered variable read disturbance, which is read disturbance threshold varies unpredictably over time. This makes things a lot worse. I'm not going to talk about it in detail. More recently, we've shown that a single row activation actually can cause bit flips across 3 DRAM subarrays, 3,000 rows. So it's a more column-based read disturbance. It's not a huge problem like row hammer yet, but the scaling trends that we have observed in the testing of the memory chips in our lab indicate that this is becoming worse. And if you don't actually have a solution to this problem, this may become as bad as row hammer in the future. And we've also shown that if you're actually doing processing using memory in DRAM, row hammer becomes much worse. So I'm going to talk about processing using memory in a little bit, but you need to actually think about what kind of disturbance effects get amplified or created because you're doing processing inside memory technology. It could be DRAM, SRAM, flash, etc. It's all important to understand these things. Okay, I'm going to skip these things so you can read a lot of papers in conference. These are not our papers, but a lot of people keep writing papers, which is great. Okay, so if you're interested in these infrastructures, please feel free to attend our tutorial in the afternoon. Now let me talk about, switch gears slightly, talk about doing computation in memory. And I classify these into two fundamentally different approaches. One is processing near memory, and the other is processing using memory. Processing near memory is very similar to what we do today, in my opinion. You have logic and memory designed completely separately, using even separate fabrication technologies if you want. And you do it separately, but you put logic as close as possible to memory. The logic could be inside the DRAM chip. The logic could be next to each cell, next to the row buffer, next to bank, inside the memory controller, but closer than what we have today. Processing using memory is fundamentally different, and this is more recently developed, at least more recently published in the 2010s with memristors, DRAM, etc. The idea is you have logic, memory, but you forget about logic. You don't design logic. You use the analog operational properties of memory to perform computation. And any memory has this sort of capability. People have shown with many, many memories, SRAM, DRAM, NVMs, etc. This is fascinating because now you're actually not adding logic. Of course, you could combine both paradigms. And in my opinion, in the end, you need to combine both paradigms to get the best of both worlds. Let me quickly talk about processing near memory. This is easier to do, of course, because this is how we do things today, except there are some barriers when you actually cross some boundary because you're offloading computation to the memory side. So people are doing a lot of DRAM-based processing in memory with prototypes. We work a lot with the Upman company, a lot of papers evaluating their systems. I'm happy to talk about that. There's CXL, which enables computational offloading. So it's good to have these interfaces that enable computational offloading to the memory side. Let me go over a couple of works that I think are interesting. These are from our examples, of course. Basically, I think 3D stacking enables this sort of technology to be more easily done. If you have 3D stacked memory plus logic layers, and you have a nice logic layer where you can actually implement any type of logic, this logic layer has high bandwidth, low latency, low energy access to memory, and you can customize the logic layer for your application. And I'm going to go through a couple of works that describe this. This is one of the earlier works that we did at ISCA 2015. The idea is inside the logic layer, you have in-order cores, an array of in-order cores, and these in-order cores can communicate with each other with a network. And the idea is you don't move the data that you're updating in a graph, you move the function of the data that the in-order core essentially owns on top of it, on its stack. And by doing this remote procedure call-based programming, which is similar to how you program things in data centers today, you can accelerate computation, minimize data movement. Of course, you have limited memory available to you in a single stack. So if you want to operate on large graphs or large machine learning models, essentially you need to have a distributed system of these 3D stacked memories connected to each other. Okay, that's a one slide or 1 minute summary of a full paper, but we showed that you can actually get a lot more bandwidth to those cores that are in the logic layer over here compared to, at the time, any type of memory that we have, because you don't have this processor memory dichotomy, right? You're really combining near memory processing processors. And you can improve performance significantly, average across many applications, and also improve energy. Other works improved a lot of the, let's say, coarse things that we did in this work, though the numbers are actually much larger based on other people's works, which I'm not going to cover over here. ML inference is something else we actually were very interested in also, and we wanted to look at data movement bottlenecks in ML inference. This is a work that we did with Google, and we wanted to understand the characteristics of different models. These are edge models that are used at Google and HTPUs at the time, and we found out that there is a huge variation in terms of both arithmetic intensity that you see in different layers and different models, as well as parameter footprints. And designing a single accelerator that's compute-centric cannot really cater to this huge variation. So there's also huge variation within a single model across different layers in terms of arithmetic intensity and multiply and accumulate operations. So our idea was to actually design a heterogeneous accelerator, a family. In this particular case, we designed 3 accelerators. One is compute-centric. The other 2 are data-centric that are customized for different data flows in the different layers and models. And you have a software layer that decides what layer should go to what accelerator. And you can basically optimize the execution this way and minimize data movement. There's a lot more detail over here in the paper, but if you do that, you need to have a mechanism for classifying what goes where. And you can actually also reduce the complexity of the compute-centric TPU over here, edge TPU, because you don't need huge buffers to deal with more memory-intensive parts of a workload, assuming you do your classification right. So you can actually reduce the area cost of the compute-centric accelerator at the expense of having more complexity in your system. And we showed significant results. You can basically improve energy consumption by about 3x on average. Here you're doing layer offloading. So you're not changing the software as much as we changed in the previous work where we wanted to offload the graph computation, like parallelize it using remote function calls. It's function offloading. So it's easier to adopt, in my opinion. You can actually improve throughput and latency as well. More recently, we've been looking at large language models. These were published in last ASPLOS. In one work, we actually have very similar observations in the end. We looked at how to partition a large language model workload based on its characteristics. Again, we have a software layer that decides what should execute where. There's some very compute-intensive parts of a large language model, fully connected layers, that have to be executed in a compute-intensive processor like a GPU and TPU. They go over there. But there are some compute-intensive parts that are also memory-intensive, and they benefit from having a near memory processor that's actually pretty computationally capable. They go there. And then there are some parts like attention parts, KV caches. They are very memory capacity as well as memory bandwidth intensive and less compute intensive. We disaggregate them a little bit farther away so that we can get the benefits of memory bandwidth. And we have actually near memory processors over here, near bank processors, that have less compute capability to cater to those workloads. So in a sense, it's very similar. You have a heterogeneous accelerator that caters to different pieces of the workload, compute intensive versus memory intensive. Today, I think we're missing the memory intensive part, so it's pretty good to add the memory intensive accelerators. Okay, well, we also looked at very quickly in this work, eliminating GPUs, and we wanted to exploit the CXL devices and the communication capability in CXL, as well as computation capability in something like what SK Hynix proposed, GDDR6 PIM, which is a near bank accelerator that does multiply and accumulate operations near each bank. So multiply and accumulate operations are done there. More complicated operations are done in a more customized processing near memory units. And then we have primitives that are added to CXL to actually do better coordination across computation. And we see significant benefits in terms of throughput as well as cost in this work. I'll not go through this in detail, but it's good to question whether we really want extremely complicated processors in our systems when we have the interfaces where we can do a lot of offloading into our system. So there's more to be done in this area. There's also a lot of work from other people that I'm not discussing over here. Okay. In the remaining time, let me quickly talk about processing using memory. And I'm going to skip a bunch of things, but this is a key summary over here. We can do a lot of things using DRAM. And we've had a lot of theory on this, or theoretical simulation-based papers that show that you can do bulk request copying, initialization, and or not majority nor NAND. And you can do more complex computation using lookup tables. And the key idea is to use analog computation capability in DRAM. If you actually activate multiple rows, either in sequence or concurrently, then you perform data copy based on if you do it in sequence. If you do a concurrent row activation, you perform computation. And we have shown more recently that you can, even in commodity off-the-shelf DRAM chips, this is actually possible. I'm going to jump to that part because we don't have a lot of time, so I'm going to skip. This is row clone work that you may be aware of. This is Mbit work. Let me jump into how to do this in real DRAM chips relatively quickly. So basically, existing DRAM chips are already quite capable. These are not designed for computation. What we do in our lab is to abuse them, meaning you actually violate some timing parameters. And by violating timing parameters, you do like activate to activate timing parameter violation. This enables you to copy a row from one location to another location in the same subarray. So I'm not going to talk about that. We built a lot of infrastructure to look at row copy and random number generation. More recently, we've shown that you can copy one row into many other rows with almost perfect reliability. So this is almost perfect, which is fascinating. We're violating timing parameters, but we're getting very little error rates. And we have actually new results that show that you can do it 100% if you eliminate some things. So it's possible to do it in real DRAM chips. You can also perform NOT, AND, NAND, OR, and NOR. Let me go over the NAND, NOR, AND, and OR very quickly, and then we'll conclude. Basically, if you look at a DRAM chip, this is one subarray. I'm showing you only 2 rows in one subarray and 2 cells, and another 2 rows over here. This is sense amplifier. These are 2 different subarrays. And based on the operation of sense amplifiers, if you have a way of activating all 4 rows concurrently, then what happens is the sense amplifier compares the voltage of average voltage of A and B to average voltage of X and Y. This is theory. Now, if you actually are able to set the voltages appropriately in the DRAM chip, for example, let's assume that this is your reference subarray. You set the voltage, this voltage to VDD and this voltage to VDD over time. Both are possible in real DRAM chips by violating some. Well, the first one is easy. The second one is a little bit harder, but it's possible. Then the function you compute in the compute subarray is actually an AND function, meaning for the result over here to be 1, both X and Y should be VDD. Otherwise, you'll get a 0 over here. So you compute the AND function over here, by definition, you have the NAND over here, essentially. So you can change the function you can compute use on X and Y by changing the voltages that you store over here. And if you have a way of doing that in commodity DRAM chips without modification, then you can get this. And we have shown that by violating the timing parameters very carefully, you can do it using our infrastructures in our laboratory across many DRAM chips, especially SK Hynix, because some DRAM manufacturers don't allow you to violate timing parameters. Even though it's possible to do it internally, we just don't know how to do it externally. And we showed that, for example, row copy is extremely reliable, and row doing AND, NAND, OR, and NOR depends on what you do, but it could be quite reliable. I'm not suggesting that people should be using this off the bat because Reliability is extremely important, but the reason why we actually looked at it is to show that you don't do anything to the DRAM chip. You don't do anything to the DRAM interface, just change the memory controller in an intelligent way. Even then, you can actually get these functions in DRAM chips. Now imagine what could happen if you actually took this DRAM substrate and designed it to actually do computation robustly. In my opinion, that's really interesting to look forward to. Okay, at this point, I'm going to stop because we're out of time. I don't want to take over. I'm happy to take any questions.
Yeah, very interesting.
Hey, Onur, thanks for that talk. So you talked about a lot of different things. The one thing you didn't talk about is how you can use AI to design systems. I know there's a lot of people using AI to do reinforcement learning to do that.
Yeah.
Have you looked at how when you apply AI, this nice combinatorial space that you described, do we get to a better point?
Yeah. So that's an outstanding question. Thank you, Partha. And we've been looking at using AI to design better memory controllers, better prefetchers, etc. And we more recently are looking at how to actually use AI to distribute computation. And I think there is a lot of opportunity there, frankly, because some of the times it's very complex to figure out where a computation should be done. And if you can take advantage of reinforcement learning, or maybe LLMs actually going into the future with lightweight overheads, I think you can do much better in terms of where to do what computation. I'm sure there are some other opportunities also, like using AI to discover some other functions in DRAM that we may not know of. Yeah, thank you.
Okay, let's thank our speaker. Where is the? Okay, this is the one, right? Why don't you second? I'll introduce it. Our next talk is Efficient and Scalable Agentic AI with Heterogeneous System by Zain from Gimlet Lab. Zain is a co-founder and CEO of Gimlet Lab and was previously at EMVP at Pixie, open source at Untitled. And he's also an adjunct professor of computer science at Stanford and was an entrepreneur in residence in Benchmark before co-founding Pixie. He has a PhD from Stanford and helped build hyperscale data and AI and Google, Infrastructure, and NVIDIA. It's my pleasure to welcome him to this talk.
All right. Can we hear this? Okay, great. Hi everyone, I'm going to talk. Oh, computer wants to do something. All right, great. I'm going to talk about building efficient and scalable agentic AI with heterogeneous systems. And in particular, the goal of this is to take a look at some of the energy and performance challenges and see if we can apply heterogeneity to get some better results, right? And I think there are a few talks that have been alluding to this type of problem today. So hopefully this will kind of line right up with that. All right, so just to context that for everybody, what are agentic workloads? So typically agent workloads involve some kind of, potentially user interaction, or they could also be agent-to-agent interaction. Here's like a very, very simple case where there's a voice input, there's some speech to text, there's an LLM, there's a text to speech, and then the LLM performs a web search, which is usually done by a tool call. These systems can get, the agents themselves can get very complicated these days where there's multiple different paths, multiple different things happening. And one of the challenges of this is that there's actually a lot more AI models running because increasingly these agents are just driven internally by lots and lots of AI models. And the main thing is this stuff is going pretty mainstream. I think everyone's probably even used many agents to write code. And another big part of it is that the part of compute that's being used for inference is significantly increasing. Most of the GPUs were used for training in the past, but now with the vast majority of the workload is inference. And they've seen pretty rapid growth in framework usage. So the question we got to ask ourselves is that we're spending a lot of money on this, and presumably a lot of our energy budget. And if you take a look at this, in 2026, people are estimated to spend somewhere around $650 billion for CapEx. But people's like fleet utilization is somewhere between 10 to 50%. So depending on how you look at this, they're wasting probably the vast majority of their money and vast majority of the energy available in the system. And just for to hammer this point home, inflation adjusted, this is actually more than was spent in the entire U.S. highway system. So we are actually like doing a pretty big infrastructure build out, like a government scale infrastructure build out, but with a ton of different companies. Okay, so if you take a look at agentic workloads as a whole, they're actually pretty heterogeneous. This is kind of an eye chart, but I'll kind of point out a few different things over here. We pulled out a few different things like LLM inference. There's aggregated inference, which is when you're trying to run different phases of the workload on the same machine. We'll talk a little bit more about what that means, but typically that's pretty high compute. You can actually disaggregate inference to run prefill and decode, and that'll allow you to basically run all the high performance workloads and the high memory bandwidth workloads separately. And this way you might be able to utilize hardware more efficiently. There's also things like KV cache storage, tool calls. Tool calls typically don't need any GPU systems at all. They're mostly done on general purpose compute. And then there are other types of models, like diffusion models that have, I don't know why it keeps cutting out. Sorry about that. That have very different performance profiles. So the question is, if you take this chart, how do you actually build a system that can go and apply this information and actually map it onto the appropriate hardware? So if you go back to the original agent we had, we can conceive that we can build like an orchestration and runtime system that'll basically map different phases of this workload to different systems. So an example of this is something like speech to text. Might even be able to run on the consumer side. You don't actually need necessarily cloud resources to do this. Hopefully that's not too controversial. A lot of systems already do something like this. You can break up LLMs into prefill and decode, where you can use either a high compute. So this would be a GPU with a lot of compute density, but relatively lower memory bandwidth, and LLM decode on a very high bandwidth system. For those of you who are paying attention to GTC last week, Jensen was talking about Grok, which was a way to basically take this very high bandwidth system to do LLM decode. There are a lot of challenges with that, and we'll talk about some of them in a few slides. And then you can offload all the tool stuff to the CPU. And then again, you can go back to on-device to do text-to-speech. So hopefully what you're starting to see over here is that there's this agentic data flow, and you can basically take this data flow and think about how to map it to different hardware and different runtimes based on the characteristics of the workload. And if you actually take this a step further, you can actually just think about making this like a convex optimization problem. And of course, like these days, you can probably just use AI to figure out what the best way to map these workloads is. But basically, you can think about your objective function as minimizing the total cost. One way I like to think about this is that if you have a particular workload which can get decomposed into a task graph, you need to buy certain resources to make this workload happen. So you need to buy a certain amount of compute, you need to buy a certain amount of memory bandwidth. Oh, let's try again. I have no idea why it keeps glitching. Okay, I killed it now. Let me just do HDMI correctly. All right, let's hope this is more stable. Okay, so the way I think about this is you need to buy like a certain set of resources, right? You need to buy some compute, you need to buy some memory bandwidth, you need to buy some network bandwidth. And the way you can think about this optimization problem is basically what is the marginal cost of buying each of those resources? So if you have a very high, if your workload requires a lot of compute, not a lot of memory bandwidth, you'll try to buy resources where the marginal cost of compute is very low. And ultimately, this turns into a convex optimization problem, and you can set up some constraints on latency, throughput, and whatever your resource capacities are, and then minimize the total cost, which could be some combination of execution costs and also energy or maybe total cost of ownership. And fundamentally, there are three building blocks we think about to do this. The first one is to create a data flow representation. In our system, we actually use an MLIR dialect to basically represent all components of this graph. And this is represented at multiple levels, where we kind of have the high-level agent flow, but we also have every single piece of the model be able to decompose in a second level. That way we can go and optimize specific phases of the workload. Then there's a data flow orchestration and serving system, where we basically go and partition all these workloads and dynamically schedule them. The challenge, of course, is that moving models in and out of machines takes a long time, so you can't actually do this in real time. So you take some guesses, and then you'll basically redirect this over some period of time. And the last step is the data flow compiler that will take these high-level workloads and then partition and send them to different hardware. One of the things that many people in the audience probably realize is that it's really hard to map workloads onto different types of hardware. Our data flow compiler does lure things to specific hardware, but there's really no substitute today from running optimized code for every single system. The good news is that you can actually use some LLMs to try to generate optimized kernels and optimized computes for like different pieces of hardware, and we've had some success in doing that. At a high level, we don't need to run through all the code, but basically you start with some very high level agent dialect, like over here is LangChain. You then convert this into some pretty high level calls, like here is like some memory load happening, and memory over here means it's the LLM memory, not like literal memory. LLM call, tool calls are happening and where things are getting stored. You can then decompose this into a further level where you take a look at all your pre-filled decode, and you can generate several different versions of this, and then basically map this onto different hardware. From a high-level perspective, if you look at it from a different way, you basically have a compute graph, which goes to the MLI representation. You have your set of resource information, like what resources do I actually have available that I can use. You can then plan and optimize this, and then schedule. The compiler over here will actually generate the device-specific assets I can deploy. The compile deploy loop is not particularly fast. You typically want to collect profile information to do offline rescheduling of the workloads based on what you're actually seeing in real time, real execution. Just for completeness, I'll kind of show you what the high-level execution system looks like and then get into the results. Basically, there's an API server. There's off-band processes, as shown, that do the planning and scheduling. But really what you want to do is have some kind of request routing system that will route you to the correct type of machines. These machines are in different colors to represent different different capabilities. And then basically we can route the request to different capabilities based on what the workload characteristics are. So for example, if you see like a coding request which has a very, very high input sequence length, you might want to send it to a different compute graph than something like a chat request which has a much smaller input sequence length. And all of this is typically tied up using a high-performance interconnect. And because we run across different heterogeneous machines, we're pretty much tied to Rocky or some variations thereof. And then there's cache management to basically keep the system up and running. So here's kind of a very high-level representation. This is relatively old. It's from the previous paper I showed you. This is taking a look at Llama across like major accelerators from NVIDIA, AMD, and Intel. And this is kind of showing you the TCO benefits. The TCO includes like the cost of the hardware and also the energy cost. Some of this is actually skewed by certain hardware over here being a lot cheaper than others. But this line over here is the Hopper baseline. And very specifically, this is looking at doing pre-filled decode disaggregation, which is a form of pipeline parallelism. And over here, the interesting things that we see over here is that you can actually take new gen systems and mix it with some old gen systems and basically get a relatively good TCO. And part of the reason you can do this is you're exploiting the fact that some of the older gen systems actually have reasonable memory bandwidth, and you don't have to pay for the cost up front. So then the question is those are looking at pretty traditional accelerators. The next question is, what if we use something, that's more like SRAM centric, right? And I think this is like all the rage in the industry these days, where people are talking about Cerebras, D-Matrix, et cetera, where you're trying to actually run these models on hardware where there's a lot of SRAM capacity. And what this allows you to do is actually just reduce your data movement. I think Onur was just talking about how expensive data movement is, and this is a little bit in that direction where you try to keep the data centric to the accelerator rather than moving it to and from DRAM. The challenge, of course, is that SRAM capacity is usually pretty limited, but the bonus point says SRAM is usually pretty co-located with compute, so you have a lot more memory bandwidth available. Whereas in most DRAM systems, the memory is off to the side, and it's relatively expensive to access. If you take a look at the physics of this, you kind of run into this problem where the compute scales as the square of the length of the chip, but the amount of bandwidth you have scales linearly, so you almost always wind up with some kind of compute memory bottleneck. Obviously, some of the stuff can get solved with stacked DRAM, but those will end up looking a lot more like the SRAM-based systems, just with slightly higher memory costs. So an interesting thing we found is that if you take a look at these SRAM chips, because of their high memory bandwidth, and if you think about them on like the Pareto curve of like what is the cost of my memory bandwidth, they're at a very different point of the curve because they have relatively cheap memory bandwidth, but relatively high cost per capacity. So if you mix these with GPUs, you can actually get pretty interesting trade-offs. So here's an experimental result, and I know I've been talking a lot about prefill and decode without really going into details, but this kind of goes into that a little bit. So most of you probably already know, but the way prefill works is that you basically give the entire prompt, and because the prompt is usually relatively large, you can basically run the entire prefill step in parallel, and this allows you to have like relatively high arithmetic intensity. So prefill is typically compute dominated. There are some cases where it won't be, but it's typically compute dominated. And then there's a decode phase where you basically will generate a single token at a time. It's an autoregressive step. So for every single token, you will have to basically refetch the entire model and the entire cache, which means that you're producing a single token after reading like gigabytes of data or more, depending on the size of the model. So what ends up happening is this step is like pretty slow. And this is like when you're seeing the model output your tokens one at a time. You're basically memory bound the entire time. So one of the techniques to reduce this is to use like disaggregation, which is what I was talking about earlier, where you actually run that on different accelerators that are slightly faster. Another technique to reduce the time is to do speculative decoding. Right? There's only like I feel like there's only a few things in computer science that people think about, right? There's either like caching, speculation, etc. Speculative decoding is a technique where you're like, well, I have this big model. What if I don't want to run the big model the entire time and I build a smaller model that can just predict the output of the big model, right? So then what you do is you run a much smaller model that'll go and predict the output of what the large model would have been, and then you do some number of tokens, and then you run a verification step. And because the verification step has all the tokens in parallel, it looks like a prefill. And the first like incorrect token you get is the new next token you're gonna get, and then you'll rinse and repeat. So the goal over here is that you can basically, depending on your speculation length and how many tokens are accepted, you can actually get a pretty good performance benefit because the speculator is very small. So I'm gonna talk a little bit about the experimental setup here. So there's 3 different things that are being tested. The first one is a normal prefill decode disaggregation. So there's a prefill pool and a decode pool. And then there's a speculative decode system where there is a prefill pool, decode pool, and a verification pool, all running on the GPU. And we're running them on different GPUs because there's actually performance advantages of doing that because the request sizes are much more similar if you run them on different pools. And the third one is we actually tried this with the D-matrix chip. We've also done similar experiments with other hardware like Cerebras, etc. But basically, you run the speculative decoder on the D-matrix cards. This is a good proxy for what it looks like if you have a lot of SRAM available. And you run the verification pool back in the GPU. Remember, one of the challenges with any SRAM-based system is you don't have a lot of memory, and the cost of memory is relatively high. So what you really want to do is see if you can run small models on there instead of running the entire large model. This does not present well. So anyways, excuse the glare, but basically this is looking at the throughput per kilowatt versus interactivity. if you look at the x-axis, it's basically telling you how fast a single user's response is for like your LLM, right? And typically, like 500 tokens per second is a good response time. If you get to like 1,000, that seems to be like the holy grail these days for people wanting really, really, really fast LLM responses. And the y-axis is basically taking a look at the aggregated throughput with prefill and the decode stages and how much that's costing you per kilowatt. So there are 3 lines over here. The first one is the prefill decode disaggregated on GPU only. We did not do the aggregated versions because we don't typically run the aggregated versions. But the green line over here, which is green for no particular reason, is the GPU only line. And then the blue line over here is actually running the spec decode on the GPU, right? It wouldn't be fair to compare the non-spec decode version with the spec decode version because they're running different workloads. And this spec decoder on average accepts 4 out of every 5 tokens. And then the red line over here is running the GPU spec decoded with the matrix, same acceptance ratio. And they're all running GPU-OSS 120B, and the spec decoder is 1.6 billion parameters. So an interesting thing over here is that you'll actually see for like a similar throughput, and you can pick different points in the curve, right? And it'll give you slightly different results. But I kind of picked like the middle of the throughput curve here. You'll get about a 4x bump by moving the spec decode. And people have cited anywhere between 3 to 5x if you take a look at other literature. And then if you actually move the spec decode to a new matrix, you get like another 3.5x bump on top of that. And all of that's basically coming because you're able to offload this and run this very quickly on another sideband accelerator, and there's very little data to ship back and forth. So it kind of supports this mode of like, I have some high bandwidth compute available, like high memory bandwidth compute available. I can do the work on the high memory bandwidth system and then ship back like the few tokens that I care about. So it satisfies the thing where there's very little data movement in either direction to get there, but most of the compute is localized to a single accelerator. And then if you look at it a different way, which is, let's say I care about 500 tokens per second of interactivity, you can get about 4x more throughput. So a way to think about this is actually, if you take that previous chart, you can actually like just look at it in terms of where you're spending time. So there's prefill, there's decode, spec decode, and verification are the 4 stages here. Obviously, in the disag case, you're only doing prefill and decode. The prefill side is, while there are actually a lot more tokens, it's very fast because you're doing them all in parallel, basically. And then the decode side is auto-regressive, so it's slow. If you take a look at the spec decoder with the GPU only, you'll basically spend a fair amount of time doing the spec decode because you still are memory bound, and the memory bandwidth of the GPU is still relatively limited compared to just reading from SRAM. The verification time, if you take a look at both these cases, is approximately the same because the verification, the only difference is that, well, actually in all these cases, it's moving around over the network, so it doesn't actually change all that much. So the verification time remains the same. It's just that the spec decoder gets way, way faster. And then, if you take a look at this chart, you're going to start seeing there's some Amdahl's law limitations here. There's not much more you can do to reduce the decode time before it doesn't really impact your overall performance. Cool. So one last data point I have is actually spec decoding when you can actually spec decode a much longer length. So this is a different use case, which is like coding. In coding, you can actually usually spec decode much more because when you start getting to the beginning of your Python function name or something, it's really not that hard to predict the next 10 tokens. So in this case, there are 12 out of 20 that were accepted on average. You'll notice that the performance benefits on the offloaded side are actually substantially higher than on the GPU side. And part of the reason for this is a little bit subtle, is because over here there are only 12 out of 20 tokens accepted. And you're actually seeing the increase in the GPU time to generate the 20 tokens starting to impact your overall efficiency, since you're only actually accepting half the tokens. Now, on the SRAM style system, it's actually a lot better because you can basically generate those 20 tokens very, very quickly And what you're actually seeing is just the overhead of moving data in and out is getting amortized over more tokens. One interesting thing I can add over here is that this is doing a single level of speculation. There's many different schemes. You can actually go start doing some kind of tree speculation. You can start speculating your speculators. Actually, there's this thing SSD by TreeDAO called speculative decoding, where you can actually speculate your speculative decoding. And if you can do stuff like that with an SRAM chip, you can potentially generate a ton of tokens that you can verify back in parallel. All right, so that's basically all I had. But future work is trying to do more better cost-based modeling and stuff, and trying to predict performance better, so we can actually allocate these workloads more efficiently and guide the scaling decisions. There's a lot of interesting work around figuring out how to distribute these workloads across different data centers, and how that would look like, especially if you have more edge data centers versus hyperscale data centers. And the last area is doing edge data centers. Basically means they're a few megawatts, typically not the hundreds of megawatts of hyperscale systems. And then the last one is, of course, going to the true edge and how you can allocate workloads like cell phones or laptops. Anyways, if you're excited about problems like this, we'd love to chat more. I did allude to there being some work around doing automated kernel generation and stuff. So please check out, there's another talk in the ML Bench workshop on program synthesis for different AI accelerators. And that's it, thanks.
Thank you, Dan. We have some time for everyone. 2 questions.
Yeah.
Hi, thank you for joining us. Choukse is Mendis from University, and I have a question concerning the first part on the complex organization for the agent AI system. Always one of the key features for the AI system is highly dynamic. I'm kind of curious, for this kind of complex organization formulation, how easy it is to deal with dynamism across all different levels.
Yeah, so that makes sense. So one of the things that you do about dynamism is that you try to take a look at different types of workloads. So there's the disaggregation of here's where my tool calls are going to run. And then you can also profile information about your typical model characteristics, right? So you need to run it for a little bit so you can figure out what is the distribution of your data. And once you have the distribution of your data, you can basically go allocate certain pools of machines or certain set of machines to go figure out this machine is good at doing high context workloads, and this group of machines is better at low context workloads. And you figure out what that distribution is, and then use that to allocate the different graphs. And then you basically make a dynamic routing decision to figure out which machine you want to find.
Okay, essentially convert it to a statistical.
Right, you have to convert it to a statistical thing because there's no way to capture that dynamism in real time, especially because it takes at least these days a fair amount of time to move models in and out of chips. Right, because if you're thinking about a trillion parameter model, it actually can take several seconds, if not more, to move it in and out.
Any other question? One question I have, people are talking about disaggregation. People before was well known, now we are talking about decode itself. How hard is it for the tool chain, the distributed system, compared to just put down only development versus going all kind of hardware? And so, any idea about the developer efficiency of overall brings up and deployment?
Yeah, so the complexity is pretty high for various reasons, especially because there's pre-filled decode disaggregation, which only involves moving KB caches, and that itself can be kind of complex because different hardware systems might assume different formats for the KB caches, so then you have to add all these transposes and stuff everywhere, and that has a performance impact. So there's a fair amount of work on figuring out what the best way to do this is. The other challenge you typically run into is you need to have some kind of communication compute overlap, and if you don't do that, your latencies will be really bad. It's much harder to figure that out across a diverse set of hardware. And the third point is even when you do pre-filled decode, it's much more complicated than that, right? Because you can do pre-filled decode, you can also start thinking about disaggregating decode itself into spec decode, which is actually the easy one. You can also disaggregate decode into attention and MOE. which is much more complex. It requires like a lot of fine-grained work between two different pieces of hardware. So one of the things we do is work on generating a lot of like automated kernels in the middle to make it faster to overlap the compute and communication, because it's pretty intractable to do it all by hand.
Okay, thank you. Let's find out the speaker round. So this is the last round before the break. We have run it from 12 to 1:50. So we talk about what are memories of system and inconsistency overall infra level inconsistency and scale. This talk is somewhat in this level it's actually very interesting. This is more into the security aspects and encryption. So it's not something I have full grasp, so that's why we have Rangan here. It's my pleasure to introduce Raegan, who is going to talk about his research on private neural recognition with homomorphic encryption and Orion framework.
Great, thank you.
Raegan is an assistant professor of electrical and computer engineering at NYU, and his focus is on computer architecture. He leads a group of PhD students whose current focus is to make cryptographic computing practical through algorithmic compiler and hardware optimization. Prior to cryptographic computing, he made significant contribution to accelerator and hardware and machine learning. The work has been recognized at ASPLOS 25 as paper and multiple other nominations. He also worked at Fairlab at Meta. So thank you. I'm my pleasure again.
Great, thank you. Is this microphone's working? All right, very good. So we're going to shift gears pretty hard here and talk about privacy and cryptography. So how many people know how homomorphic encryption actually works? Amazing, two and a half. Okay, good. So even if you don't know, this whole talk is intentionally made for systems people, so anyone should be able to understand it. And specifically what we're going to talk about is three of our works. Orion, which is a new framework to make FHE accessible to anyone who can write Python or PyTorch. Einhops, which extends operation coverage to include einsum. So if you've ever used einsum before, we now support that in homomorphic encryption. And finally, I'll show our most recent work, which is how we've actually been able to map DLRMs or neural recommendations into homomorphic encryption. So let's keep going. So pretty typical setup here, right? Client in the cloud. How do we do things today? Well, the client has some data. We encrypt it. We send it over the wire, totally protected, secured under encryption. Then when it gets to the cloud, we decrypt it for computation. This works pretty well, but the cloud still gets to see your data. Homomorphic encryption is just an extension of the standard technique where your encrypted data stays encrypted through the entire time it's off your chip. So now all the computations that are happening in the cloud incur directly on encrypted data. You get very strong security and privacy guarantees. Moreover, if you do it correctly, you still get the exact same result that only you can decrypt. Diagonals that you have, problem size, and runtime normalized on the x-axis to just doing the diagonal method. So there's actually two forms of hoisting, single hoisting and double hoisting. We always do double hoisting with BSGS. And you can see that for something like a typical number of diagonals in a CNN or a problem size, we can get roughly a 10x reduction in computation or runtime using BSGS and double hoist rotation. So this is a very nice thing to have. This is one of the most powerful tools we have in CKKS. And this is going to be our hammer in Orion. So we're going to use this. This is what we're trying to map all work to. And we're going to very carefully set everything up to use it. So let's see how we can. So obviously, if we have vector matrix, we can do fully connected or MLP layers. The next thing we want to do is support convolutions. How we do this is with a Toeplitz representation. If you haven't seen this before, if you think about having an input and striding a filter over it, each stride of that filter over the input corresponds to one row of the matrix. So each of these rows here is just one pass of a filter over the image. That allows us to map a convolution very effectively into a matrix. Once we have a matrix, we can take our diagonals, do BSGS. We are very happy. This is a very trivial convolution, right? This is not what convolutions look like today. They actually typically have multiple input multiple output channels. The nice thing about a topless representation is that if you have multiple input channels, you can just extend that horizontally. You continue to use the diagonal method. In the matrix here, you can see the yellow color. And if you have multiple output channels, that just corresponds to unique output. We call them neurons or nodes. We can just expend the vertical dimension. So even with MIMO, we still have a matrix representation. We can still process it with BSGS. Life is good. Things get a little tricky when we start to consider strides. Strides aren't a regular computation. They're still very structured, but any gaps in computation can potentially cause a lot of issues with FHE because they can result in gaps in the ciphertext and poor slot utilization. So there's a couple things to note here. First, when we use the topless representation in Orion, we can handle strides with no problem, right? We just zero out the computations that we miss in the stride. We still use the topless representation. Life is very good. And our output, we can see, is very compact, right? All of our data is perfectly aligned. There's no gaps in our ciphertext. We don't have to patch anything up. We're still doing a MIMO convolution by only consuming a single level. This was actually a pretty significant improvement over much of the prior work, which actually had to consume 2 levels for strided convolutions. But if we look a little deeper, maybe we could do better, right? We have all these zeros in our diagonals. That's poor slot utilization. That's wasted work. And this work is super, super expensive in homomorphic encryption. We really don't want to waste computation by having 0 slots. So one of the observations that we made is that when you have weight matrices that look like this, you can see the row indexes being called out here, you can actually permute them. You can permute the rows and still get the exact same output. You just have to carefully keep track of when you flipped your rows, how that correspondingly flips your output matrix. So over here, if you watch, we can rotate the rows to try to smush all the non-zeros towards the main diagonal. That's going to give us much more dense diagonals that we process, and we're going to have a bunch of 0 diagonals, which we just don't have to compute. This is great. It saves us quite a bit. You can see we still have a dense output ciphertext for downstream tasks. You do have to manage a lot more indexing because this is not in the most convenient format, but Orion does it all automatically for you, so you don't have to worry too much about that. So now if you look at the main diagonal we had before, we are much more dense now, we're much more efficient, we can be much more performant. This turns out to work really well if we just consider packing compared to the state of the art. If you just look at the rotations, which we were really trying to optimize for, those are super expensive. On something like AlexNet, we were over 6x fewer than really competitive state-of-the-art work, stuff like Felipe and Da Capo published in top venues. So now that we know how to pack and represent our data in ciphertext, let's look at this bootstrap placement problem. And this gets a little tricky. You might think, well, okay, I have to bootstrap when I run out of levels, right? So when do I bootstrap? When I'm out of levels. That's called lazy bootstrap placement, and it's been shown repeatedly to be non-optimal. So we'd like to do better. And the reason we have to place bootstrap, some people don't use it, but if you want to do deep computations, there's no way around it. So your framework should support it. And if you do manual placement, it's just really a tedious task. And there's a lot of suboptimal solutions that we should seek to avoid. So let's understand how we solved this problem in Orion. And really everything's about the problem setup. So I'm going to spend a lot of time explaining that. And let's begin with a really simple neural network where you just have an input and you want to run a couple fully connected layers. One of our key contributions here was by introducing what we called a level DAG. So what you do is enumerate all possible network states of the neural network. So if I have input FC1, FC2, FC3, I take each of those layers and I have a node for each possible level that each of those computations could run at. So if I look at something like FC2, I could run that matrix vector product at level 1, level 2, or level 3. And I just have nodes reflecting each of those choices. Then what we do is we actually profile running each of those operators at each of those levels. And what happens is that running an operator when you have more levels takes more time. So if I want to run FC2 at level 3 versus level 2, this one will take longer. So we just profile and weight the nodes by the runtime that we found. The last thing that we do is when we have edges connecting nodes between layers, we weight them by whether or not you have to run a bootstrap. So remember that the only time I would ever bootstrap is when I want to increase the number of levels that I have. That represents going from one layer down to the next one, moving to the right by increasing the number of levels we have. Those are shown in red here. So that we weight by the bootstrapping time. If you go down levels, it doesn't matter. So that's effectively free. Now we have a directed weighted graph. How can we solve this? We just call shortest path. If we call shortest path through this, not only does it solve all level management for each node, we know where to place bootstraps. It's where you go to the right, wherever you increase your number of levels. Now, that was a very simple example. You might think, why are you doing all this? That was trivial. It gets a little more complicated when you have things like residual connections, skip connections, or anything that's just not top down. And that's because all computations have to occur at the same level. So if I have something with a lot of levels and something with a few levels, and I mismatched it, managed it poorly, then I either have to call bootstrapping on this one, or I have to throw away a bunch of levels on something that I had a lot more left in, and it's just wasteful. The way that we solve this problem is by isolating first these skip connections and breaking it into two graphs, a backbone graph and a residual graph. Then we do shortest path for each input-output node pair in both of them. So 1 to output node here, 2, 3, 1 to 2, and we create this aggregate representation of the skip connection that sums the weight of each shortest path. Then we have this nice simplified subgraph. We plug it back into our main graph, and then we can just call shortest path on it. So this turns out to work really well. If we compare against many of the state-of-the-art works here, we're either much, much faster than them, or there was actually a really good paper published, I think it was at Usenix or CCS, that only focused on bootstrap placement. We were able to find the same solution as them, but we were over 1,000 times faster in finding it. So this is pretty effective. And then lastly, there's just a lot of things that you have to take care of when you want to map a workload into homomorphic encryption. So because we only have, for example, addition and multiplication, you can't do things like ReLU. You have to approximate it with a polynomial. It might sound pretty easy or not that hard, but it's actually really, really hard, especially when you have deep networks. So Orion does this all for you. It automatically fits polynomials to your activation functions. It can even do some fine-grained training if you need it. Another pretty nasty issue is that the way that you get fixed point, or they call it floating point, but it's really closer to fixed point, is that you have to introduce some rounding and approximation in your computation. And if you have a shallow computational circuit, that's not a problem. You just get a little bit of error and you just deal with it. You still get the right answer. But if you have a really deep circuit, that error can really compound, and it turns out that you can't run deep computations because you won't get the right answer. So we came up with a way to do what we call errorless scale management, and that's what allows us to do super deep computations. We also have huge data structures, and we handle all going back and forth the disk before you. We ran these on machines with 1 terabyte of memory, and we still ran out of memory. So you have to go to disk. There's no way around it. Okay, that was a lot. And if absolutely none of that made sense, it actually doesn't matter. Because if you want to write fully homomorphic encryption now with Orion, this is what it looks like. Some of you in the back might not be able to see it. I'm sure you would think this is just Python or PyTorch. That was the idea. This is VGG, family of VGG networks in Orion. This is all it takes to run it. You can pip install Orion right now. And if you go to our repo, you can just clone the examples and run it. We run it on a bunch of things. It's not only super easy to use, it also beats the state-of-the-art, best-in-class performance for what it does. Ton of results. And these are the two things I'm most proud of, is that it really pushed what we could do with homomorphic encryption. So if you look at this dot here, this reflects the number of flops in the benchmark that everyone was using to publish homomorphic encryption papers. The workload that we demonstrated in our ASPLOS paper, this is to scale how many flops we did. So we were the first to run YOLO v1 in the Pascal VOC dataset at 39, almost 140 million parameters, largest correct computation at the time ever run under homomorphic encryption. So we were proud of it, still a lot of work to be done. This took 17.5 hours. Thanks to Google, we were able to get a super powerful GCP server, the most powerful one they would let us use, and we're working on that now. The other thing that I'm extremely proud of in this work is when I started doing this in 2019, 2020, we said we were going to work on homomorphic encryption. We literally got laughed at because people were like, that thing is so ridiculous. It's never going to work. Go back to academia. It's just, why aren't you doing accelerators for AI, basically? I made a huge mistake. Yeah, maybe I did, but this is more fun. Last year, we run a K-12 AI summer program every year at NYU. We get 75 to 100 high school kids, true high school kids, like freshmen and sophomores, things like that. We taught them the basics of homomorphic encryption. We gave them access to Orion. This is an actual picture of Austin teaching it in the class. We had high school kids running FHE on their laptops and actually using it. So this technology is actually coming to light. We're seeing high school, it's so easy to use, a high school kid can do it. This is what we're really excited about, is getting a real user base in FHE. Then we're going to be able to really, really address those performance overheads. Okay, 2 more pieces of work. So you might say, what are you talking about? It's 2026 and you're talking about convolutions, right? Well, convolutions are really the stress test for homomorphic encryption up till about now. Obviously, we don't just want to process convolutions. What do we want to do? We want matrix, matrix multiplies, transposes, and attentions. People are obviously looking at that, and there's been great work, right? One of the challenges is that this thing is still kind of hard to use. So every time you support a new operator or have some new optimization, that's a paper, right? You publish a great paper on that. And so the challenge is that if we want to support a lot of operators, every single one is 6 months to 12 months of graduate student effort. This doesn't scale. What we'd really like is a more general approach to support a ton of operators all in one language. And that's what we do in we call it einhops, our einhop work. And what we're doing here is actually supporting einsum notation. So what you can do, folks have probably seen einsum in PyTorch before, perhaps. You just specify the tensor dimensions of your inputs and your outputs, and it'll automatically figure out the computation that you want to do. I'm going to go through this one a little quickly so we have time to talk about recommendation. And I assume folks have seen einsum before. If you can do this and you get this language, then you can support lots of different tensor computations. You can do matrix, matrix multiply, of course, matrix vector. You can do summations or reductions. You can do transposed, chained or batched matrix, matrix multiplies. Really powerful stuff. And so what my student did very cleverly is extended the align and broadcast rules from einsum to CKKS fully homomorphic encryption. So he does the align directly in the 1D ciphertext. He handles all the broadcasting, so you get the exact same tensor dimensions. And then once you have this, you're home, right? Because you already have SIMD natively supported in FHE. You do your SIMD operations, you get your partial matrix, and then you just sum and reduce to get your final output. So this is very nice. We show that we can do a ton of different computations with einhops. It's publicly available. It's supported in Orion, so you can go and test it out for yourself. So the last thing, I have a couple minutes left. I'd like to talk about this quickly, is our DLRM work, right? So what we also wanted to do is try to support ads. We thought supporting neural recommendation under confidential computing would be something folks would like to see. And ads was also nice because it poses a different challenge, right? You have both your dense features. We know how to do that. Everyone knows how to do that. But these embedding tables are the ones that are actually quite interesting. So they're sparse. You have to do an index lookup into a table, and they're huge, right? So Criteo, which is one of the industry scale models publicly available to us, has 26 embedding tables and about 30 million rows to look up. So now our client has sparse data. It's basically going to send an index to the server, and all we're trying to do is compute this embedding of I, a table lookup of a single index. This is trivial in the clear text and plain text. I would just take my pointer, look it up in the table, and get my data, right? This is not that interesting to talk about. But in FHE, this is a nightmare because you can't do it. You have to have data oblivious computation. What you have to do is convert this into a matrix vector product. So now my embedding table is transposed. I one-hot encode my index, and I have to do a matrix vector computation to get my embeddings out. So you might say, well, that doesn't look so bad. You just convert everything to a matrix vector product. But if you naively do that, remember, this thing had 30 million rows. If you think about one-hot encoding, each of those ones that you have to multiply the table by, you get 1,000 ciphertext. That's about 5 gigabytes of data just to encode embeddings. Moreover, remember, that's one hot encoding. That's only 26 unique IDs in 5 gigabytes worth of data. It's not going to work. You could try to send them over. Also not going to work. 5G is too slow. And it's a lot of data to process. So I'll give you the takeaway. What we want to do is compress the embedding tables. Go to something that is represented as P to the L down to L unique tables of each size P. So this is compressed embedding. So we go from P to the L to P times L rows. It makes everything much simpler, but now we have to have a mapping. So we have to map our original index into the mappings of each of these factored tables. So what prior work did is they actually built that into the learning phase. So they learned the mapping from the original embedding into the compressed or factored embeddings. There's a bunch of problems with this. First, now the client has to store those embedding tables. And they're quite large. So you don't really want to put that burden on them. Second, because those are learned, every time you update your model, you have to re-download those embeddings, which perhaps you don't want to do. Next, those don't actually give you the one-hot vectors. You can just send, oh, I'm looking for 2 in this sub-matrix, or 3. Then you have to apply a mask. You can see this is an index mask. You do a subtraction. That will actually give you a hint at where the 1 was. It'll flatten it to 0. Then you have to run this indicator function on that to convert a one-hot vector. But this is the indicator function. You can see this is 2 to the r. This consumes so many levels that just converting a 0 to a 1 requires a bootstrap. So it's incredibly slow. Instead, what we do is we propose a static mapping from the original embedding into the compressed embedding. This is just digit decomposition. It's how we represent numbers. So just take your embedding, you divide it by 4, because P is 4, raised to the table you're looking at, mod 4. Now the client can compute this. There's nothing to store, trivial computation. That mapping doesn't change, but you can still learn the compressed representation, so you can still update the model without having to update the client. Moreover, you can now directly send this one-hot vector to the server, so they don't have to worry about it. They don't have to run the indicator function. You can do an entire embedding, only consuming 1 level. You don't need bootstrapping. I'm running a little low on time here, so I'll skip how we pack everything really nicely. Spoiler, we represent everything as a matrix, so we can use BSGS. This turns out to work exceptionally well. So this was the prior state of the art, is this blue bar here. Our solution, we call it HELRM. It's on archive, you can check it out, is the green bar here. Doesn't quite show up, but we're getting up to 77x, between 1 and 2 orders of magnitude improvement on end-to-end neural recommendation. Moreover, we did actually run this end-to-end. We got the right answer. We're actually talking to a couple startups to try to see if they can run this thing for real. And yeah, we can run neural recommendations through Orion, and you can too, because everything is open source. Finally, I'll leave you with this. Everything we do is open source. Orion's open source. Einhops is open source. HELRM is open source. Go check it out. Chat with us if you want to work together. We'd love to. These are my 2 students. They're fantastic. They're both here somewhere. Austin and Karthik, they did a lot of the heavy lifting, so I wanted to recognize them. Thank you.
Thank you. We have time for maybe 1 question or 2. I have a question.
Sure.
So, when you implement this, in terms of performance or energy efficiency, what do you see compared to what the state of art is? Is it what order of, because large embedding table can be quite costly in terms of energy efficiency. So, with your technique,
Okay.
what level of improvement do you see?
You're asking specifically about energy efficiency? Yeah, so this is a massive failing on my part, and I think the FHE community's part in general. So if you look at the numbers that we're talking about running a single YOLO inference in 17 hours, right? People are hyper-focused on just getting that performance down as much as possible. I mean, people put like a power number in their paper, but nobody's reporting energy efficiency. Right now, we're all hyper-focused on performance. So the energy efficiency of these things is terrible. Like basically the slowdown, you just multiply the energy overhead of that by that factor, and that's probably what you're looking at. I think there's a lot of opportunity to look at energy efficiency, but unfortunately we've just been so focused on either trying to get computations to work, like we don't know how to do them in homomorphic encryption, or trying to address that 17-hour runtime that we haven't gotten there. The good news is that everything, we wanted to run it for real. We have other work on accelerators that I didn't talk about. There's tons of work on hardware accelerators. There's great work on GPUs too. So people are showing really good results on GPUs. Hopefully that improves some energy efficiency. And the accelerators are doing very, very well. So if we ever do get to accelerators.
That was my follow-up question.
Okay.
So in GPU, do you see any specific family of accelerator where this could be the Asgar as well as the Gimlet?
Yeah, so there's a big there's an interesting debate going on within the hardware accelerator for homomorphic encryption community. So some people say that vector architectures is the best because we have vector paper on this too. So we do love our vector architectures. You look at it and that makes sense. The fundamental data structure in homomorphic encryption is a vector. So you build a vector architecture. So folks have done that. Some folks have more of a clustered style approach. They've shown very good results in that. We argue that at the end of the day, what you want to build for your accelerator is a systolic array. So what we have shown is that it's not obvious that you can map this to a systolic array. You have to make some concessions. But what that does is it simplifies everything about the hardware. You basically need to make 4 little modules, and then you just stamp them out. And then you have a systolic array. The entire chip runs in lockstep data flow. You can perfectly balance your compute communication overhead. Turns out to work great with BSGS. But I think the jury's still out. Is it a systolic array? Is it a vector? Or is it sort of like a tiled distributed style compute? So
one quick follow-up on that, kind of going in the co-design space, not looking at architectures alone, but can we build a different library of fundamental operators in the that are more suitable for machine?
Yes, that is what the crypto community is working on right now. So this is specifically, I talked about CKKS. CKKS came out in like 2016. Amazing paper because it fundamentally supported fixed point. Before that, you only had integers. Everything overflew. It was a nightmare. So people like CKKS, we still use it. There's another one called TFHE that supports unary projection. So you basically get a lookup table. Also very nice, but it has its own drawbacks. One of the major things that's going on now, I think the Gentry just gave his talk in Cross, been going around and giving it, natively support matrices. So rather than supporting vectors, you support a matrix. So fundamentally different data structure, and that's what we're looking at now. So the crypto folks are on that, and yeah, as much as we can co-design that with the application, everyone's talking about LLMs here, you need matrix multiplication, that makes a lot of sense. So that's definitely where we see things going, for sure. Great question, thank you.
Let's thank our speaker. With that, we come to the end of the morning session. We will regroup at 1:15, not 1:30, 1:15. So see you all here at 1:15. क्या चीज इसकी बैग रख दो put this on charging as well.
I have actually another microphone.
We have a break.
So this is okay. This is on blue, so it should be fine. Oh, this also.
Yeah, it could be risky.
left my laptop and I went out. Came back.
Oh, you're taking your bag anyways, right? I would say
No bag may not be taken. I'll take my earphones.
Okay.
Just if you want to leave it here.
I think it's okay. Yeah, if it's hooked up, it's fine. We just.
There is one speaker. We'll have to use the video.
how you connect the USB-C? What do you need to do?
Connect the laptop.
Oh. And when you're ready, just turn it on. One of these papers, this guy is not presenting, but he sent a video. I'm not able to open that video here. It's on OneDrive. What do we do? Yeah, I think it's the Wi-Fi here which is blocking.
Can you download it using this mobile?
Sure. Can you try? I sent you the link.
Did you email it?
I did. I can send it to you again.
No, I can.
See, look for camera ready.
Dematrix?
Yeah, Gmail.
Oh,
Shall I send it to your Gmail?
no.
Hi, I'm Urmish.
Hey, Urmish.
Do I need to test out my laptop for connections and things like that?
So far, we haven't had any technical
Okay.
issues.
So all the
If you
plugins will
have
be
a
available.
backup on a USB drive, that will be good.
I don't have a backup USB. I can email to you folks if that's.
Yeah.
Yeah, I'm Neil, by the way.
Oh, Urmish.
Nice to meet you.
Satyam.
I just joined Microsoft. Yeah, I joined their super into this lab. It's just been a couple of weeks. And a lot of this work was. I know. Yeah, right. A lot of this work is company that I advise and also some other systems. So I know to add. Okay. Sometimes when you add Microsoft affiliation to all these companies that you advise to add. Yeah, yeah.
He got into trouble just taking a question about the EMC2 workshop from the reporter when he was at Microsoft.
Oh, really? Yeah, that's it.
I don't see your email.
No?
What was it? I sent to you for camera ready solution. Can you show me the advice and some of the work from there? And I didn't really want to combine things. It's just been 2 weeks for me.
Microsoft weekend is too sad not to easily. Don't
This
they
one.
have 10
Oh,
things
so
like
Friday,
whatever pool of
Yeah.
or if they're working on similar technology?
Yeah, I think this is a different computer version of the website. But I also have all the super intelligence like that. Yes. So they're a little bit more next.
You're better off now.
By downloading this video on your phone. The Wi-Fi here is blocking it.
So how do I do something? You have to turn off your video.
Satyam, I'm able to.
We are able to?
Looks like it.
Oh, okay, good.
I turned on my this thing. Hotspot.
So why don't we do this? Which paper is this?
So is the video we are going to play? It's not like in-person one?
Not able to make.
Where is this?
Go up here.
Where is it?
What?
SMOE. Is it not Nodal Talk? What is messed up here? These are not the papers. We had 8 papers. 2 of them were supposed to be poster only.
Yeah.
And I think this one was poster only.
Yeah.
Where is SMOE?
Okay, where is the original list? Let's go to that. Anyway, let's give 10 minutes each. Just whatever that. Here. What is the status?
So, this is one of the first top 6 papers.
Okay.
So I think Sushant screwed up somewhere.
Yeah. So, but you know which one to replace.
Okay, so yours is the only one. We can replace yours.
Yeah, that's fine.
Or if you want to cut it down to 10 minutes.
I can do 10 minutes. 10 minutes actually more than it. I don't
Because that's unfair. This is one of the better papers.
So he is actually. Why don't we actually put in the first session? We start with
let's start with that.
Yeah. And then
So you have the video playing, right?
Yeah.
So once you finish your talk,
yeah.
we'll go straight to this one.
Yeah.
And then go through the next.
What about there is another one which is missing?
Yeah, the number 2 and 18, these were poster only.
Okay, then it's fine.
We need to check how the audio works.
I'll take 10 minutes. That's more than enough.
I think we have time.
Okay.
Share setup, I think.
Oh, so I
Hey folks, we'll be starting the afternoon session in another minute. The paper authors, if you're here, please come to the front and just make sure that you have everything that you need, because we'll be going straight to the paper sessions after the sponsor talk.
I think I'm the first presenter. Yeah.
We'll just play a video for that.
Oh no, that is this laptop, right? This is.
And maybe
where is the audio jack? This here. This would be okay, no?
yeah, this is
Oh,
we have
you say you're
okay.
saying attach this over here?
Yeah.
We can test. You want to test it out?
Test out. Hey. Why the audio is not working?
Audio is not working. Oh,
might be zeroed out.
Wait. Why we remove this and then just let's play?
With very tight memory margins. This is Zheng to work with Wang Guanguo from Tsinghua University. So let's start with some context.
No, this is the max
Large
version.
language models are
No,
everywhere
I've
now,
disconnected the
and people increasingly want to
because that's
run
not
them
working.
locally
Okay, let's.
on laptops or workstations, rather than
No, I think this is a different. What is this one?
No, that is power, right? This other one. The
Oh,
audio
that's
jack is
power.
this. Why don't we actually play this?
the reason is the ASPLOS.
This.
Take tunes 330B H3B as an example. It has 30 million parameters in total, but for any given token, it only activates about 3 million.
Speaker.
And is competitive with DeepSeek V3 on several benchmarks. So you get strong model quality with a fraction of the compute.
Okay, that was more.
Oh, so that's what you'll have to do.
Okay, improvise.
Start in one.
But we can connect with you.
Is the screen live? It is?
Yeah.
YouTube is live.
Just check. It is, but
All right, welcome everyone. We are going to start the afternoon session. And to begin this session, we have a representative from our sponsors, G-Matrix. The company has been generous in sponsoring the workshop over the last 5 or 6 years. And this time we have Neil who talk about the company and what they do.
thanks, Satyam. Today I'll be talking about empowering AI innovation with D-Matrix Corsair and what we have coming up next. So the fundamental crisis in Gen AI isn't a lack of compute. It is the imbalance between arithmetic intensity and memory bandwidth. In a standard transformer inference cycle, the workload is overwhelmingly memory bandwidth bound. As we generate tokens, we aren't just performing math, we are constantly reading and writing into the KV cache. For every new token, the processor must fetch the entire history of the key value pairs from the off-chip HBM just to calculate the next step. Even with the HBM in today's leading GPUs, we are hitting a physical wall. The energy cost of data movement is roughly 2 orders of magnitude higher than the energy required for the 8-bit or 16-bit Mac operations. The result is a stalled processor. We have teraflops of compute sitting idle because the memory subsystem cannot feed the execution units fast enough to maintain human speed interactivity. As context windows expand and parameter counts climb, this overhead becomes unsustainable. To break the memory wall, we cannot simply iterate on bus widths. We have to collapse the distance between data and logic. So how does D-Matrix break the memory wall? We don't just try to build a wider bridge to memory. We collapse the distance entirely. Our core innovation is digital in-memory compute, or DIMC as we call it. Instead of the traditional von Neumann setup, where the compute unit and the memory are discrete blocks, we have redesigned the memory bit cell itself. We create a custom SRAM cell that can store a bit and perform multiplication. So here's a picture of our Corsair PCI card. So we have 8 chiplets on there, built with TSMC 6 nanometer technology. The performance it gives is 2400 teraflops on MX int 8. Not sure how to use this. Right, so we get a performance of 2400 teraflops on MX int 8 and 9600 teraflops on MX int 4. This has a PCI Gen 5 connectivity with 128 Gbps bandwidth, and a total, the TDP is 600 watts. The on-chip SRAM gives a total bandwidth of 150 terabytes per second, and each card has 2 gigabytes of memory. And in addition to the SRAM memory, we also have 256 gigabytes of slower DRAM memory, the LPDDR5, which operates at 400 gigabytes per second. So if we look closer into each chiplet, or this is a picture of each card which shows 8 chiplets on there. So in total we have 2048 DIMC cores, which are SRAM cells, which are the custom SRAM cells. The total storage capacity is 2 gigabytes. They enable memory compression and block floating point formats. We have a die-to-die link, which provides a bandwidth of 8 terabytes per second. As I already mentioned, there's an off-chip LPDDR5 with 256 gigabytes of memory. We have a DMX bridge across 2 cards, which gives a bandwidth of 512 gigabytes per second. And it's a PCI-based architecture. So one of the big use cases of this is it's a plug-and-play type architecture where you can use your existing server, fit in the PCI card, and you don't need to design a full rack or a full custom server for Corsair. So here's a picture of a Supermicro X14 server with 8 Corsair cards. So we didn't just stop at building cards, Corsair cards. We are looking at scaling as well. So we built out a Jetstream accelerator, which allows us to scale from a single server to an entire data center rack. So Jetstream is a custom PCI Gen 5 accelerator, a transparent NIC, designed to let Corsair cards talk to each other directly across servers using standard Ethernet. So it's 400 gigabytes, 400 Gbps, industry standard 802.3 Ethernet. It has a sub 2 microsecond accelerator to accelerator latency and 150 watt TDP. It also supports squad rack configurations, which enable 100 billion plus parameter models to run entirely in performance memory, which is the SRAM, across a cluster. So here's a picture of our scale-up solution. So we have 2 CPUs within a node, and using our PCI solution, we can have 8 more than, you can have multiple Corsair cards connected to each other. So moving forward, we look forward at what's coming next. While the current solution of SRAM and LPDDR5 provides massive bandwidth, we are still limited by capacity. So our future, for the future, in a future roadmap, we are going vertical. We call it the 3DIMC solution, or 3D stacked digital in-memory compute. We have already validated this 3D stacking, where we have a DRAM die, we have a logic die which is on top of a DRAM die, and we have validated it with actual real silicon with our Pavehawk test chip. The 3D stacking allows us to target 10 times better memory bandwidth and 10 times better energy efficiency using 3D IMC over HBM4 configurations. Apart from all the amazing hardware we are building, we have our own Aviator software stack. So this picture gives a whole overview of our software stack. So Aviator is a software environment built to work directly with the tools you already use, such as PyTorch and Triton. The workflow is straightforward. You start with the model factory, which provides pre-optimized templates for major LLMs. You don't have to manually partition your model across our distributed chiplets. The software handles the mapping of weights into our SRAM arrays automatically. To maintain high accuracy at low power, Aviator includes the compressor toolkit. This natively supports the OCP standard MX formats like MXint8 and MXint4. It allows you to shrink your model size while the hardware maintains full floating point precision where it matters most. Finally, the distributed inference engine makes a cluster of Corsair cards look like a single massive logical device. Whether you're running a 7 billion model on one card or a 400 billion model across a rack via Jetstream, the API remains the same. So if you're interested in building with us, in partnering with us, we are always looking out for talented people who are ready to tackle new problems with new solutions, with innovative solutions, thinking out of the box. So if you have some ideas in mind, feel free to approach me, talk to me, or my colleague Satyam, who's also the co-chair here. And that's it. Thank you very much.
Any questions? If not, we'll be around. If you have any questions about the company or you are interested in working with us, catch hold of us. And again, there is some merchandise kept on the table on the left. If you want to grab something, please do. With that, we'll start with the paper session. And the first paper is SMOE, a 3-tier storage inference framework for MOE models under edge memory constraints. Unfortunately, the speakers are not here, but they sent a pre-recorded video which will play on the behalf.
We just bring that up. Should I play?
This is not connected. Or can you start on this laptop?
Yeah, that didn't work.
No, okay.
Okay, I'll change that.
Yeah. Let's just directly connect to HDMI. No, you have
No,
built in.
Very tight memory margins. This is true to work with one.
Increase the volume.
Hi everyone, I'm Laura from University. Unfortunately, I wasn't able to attend in person, so I apologize for not being there with you today. I'll be presenting our work, SMOE, a three-tier storage inference framework that lets you run a mixture of expert models on edge devices with very tight memory budgets. This is joint work with Wang Guanbo from Tsinghua University. So let's start with some context. Large language models are everywhere now, and people increasingly want to run them locally on laptops or workstations. Rather than relying on cloud APIs, there are many reasons for this: privacy, latency, cost, and so on. Now, MOE models are particularly interesting for edge deployment. The reason is simple: they are sparse. Take Qianwen 30B A3B as an example. It has 30 billion parameters in total, but for any given token, it only activates about 3 billion. And is competitive with DeepSeek V3 on several benchmarks. So you get strong model quality with a fraction of the compute. Sound like a great fit for edge, right? Well, the compute is sparse, but the storage is not. You still need to store all 30 billion parameters somewhere, and that's where things get tricky. Existing approaches like K-transformers and hybrid MOE are doing something clever. They offload MOE expert ways to CPU memory and run expert computation on the CPU. At the same time, they keep attention layers on the GPU. This does solve the VRAM problem, but what it actually does is just move the memory pressure from VRAM to DRAM. Look at these numbers. For Qianwen 330B, K-transformers need over 20 gigs of DRAM. Llama MOE mode needs 17. And for Qianwen 3235B, over 90 gigabytes are needed. A typical edge device has 16 gigs of DRAM and maybe 8 to 12 gigs of VRAM. None of these methods fit. So the core question is, can we actually bring DRAM usage down to single-digit gigabytes? Our insight comes from looking at this access pattern more carefully. In a model like Qianwen 330B, each MOE layer has 128 experts, but only 8 get activated per token. That means at any point in time, you only need a tiny fraction of the expert base in memory. The rest are just sitting there. Meanwhile, NVMe SSDs have gotten very fast, and they come in terabyte capacities. So the idea is, why keep all these expert weights in DRAM when we can store them on SSD and load just the ones we need? This is the foundation of SMOE, extending the two-tier VRAM DRAM structure into a three-tier VRAM DRAM SSD architecture. Let me walk you through the design. We split model weights into two categories based on their access pattern. Hot weights like self-attention layers and shared MOE and shared experts stay permanently in VRAM, and the GPU handles their computation. Nothing changes here. Hot weights like the rotated experts are the ones that are sparsely activated. These live on SSD when we reach an MOE layer during the inference. The gating network tells us which experts are needed. We load those specific experts from SSD into DRAM, run the computation on CPU, and then immediately release that memory. The beauty of this design is that your VRAM footprint is determined only by the attention layers and the shared experts. And your DRAM footprint is determined only by the handful of experts that are currently active. For Qianwen 330B with Q4 computation, that works out to about 5 gigs of VRAM and roughly 4 gigs of DRAM, both well within edge budget. Now, the obvious concern is that loading experts from SSD as every MOE layer will be painfully slow. This is absolutely true if we do it naively. Waiting for the SSD every single time creates a massive bottleneck. The load time often takes longer than the actual computation, which means the GPU would just store at every layer. To fix this, we need to overlap the SSD reads with computation. And to make that happen, we need to know actually which experts the next layer will need ahead of time. This leads us to our prefetching mechanism. Here is our key observation. Thanks to residual connections, adjacent layers in transformers share very similar inputs. Layer I and layer I+1 look almost the same. So we can just take the current layer's input and pass it through the next layer's gating network. This gating step is just a simple, cheap linear projection. Doing this gives us a quick prediction of which experts the next layer will activate. Let's look at the accuracy in this figure. Predicting the top 8 experts gives us an 81% hit rate. If we bump that to top 12, it jumps to 92%. Going any higher does not have much and just locks up the I/O bandwidth. Therefore, top 12 is our sweet spot. I want to emphasize that this prediction is completely safe. It does not change the model's math at all. If our prediction misses an expert, we just pause and load it before doing the math. In the end, the output is bit for bit identical to running without any prefetching. So once we have the predicted expert list, we kick off asynchronous SSD to DRAM loads through a dedicated thread pool. This runs in parallel with the current layer's expert computation on CPU and the attention of computation on GPU. At the time we reach the next memory layer, the predicted experts are hopefully already sitting in DRAM, ready to go. On top of this, we capture the entire single-step decode forward path as a CUDA graph. Now the tricky part is that CUDA graph cannot natively capture a whole set of operations like our CPU experts computation and prefetch scheduling. We solve this by embedding this as host function through the CUDA launch host func API. This way, the whole decode step, GPU kernels, CPU computations, prefetch scheduling runs from a single graph replay, cutting out all the per layer kernels launch and synchronization overhead. And the impact is significant. In our ablation, the graph alone gives a 2.15 times speed up. That's a lot of overhead that was hiding in the launch and the scheduling path. All right, let's look at these numbers. On Tianwen 330B with Q4 computation, SMOE achieves 19.49 tokens per second using 4.83 gigs of VRAM and just 3.9 gigs of DRAM. Compare that to key transformers, which needs 20.3 gigs of DRAM, or LAMMA mode at 17 gigs. That's roughly an 80% reduction in DRAM. And 19.49 tokens per second is perfectly usable for interactive conversations on a local device. That's still faster than most people read. But the more existing result, in my opinion, is Tianwen 3235B. This is a 235 billion parameter model. With Q3 quantization, every existing method needs over 90 gigabytes of DRAM. That's simply not happening on every edge device. SMOE brings that down to 10.9 of VRAM and 6.9 gigs of DRAM. For the first time, you can actually fit this model within a 12 GB VRAM, 16 GB DRAM budget. Yes, the throughput is 3 tokens per second, which is on a slower side. But consider what we are doing here, running a 235 billion parameter model on hardware that costs a fraction of a data center GPU. For offline tasks, summarizations, batch processing, That's absolutely useful. Although Llama MOE is 3 times faster on the 30V model, it also uses 4 times in DRAM. So we introduced a metric we call throughput per gigabytes of DRAM, which captures how efficiently you are using your memory budget. And here the picture is very different. SMOE has 5 tokens per second per gigabyte on TL330V, significantly higher than transformers at 2.2 or Llama MOE at 3.6. On the 235V model, the gap is even better, 0.4 versus 0.1 for key transformers. The takeaway is clear. When memory is the bottleneck, which is on edge devices, SMOE makes much better use of the memory you have. Let me quickly walk through the evaluation to show where the gains come from. Config A is our upper bound. All experts in DRAM, no SSD involvement. That gives 38 tokens per second, but need 18 gigs of DRAM. Not feasible for edge. Config B enables SSD offloading, but with no prefetching. Pure synchronous loading. DRAM drops to 3.7 gigs, which is great, but throughput falls to 16.7 tokens per second. That's a 57% hit from the I/O stores. Config C, our full method, as predictive prefetching on top of B. Throughput recovers to 19.49 tokens per second, and a 17% improvement, with only 0.2 gigs of additionally DRAM for the prefetch buffer. And the plot graph on top gives the 2.15 times speed up I mentioned earlier. So every component pulls its weight. SSD offloading value the memory savings. Prefetching recovers a meaningful chunk of the I/O penalty, and the plot graph handles the system level overhead. This is a working process. The prefill phase hasn't been optimized yet. We focused on decode because that dominates users' perceived latency in interactive settings. Our experiments run on server-grade hardware, not actual consumer devices, though we verified that peak resources usage stay within edge budget. And the current system uses static configurations. We don't yet adapt to runtime memory pressure or background applications. These are all active direction for our future work. To sum up, SMOE introduces a 3-tier DRAM SSD architecture for MOE inference on edge devices. By keeping only attention layers in VRAM and loading export from SSD on demand, we reduce DRAM usage by about 80% compared to existing CPU offloading approaches. Our cross-layer predictive prefetching achieves over 92% hit rate and meaningfully recovers throughput loss to I/O. And we demonstrate for the first time that a 235 billion parameter model, MOE model, can run within typical edge resource constraints. We believe this opens up a practical pathway for deploying large MOE model on consumer devices. That's all for my presentation. Thank you very much.
Our next paper is Fight Essay, Making BP Pipeline Processing Elements. So guys.
This one.
Hi, my name is Chen Yi Wang, and I'm a junior student majoring in computer engineering at University of Washington. Today, I will present PIPE as a way to deeply pipeline the processing element in a systolic array to boost the clock, the frequency, and throughput for modern AI workloads. And first, please allow me to briefly introduce what the systolic array is and what we use in this. And the systolic array is one of the main microarchitecture for matrix multiplication in AI chip for its local PE to PE communication and the data reuse. And as shown here, each PE gets the input from its left or top and pass the output to its right and down. So there are two main the data flow, which is wait stationary and output stationary. They accumulate the partial sum at the different way, which lead to matrix multiplication. And so the key assumption in the systolic array is that each PE could complete a FMA in a single circle. So here is the wait stationary and output stationary. For the first one, we first load the weight into the systolic array, and then we input the if map from the left, and the partial sum is accumulated from the top to the bottom, and we could drain the output in the bottom. And those are the shift registers which could meet the timing schedule for the PEs. And for the output stationary, the weight input from the top and the if map input from the left, and the partial sum is accumulated looply at each PEs. So both two ways and have the one same assumption. Every PE produces the result every single circle. So the problem is that in int8, the critical path of the FMA, that is only 400 nanometers, but actually if in more than large language model, they use BF16 or FP16 with FP32 accumulation. As shown in the table, BF16 and FP16 FMA delays exceed 2 nanometer, which is 3 to 4 times longer than int8. So the critical path in a PE becomes the bottleneck for the future improvement. So there is a nature fix. We pipeline the PE and boost the clock, the frequency. But there breaks the timing assumption. WS and OS all depends on, as we mentioned, that each PE and cannot produce the result in a single circle. We produce the result for multiple circles in the pipeline PE. So for detailedly is that in WS, the partial sum from the P above arrived late. So the if map is already there, but the partial sum we need is not arrived. So there is mismatch. So there is bubbles. In OS, the feedback loop become multi-circles. So new data arrive before the last accumulation, the last partial sum is ready. So there is data hazard. And we needed to have a pipeline-aware scheduling, which enable preserving high utilization and with compatibility with standard systolic exclusion. And that is what PAP-SA do, and we do in our research. So in the PAP-SA, we schedule the pipeline-aware scheduling, and this is for the wait stationary. What we do is very simple. We just add the shift register before, and to make the second row delay as circles instead of one circle. And which means is that the partial sum from the first row comes to the second row with as circle multiplication process. And also at the same time, the second row, the if map comes also with the S circle delay by the shift register. And in this way, the mismatch is solved, and we can have the scheduling just as what a classical WS do. And as we can see here, if we let S equals to 1, that is just what we do in the classical one. And with double buffering, the initiation interval stays T, which is bubble free at a higher frequency with the pipeline PE. And for the output stationary, PEP-SA interleaves multiple matrix multiply across in pipeline slots. An S circle P naturally has S slots, one accumulation plus S minus 1 pipeline register. Each slot is a separate accumulation context. So the P takes a new operand every circle. The same slot update are separated by S circles. The hazard is gone. But there is a problem in the draining process. And if the first matrix, the output is not finished draining, the output SRAM is still busy receiving the output. So if we want to use that, we need to have the R circles in the matrix, which lead to which solve the draining process. And the same slot reuse is bounded by K. No extra register file is needed. Oh, also with double buffering, we can have the 100% utilization. And because we have the stream matrix get in one by one, and so that could solve. So if the S equals to 3, which means we got a 3-stage pipeline. And this table summarizes the formulas. S is the P pipeline depth for the stage for each computation is go. T equals to M for WS, and R is the array dimension. K is the reduction dimension. With double buffering, wait stationary initiation interval stays T. The output initiation interval is R across slots. K is for the same slot reuse. As I just explained, if S equals to 1, recovers the classical baseline. In all cases, the double buffer could make the bubble free for higher frequency. And we synthesize DF16 PEs with cadence genius on AS87 PDK and extended scale sim with double buffering on a 128 and 128 array, which like the TPU. And we added bandwise raising and overlap and S-stage pipeline feature in the scale sim. And we test the 6 GMM kernels. 2 is memory bound, and another 4 is compute bound. And first, we test how many frequencies that could reach. First of all, that is the baseline is 0.88 gigahertz. And if we add 1 stage on, that will be 1.46. And if 2 stage is added, that is 2.1. Which is 2.38x faster. However, though the area goes up 41%, but the performance per area is still improved, which is 1.7x. And here is the result get by the scale sim. And the peak compute goes from 29 to 48 to 68 if the pipeline stage is increased. The dB means double buffer here, so we can see that the double buffer is important. And if without double buffer, the gain from the pipeline is 8 by the stall. And the same story for OS. The peak scale with increase with pipeline depth. The double buffering is also important here. And here is the final result. For the bottom line, up to 2.11x the throughput, and also 1.51 performance per area gain. The PE pipeline work and the PEP-SA makes it practical for real workloads. And that is all for the PEP-SA. And an advertisement for myself. I'm a junior student now, and I'm looking for PhD opportunities for 2027. And thank you all for the hearing.
Any questions for the speaker? On any of the techniques that you identified, do you have to go make model changes as well?
I'm sorry?
To get the kind of pipelining enhancements, do you have to go modify the source model too?
The source model?
The model definitions itself. You have to modify the operators of the model.
We just modify we just add the add stage in the PE, make one circle to multiple circles. That is what we did in the PE, and all the scheduling is same as the is roughly the same as the traditional TPUs, and we just add the shift register in the WS. That is very easy and could leave the most of the TPUs unchanged, and we just reschedule some. We just reschedule the OS and keep the register file same as the OS. That is the modification of what we did.
Thanks. Our next paper is cache flex. Explicitly control what you need in your cache.
Yeah, by the way, that's my cat. It's so small. One second. I can't see the top. Oh, I see. It's above it. Okay, 1 second. Let me just.
Just go to slideshow.
Yeah, where's my mouse? Oh, I see. Yeah. Okay. See if I can do it. Okay. Okay, so hello everyone. So I'm here to help presenting our group's work, Cache Flex. Explain control what you need in your cache. So my name is Jiayi Wang. So here's the outline for today. So we're going to go through the background and then motivation and our cache flex architecture. And finally, I'm going to show some experiments and results. So firstly, let's look at some background.
So while accelerators like GPUs and TPUs get most of the attention today, but CPUs remain a critical and fundamental component of the modern AI infrastructure for the following three reasons. Firstly, like cost efficiency. For private or medium and small size models, CPU offer a highly economical and secure alternative using existing infrastructure. And second is versatility. Even in like GPU heavy systems, CPUs are still everywhere. They manage I/O like coordinated control logic and take care of like non-parallel works. And on top of that, CPUs supports the full software stack. So in practice, they are still the backbone of any high-performance hybrid system. And finally, power efficiency. In edge scenarios like laptops, mobile devices, and IoT, we are operating under tight power budgets. We still need to serve personalized small-scale models with low latency. So in these settings, CPUs are often the most efficient and practical solution. And here's a motivation for our cache flags. So first, let's look at a gene running on CPU for an example. So in state-of-art like kernel, gems are we often use like tiled gem to compute the matrix measuring multiply. So we break a large matrix into smaller tiles so they can fit into the like on-chip memory hierarchy like caches and maximize throughput. So to fully utilize the like vector units or SIMD units in our CPU, the software has to reshape the data to the way we will load, make it to be like a continuous address, like here, like the A, if we want to do a dot product of A and B, like A is need to read it like in a column major order. And this data layout is not actually free. It introduces a lot of like extra register reads and writes. For small gems, it's more like obvious, like this layout overhead can take up to around 10% of total execution time. And another thing is like while our like in recent like when we are running real like gem workload with like our simulators in the CPU, some SIMD cycles are still like we say they experience a lot of stores. So there are several reasons for that. First is the bandwidth. So memory bandwidth cannot keep up with the SIMD throughput. Even if the data is like nearby, we still can't feed the vector units fast enough to keep them fully utilized. And second, capacity misses, like during software-driven tile transactions, like the L1 cache capacity cannot actually keep up with A, B, and C like tiling. So that will introduce a lot of like read and write like cache flashes between the L1 and the L2 cache, and even L2 cache and the main memory. And like also every time when we switch to a new tile, we trigger a high latency like a refetch, which stores the entire pipeline. So based on also, and there are like unnecessary energy and power savings. So like on the left, every memory access have to go through coherence like TLB translation and LSQ dependency checking and also tag lookups. So these energy is not like very good in our like modern AI data flows because like the AI flows, their data pattern and X pattern are very predictable, very like regular, and a lot of this work is actually unnecessary. Like if we can use like a software managed simple stretchpad memory at L2 cache, we could just move like virtual. We can remove the like entire process of like virtual address translation, tag checking, and we can bypass L1 and we can access data directly from L2 with larger, which has a very larger capacity. In this way, we can also save like a significant energy here. So what's our solution to respond to these like inefficiencies for like doing AI workloads on CPUs? So firstly, we could like dynamically convert portion of data cache into software managed and private stretchpad memories, SPM or SPMs. So this is very like the idea in like GPUs. GPUs, they have like a shared memory combined with L1 cache to become a unified memory space, and like user can dynamically change the size of the shared memory part and the L1 cache part to be to basically accommodate different types of workloads. And the second thing is, while we choose to make a cache become a stretchpad memory and cache compatible stuff, we choose to convert the L2 cache instead of L1 cache because L2 cache we have much higher capacity and much higher bandwidth, and it also opens like bank-aware data paths. And three, while we are accessing these like stretchpad memory, we can just bypass all these like a coherence check, virtual memory translation, tag lookup, and these things and all these overheads, and we can also use less space for like addressing. So that's our solution and forms our cache flags. So what does cache flags architecture really look like? So at the right side, we show a very simple diagram for our like microarchitecture. So what we did is we extended the existing like ISA for to accommodate for our SPM access, and on top of that, like we also introduced some like lightweight SPM access patterns, so which allows that your CPU can directly access the SPM and allows that your CPU can basically translate memory directly between the SPM and the cache. And so let's introduce the ISA extension first. So here we introduce 4 ISA extensions. So as the SPM memory space, we introduce SPM load and SPM store. So this basically says you can directly load data from the SP stretchpad software control memory into the register file, and you can directly store the register file's data back to the software manager, the SPM. And the SPM copy and SPM write back is like how you manage the data between your L2 coherence cache and your SPM space. So SPM copy just says like you directly move the data from the L2 cache into the stretchpad memory. And SPM write back says you write back the data from your software controlled stretch memory back to the L2 cache. And why do we need the SPM copy and write back? Because if you look at this, the right side, like if we want to move the data, we want to read some data from the stretch memory after computation, and we want to write, basically write back to our main memory, we need to basically access the SPM first and use load the SPM data back to the register file. Then through register file, then we can actually go through L1 and L2, finally load it to the memory. And also vice versa for the SPM store. But if we have memory SPM copy and the SPM write back instructions, we can directly like bypass this L2 cache and load store queue, and also like here store queue directly like shuffle data between the L2 cache and the PM. That's within the cache itself. And so how do we actually design the load store queue for our cache flags? Because like now we have basically 4 more new types of memory load and store mechanism. One important thing is that we need to ensure the memory consistency during this process. So that's why we need some special like design for the load store queue. So here is like our original CPU load store queue. We have load queue and store queue. So when we actually issue SPM copy and SPM write back, these 2 instructions will be sent to the store queue for this to ensure that there's like no speculative memory access. Like these instructions cannot basically execute speculatively. They must be committed before writing back because they will modify memory. And also for these instructions also involve virtual address translation. Like normal LSQ handles the virtual to physical address translation for these instructions. And finally, we need to also handle the store to load forwarding. So for these 2 instructions, although they are treated as like a store instruction and they are sent to the store queue, here we can not actually like enable the actual store forwarding to the load instruction here, because like SPM copy, it sits in the store queue, but it's just a load from the coherent memory. So it never forwards any data, and SPM write back does not carry any data itself. Everything is happened like just within cache. It's not like going through the register file and L1 cache. And besides the normal LSQ, we need to insert these 2 instructions. We also need a special SPM load store queue to handle the memory consistency here. So at the right side, at the bottom side is our normal SPM load store queue. So basically our SPM copy and SPM write back will be also like sent to the normal store queue, also the SPM's like load queue and the store queue to ensure there's like the memory consistency and the correct sequence of loading the data. But for our SPM store queue, we don't do like store to load forwarding because like all operations in SPM are explicit. So you can think of it as a large software managed register, which is predictable. We will not add like this complexity to our SPM load store queue. Okay, so let's just go over quick operation like after the load store queue, how we actually do this in what's the procedure actually when we actually execute these instructions. For SPM, load store is quite simple since it's just like a load and store data between the register file and the SPM. So we just like treat it as a very simple memory. And for SPM copy and write back, there are several cases that could happen. So at the left side is the first case that we already have data in L1 cache. So when we actually do the SPM copy, we want to copy some data from the cache to the SPM. We're gonna first like in the L1 cache, we're gonna write back with updated data. If data is updated, write back to the L2 cache first to ensure like L2 cache and L1 cache data are the same. And then we directly move the data from L2 cache to the SPM. And for write back, it's similar. If the L1 hits, then we will basically invalidate this L1, L2 data here in order to make a space for the SPM data to move from the SPM space to the L2 cache. But what if like L1 miss? L1 miss is even simpler, since that means like the data copy in L2, there's no data copy in L1 like there. The data is still is only in L2. So we directly do the data shuffle, like we move data between L2 and SPM without like intervening the L1 cache. And a more complicated is like both L1 and L2 miss, then that involves more operations. So the copy, since we miss the L2, the data is not in L2, we need to go through the normal cache pipeline to get the data to L2 first. Then we move to the SPM. But for write back, there are two cases. For normal write, that you are write some data back to portion of the cache line, not the entire cache line. Then we need, if the L2 miss, we need to fetch the original cache line first, and then we fill the cache, and then we can write from the SPM, and SPM will finally send an acknowledgement back to the load store queue. And if we are doing the whole line write and L2 miss, then we don't actually need to bring that line here because we are overwriting the entire cache line. So we just write the SPM for that entire to the L2 without actually fetching the original data. And okay, so that's how it works. And finally, I'm going to show some experiments and the results. So what we did is we modified the Gen5 CPU simulator to support our these instructions, and we modified the the hardware architectures. Like we added the load store queue, and we added the dedicated SPM to L2 normal cache banks interconnect to enable the data shuffling between the normal cache bank and the SPM bank. And here's some parameters of our CPU model here. And here's some primary results we have. So basically, the right part is the cache flex, and the left part is the baseline. So we can see like among different gem size, and for like large gems with large tiling, we actually achieved better performance, like around at least a 10% performance boost with a normal CPU. And for the energy part, basically the SPM-based DRAM access, we will reduce some DRAM access with software managed stretch memory, so the DRAM energy actually lowered a bit. And yeah, yes, that's it. So thanks for your attention, and we appreciate any questions.
Let's thank our speaker. We are running a couple minutes behind, so we're happy to take the questions. Our next speaker is Esha. She's a senior researcher at Microsoft, Azure Research Systems Group. Her research interests include efficient AI in the cloud, spanning the layers of AI platforms, hardware and data center design and provision. In the past, Esha has also worked in sustainability, memory systems, and compression. She has published prominent papers at mainline conferences, and she has a PhD from Curiosity.
use this slide or do you want to move around?
I can just use this. Thank you. All right. Hello, everyone. Thank you for having me. And today I'll be talking about making the accuracy efficiency trade-off in agentic systems. So just a little note, I'm at Microsoft in the Azure Research Systems Group, but I am presenting work that was done in collaboration with MSR and students from University of Chicago, NTU, MIT, and UT Austin as they came as our summer interns last year. So just I wanted to start with sort of like a look back, since I did speak at this workshop 2 years ago. So our group does a lot of work across the stack for efficient AI, right? So crossing the layers of AI platform, hardware, and DC infra. And last time when I spoke at ASPLOS 2024, I spoke about these 4 works, which, as you can see, kind of cover the hardware and DC infra scope more. They do change the AI platform, but they don't really touch the model or model accuracy parts at all. Since then, we have sort of taken a different route and started playing with workflow accuracy, model accuracy, and I'll talk in a little bit about why, but those are the works that I'm here to talk about today. So systems, as we all know, are all about trade-offs, right? We have, for decades, built systems with these 5 primary trade-offs, but accuracy of the workload was always a given, except for maybe like approximate computing workloads, which right now is essentially most of the workload that we are dealing with in the data centers. So why is AI different? Of course, as we all know, it is approximate by default, and there are a lot of use cases within AI where some are more resilient than others, right? So we're using AI today for such a variety of use cases. Maybe there are some use cases where you don't want to play with the accuracy because you don't really know what sort of really bad impact it could have on some very important system. But majority of this is happening during design time, where the bugs can be caught later, or just sort of in conversations where, in chats and conversations where the effect of slight degradation in accuracy might not really matter as much. And finally, of course, the scale of deployment and expansion for this particular workload in data centers is just like something that we've never seen before, right? The capacity is growing much slower than demand. In fact, like we've seen that essentially we continue to sort of outgrow in terms of the requests for capacity, we continue to outgrow what we can deploy at Microsoft. Combine all of that with the fact that lowering the accuracy generally means that you, across the board, win for all of these trade-offs that we've been playing with for decades, right? And so then that choice of preserving accuracy at all costs versus reducing accuracy in a trade-off to all kinds of efficiency becomes a much easier choice to make. And so given all of this, we have been working more towards making this sort of accuracy efficiency trade-off, and I'll be presenting these 4 works today if time allows. So all of these are really runtime optimizations where we're trading off accuracy. The first one is called DroidSpeak, which is about KV cache sharing across LLMs. This work will be presented at NSDI in a couple of months and was led by Yuhan Liu, who was a summer intern a couple of years ago. So the use case that we are dealing with essentially is when there is context sharing between 2 models, whether it's domain, a general purpose model to a domain specific model, or like multi-LoRa scenario or personalized agents, or just these days any agentic workflow. When there is context sharing, the receiver model has to do prefill on that context again, which is something that the sender model, of course, had already done and built the context in its language, right? And the question that we started with is, can we have the models communicate in something that's not natural language, something that's higher dimensionality, such that we don't have to pay the cost of this repeated prefill. And the problem that we solve in this particular work is a small subset of this question, right? Where we're looking at models where we do share the same model architecture. So we're talking about either fine-tuned versions of the same model or different types of adaptations of it. So the important thing with this work was that between the receiver model and the sender model, we wanted the receiver model to have a higher accuracy on the workloads that we treat, because essentially we're telling the receiver model to not do prefill again and reuse the context of this other model. So the worst case scenario in this case is, of course, if the sender model did not understand the context as well as the receiver model is going to. And so that is our baseline assumption for all the data sets and scenarios that we drafted. So the first thing that we try to do is direct KV reuse, right? So can we just reuse the KV cache of the sender model at the receiver model as is? And as expected, the answer, the accuracy does get impacted quite a bit. So across the board, more results in the paper, but across the board, essentially, direct KV reuse does impact the accuracy for most workloads. So the next question that we asked was, what if we just reused the KV cache one layer at a time, right? Not all layers are important, especially when we see the fine-tuning in today's models, right? Where we do tend to limit the amount of parameters that are updated and things like that. So when we looked at that, so if we're just changing the KV, just sort of reusing the KV cache of just one layer at a time, we do see that some of the layers have way more impact on the accuracy than the others. And so we kind of took that and ran with that, right? We learned the important layers for each of these model pairs offline and found that this was actually robust across different types of data sets for different types of tasks. So essentially, it is more about what is the fundamental difference between these two versions of the model in terms of layers, rather than being very dependent on the task type. And so essentially what we did is build a system around it where we identify these important KV layers, and only for those layers do the recompute at the receiver model. Otherwise, we're just reusing the KV cache, right? So essentially what we've done is, depending on how many KV layers we are recomputing, we've kind of like created this Pareto optimal frontier in terms of accuracy and efficiency. So what I'm showing here is the latency saved from prefill, but essentially the X's are full prefill or full recompute. The yellow dot is what would happen if you did a full KV cache reuse, and the blue line is what we are able to achieve with this work. So this is an example of sort of trading off accuracy to efficiency when it comes to context sharing. The next thing that I'd like to talk about is around thought pruning with self-consistency. This is work that was presented last year at EMNLP, done in collaboration with Colin from NTU. So self-consistency is pretty popular when it comes to chain of thoughts, tree of thoughts, right? Essentially what happens is you give the model an input, and instead of generating like the one-shot output or a single chain of thought output like it usually used to, there are now several chains within the inference that get generated in parallel. And in the end, there is a majority vote, that's the self-consistency part, to finally generate the final answer, right? So this is a version of test science scaling that is becoming popular. The number of thoughts that's allowed is kind of arbitrary or heuristic based in most of these cases. It really depends on the model and whatever the planner, the LLM planner kind of thought would be the right thing to do. So as we started going deep into these chains of thought, the first thing we realized is that, and most of these results are from Quen models, by the way. So the first thing that we realized is incorrect answer generating chains of thoughts tend to be longer than the ones that generate the right answers. And again, we saw this across different data sets, right? It was an interesting result, and like one way to think about it, I guess, is that if you don't have a good, strong opinion about something, you tend to kind of blabber as a human, right, when you're asked about it. And it seems like that is what is happening here. So it seems like the model is not able to decide that this is the end of the answer because it never gets enough confidence into where it has gotten to. The interesting part was that we even saw this in math data sets, right, where it kind of just in a circle kind of kept going through the proof process while eventually landing at the wrong answer. So this was very interesting. So after this, what we did is we started seeing what are the factors which will help us kind of cluster similar thoughts. So we looked at cosine similarity based clustering using these thought matrices. There was a high intra-category similarity between the wrong chains themselves and the right chains themselves, right? So the clustering was working in terms of generating sort of like a representative wrong answer and representative right answer. And there was like low cross-category similarity. So what we ended up doing is essentially periodically prune thoughts based on this clustering. We allow warm-up, of course, avoid any early pruning. We retain the chains that have higher internal diversity. This was, again, sort of like a learned thing that we found. So if the cluster itself has internal, if the thought, the chain of thought itself has higher internal diversity in terms of sort of having thought about a lot of different points before reaching the final thing, we did retain it. And so finally, what we had with this, again, a lot more results in the paper, but finally what this led us to is less than 1% accuracy impact across the board. In fact, there were cases in which we even increased the accuracy because of the way we are doing the clustering and sort of, in some cases, reducing the impact of the wrong answers. And in terms of latency and generated tokens, we did achieve quite a bit of efficiency in here. So you can see that the latency, so the 45% lower latency is interesting because like if you consider the really long chains of thoughts that I was showing with respect to the wrong answers, what happens when we cluster all of them is that the tail latency kind of reduces and really helps with the overall latency. So that was the second one, where so far we were talking about sort of like a single model call or communication between just a pair of models. And with that, let's, I guess, move on to sort of these longer compound AI systems or agentic workflows that are more popular today, right? So the next one is Murakab. This was work done with Gohar from MIT CSAIL. He was our intern last year. An early version of this was presented at HotOS last year. So what Murakab is really is a cloud scale orchestrator for agents, right? So I guess I'll take an example and go from there. So this is an example video Q&A workflow. What's happening here is there is a video input and there is a question being asked about the video. The video itself is going through scene detection, frame extraction. There is a parallel speech to text extraction as well as some frame resizing to kind of finally get into the multimodal LLM, which then gets the question and then generates the answer, right? So quite a few different parts to the puzzle in this particular workflow. However, when it comes to transformer models, we are primarily looking at the multimodal LLM or like the much simpler speech-to-text model. And the rest of them tend to be more sort of domain-specific tools. So what we do in Murakaab essentially is to be able to reconfigure the DAG that was generated for this particular problem. So we're doing this on the fly, so we're doing it according to the current deployments. For instance, if this is running in the cloud and we have more capacity of a certain model available, which might be of ISO accuracy or like similar band of accuracy to the model that was chosen by the LLM planner, then we would sort of switch it in place, right? So things like that. So for instance, like the multimodal LLM, should I use Gemma? Should I use NDLM? One of them is much larger than the other, let's say, but spinning up the smaller one just for this particular request would lead to a way larger overhead compared to just sort of sending this request to an already running larger multimodal system, right? So that is the example of like how we change things according to the deployments. We also do this according to the cost or latency SLO of the DAG itself. And these kinds of knobs tend to be DAG specific or workload specific. So things like number of frames to extract, right? Do I really need to be able to read the text that was said in the video, right? So do I need to use speech to text essentially, or can I only use the video? On the other hand, can I just use this speech to text and only use like just an LLM that's based on text, right? Not a multimodal LLM. So these are like workflow specific knobs that go hand in hand with what the SLO of the workflow is. Because we are now coming across agentic workflows that have sort of like an end-to-end cost estimate that the user wants, but given that these workflows are generated on the fly, there's not a very good handle on what the cost could be once the answer is generated, right? So we're trying to create more and more options in the runtime to be able to meet these SLOs. And then finally, the hardware knobs. So this gets into the choice of the hardware as well as knobs like DBFS on the final system. It also includes AI platform knobs, things like should I be using a particular type of parallelism, or should I be going disaggregated versus chunked prefill, things like that, right? So essentially, for this particular workload, the knobs that we'll be looking for like platform level things would be CPU versus GPU. Like, can I just run this model on the CPU? Or like especially the domain specific tools that tend to be much smaller, can I just run that on the CPU? And then for model parallelism, what do I need to use? So going from the user input all the way to what happens in the end, essentially what we're adding here in between is this logical workflow. So we are asking the LLM planner or the orchestrator not to generate the very well-defined physical workflow that will finally run in the end. We're asking it to generate this logical workflow that says, that kind of like puts the overall workflow with sort of boxes that need to be well defined in the next stage. And then we are, based on all the options that we have, choosing the knobs to convert the logical into the physical workflow. So of course, all of this assumes that we have an agents and tools library that is well profiled, right? And then we have the runtime and infrastructure knobs that are coming from all the telemetry that is being collected from the cloud, right? So for agents and tools library, the version of Murakaab that's on archive today does assume that all of these are like fully profiled. So we have like a very rich profile of all of these things under assumption, but we are looking into more sort of runtime improvements, runtime feedback and improvements to make the system more amenable to dynamically generated graphs. So I'll just give a small example of what this can do, right? So this is an energy versus accuracy graph of the same workflow that I was showing earlier. And you can see that with all of these frame interval and speech to text true or false versus which model to use. So just with these knobs, we're able to see like a variation in quality of up to 37%, and a variation of energy up to 30x, right? And we can actually get an ISO accuracy solution with sort of 63% of saving if that much accuracy impact is allowed in the SLO tier that we are talking about, right? So again, it is an accuracy efficiency trade-off. It's not for free, but it gives us like huge benefits for the other things that we care about. Again, lot more results in the paper, especially on the cost and performance side of things. So finally, the last piece of work that I want to talk about is Sherlock. This is work that was led by Yunju from UT Austin. Again, the paper is in archive. So this work is more about efficiently doing reliable and accurate agent workflows, right? So as we all know, agent systems do need verification. In the ML community, there are a lot of different types of verifiers that are popular. One of them is refinement process. So you either use the same model to kind of loop through, so that's the self-refine process, or you could also do the advanced refine where you're essentially using a bigger model to see if it has an opinion on how this answer could be better. Right? So it's pretty much like a larger LLM as a judge in the refinement loop. There's LLM as a judge where it's choosing between two different answers that were generated either by the same model or different versions, different models, right? And then there's LLM debate, where there are rounds of debate until they finally sort of agree on a consensus. And then finally, the self-consistency stuff that we talked about earlier, where there are different chains of thought, and there is either a judge or a majority vote in the end. So this is just, I guess, a sampling of the verifiers that are popular in the ML community today, but we are seeing more and more of these coming up. And as systems people, I hope all of these things scare you, because it's a lot of overhead to be able to generate a better answer, since we all know that each circle here represents a very expensive computation. So the default thing today is if you really care a lot about accuracy, you use a per node verifier. But of course, adding a verifier on each node is going to be super expensive and very slow. And so the first task we had at our hands is how can we identify vulnerable nodes on the fly, right? So these are dynamically generated workflows. How can we figure out which of these nodes is going to, essentially if you do fault injection, which of these nodes is going to lead to an error with higher probability than others, right? So what we went with is a topological based study, and so essentially position-wise sensitivity, where the terminal nodes are very important, the root nodes are very important. The fan-in degree and fan-out degree has a huge impact on how fault tolerant that particular node is. So combination of all of these things turned out to be a very good estimate for this dynamic vulnerability analysis. And of course, this can be extended to include task-based vulnerability, right? So each node is executing a type of task, it's executing a particular role. And you could take that role into account to kind of enhance this topological identification of vulnerable nodes. So this is how we deal with this on the fly for dynamically generated workflows. The second question is, how do we choose the verifier type, right? So I talked about many different types of verifiers. And as you would expect, different verifiers have different they, like different workloads prefer different verifiers overall. Um, alongside that, the tasks within a particular type of workload also prefer different verifiers, right? So it's not as if like all the coding questions prefer like a refinement process with a verifier or something. Some of them do prefer LLM as a judge, for instance. So given all of this, the way we choose the verifier is essentially with a small model that we based on modern BERT, and we trained it with all the different choices that so essentially for each task we have this uh, array of what each of the verifiers would generate, and then the cost function could either be the loss function could either be inclusive of the cost, or it could just be the accuracy, right? So you could just say that it's a 0 or 1 factor depending on whether the answer is going to be right if I use this verifier, or you can sort of normalize it by cost or any other metrics that you care about. So what we ended up doing is a cost normalized loss function, and this is what it gives us, right? So we are able to, again, sort of generate this Pareto optimal frontier where we're looking at the average task accuracy versus the cost. And so depending on where in the flow we are in with respect to the SLO that's expected for this task, we could sort of choose a point on the Pareto optimal frontier. With respect to accuracy and normalized cost, we do much better. So we're getting better accuracy while being much lower on the cost side. You'll see that the yellow bar is still way higher than the blue bar in terms of cost. But that's where we are in terms of, like if we use more LLM calls to be sure of the answer, it is going to be very expensive, especially if we're going to use larger LLMs to do this, right? So a lot more work to be done there, but this was sort of like a systems view into how you could build a more efficient, reliable workflow servicing. So I talked about like 4 different examples here, but of course there are way more examples. If you look around in the research community, there's a lot of work on hybrid model selection, model routing, right, on the fly, figuring out the toughness of the query and then using smaller models for easier queries, things like that. There's a lot of work on different types of KV cache compression, whether it's token dropping, quantization, right? There's expert selection fuzzing, early exit. So myriad of tricks that are being applied in this whole space. So hopefully we all agree at this point that there's a lot of opportunity in this sort of like efficiency, accuracy trade-off. But what are the challenges, right? So the first one, the glaring one, of course, is the metrics. So we, as a community, we widely have agreed for a while on perf per watt as a metric that different hardware and AI platform techniques are measured up against. But we need something similar in terms of this sort of accuracy efficiency metric, right? How do we reason about this at the workflow level, at the LLM level? Like, how does the accuracy at the LLM level sort of translate it workflow and as the workflow changes over time? The second one is benchmarks. Of course, the accuracy impact would change a lot for different types of prompts. So we really need representative benchmarks for each of these use cases. And finally, we have to think about feedback loops online, right? It cannot be, like we cannot just decide that this is what we are going to do and then serve it exactly that way, especially if that workflow is going to be used for a while in a loop or so. We do require feedback loops where, you know, either you're doing prompt evolution in a loop, or you are sort of changing the model or changing the system design choices that you made based on the impact that it generated, right? So for that, we really need the feedback from different points in the workflow. So this is a very tough problem that we are just starting to work on right now. So yeah, with that, I guess I'll stop my talk here and take any questions if there's time. Thank you.
Thank you. We have time maybe for one quick question.
Hi, Mr. Very nice talk. When you talk about matrix, is it just the LLM or the overall system you're talking about?
When I talk about what?
The matrix to measure the.
Oh, both, right? So depending on what part the impact is to, right? Whatever system. So essentially, what I'm trying to say is that we are suggesting that the systems should change to be able to make this trade-off. If it's just that we are changing the model choice or that we are doing KV quantization or something that's limited to the LLM, in terms of what that particular LLM's accuracy becomes, but it still has an impact on the end-to-end workflow if you're talking about it in an agentic sense, right? So, and how exactly that particular node impacted the workflow is a very difficult question to answer if you're just sort of trying to aim this with like feedbacks generated with online users, right? So I think that is going to be a difficult problem.
Let's thank our speaker one more time. We'll continue with our paper sessions now. The next paper is Fast NF4 Dequantization Kernels for Large Language Model Inference. Do we have any other speaker? Others for Fast NF4 Dequantization? We'll skip ahead. So we go to iFuse, Profile Direct Speculative Load Micro Op Fusion for data center applications. We also have this, we offer this for store or recompute.
I don't have a HTML. Does this work?
Do you need to advance the slides?
Yeah.
This doesn't seem to be working. Why don't you start? I'll give you something else.
Hi everyone, my name is Deepanjali Mishra. Today I'm really excited to talk about my project, Speculative Load Micro-Op Fusion. Okay, so the setup is data center applications run across millions of servers, serving a variety of applications such as LLM inference, social media, recommendation systems. So the problem is these applications process massive amounts of data, and the question is, what causes performance bottlenecks in these data center applications? So here in this graph, I'm showing you a bunch of applications on the y-axis and the bottlenecks on the x-axis. This is prior work from Google, and so basically what I mean by backend stalls is stalls in backend pipeline resources, and the takeaway here is around 40 to 60% of processor cycles are spent being backend bound, primarily due to memory accesses. So the takeaway here is backend stalls are a key performance bottlenecks in these applications. Does this work? Okay. Okay, so the question is, how can we reduce these processor backend stalls? And there have been several processor optimizations for decades now, such as prefetching and whatnot. So in this work, I'm focusing on one such existing optimization, which was proposed decades ago, which is called load fusion in general. But in this work, I'm focusing on load micro-op fusion. What that means is memory load instructions are broken down into one or more simpler form known as micro-ops. And here I'm going to demonstrate what that means. So let's take a scenario without a fusion. So what that means is, in this example, say we have two assembly instructions which perform two memory loads, and each of these translate into two different load micro-ops. So here's a processor and a memory, and if you would need to fetch this data, so you would the processor would send a request for the first load, followed by the second load. And here, the takeaway here is the processor issues two separate memory requests to the same memory region, specifically a cache block. But with this fusion of loads, what happens is you have a memory load, and then you have another load which is to the same region. And this fusion essentially merges these two micro-ops into a single micro-op. So you send a fused memory load request, basically reducing the total number of requests you send to the memory. That is the key goal. So yeah. So, but the question is, how valuable is fusing this load micro-op? Like, why should we even care about this? So here in this graph, I'm showing you a bunch of applications on the x-axis. It's a combination of database applications like MongoDB and Postgres, and other graph analytics applications like depth-first search, depth-first search. And on the y-axis, I'm showing the speed-up percentage compared to a no fusion baseline. So here, the takeaway is, on average, we see around 9 to 10% of ideal fusion performance benefits. So this shows that this fusion is a promising technique. The next question is, how close is the existing state of the art to this ideal case of fusion? So I'm showing a similar graph. So the x-axis shows applications and the y-axis shows the speed up percentage. So you're seeing the same graph just with another color, that's the pink one, that shows an existing load fusion technique. And the takeaway is this technique is able to achieve only around 13% of this ideal fusion performance. So the question is, why aren't we close to this ideal fusion? So the question we ask in this work is, how do we achieve this ideal performance with this load micro fusion? So specifically, we focus on, are there predictable parameters inherent to these load characteristics that we can use to guide fusion? So here's the intuition. What we know is both loads access the same cache block. Here's an example. If the first load accesses, say, the first byte in the cache block, and the second one accesses, say, at an offset of 8, so this is, the first one was at an offset of 0. So this offset delta is, say here, in this example, 8 minus 0, it's 8 bytes. The reason I'm showing this is, in this talk, I'll be talking about 3 things. First, we characterize opportunities for fusion in the applications I'm evaluating, and then talk about the technique that we propose, and finally show the results. So in this characterization, the first graph that I'll be showing you is about the cache block offset delta that I tried to convey what it meant. So in this graph, so what this graph shows is, on the y-axis, we're seeing how often a given offset delta appears, and the x-axis shows every possible fusible load pair. So the takeaway here is, having more points in this graph closer to the 100% means that this parameter is predictable versus less. And we find that these load fusion opportunities that we see in these applications have predictable cache block offset delta. So using that characterization result, we developed this technique which I call deep fuse. So here's the high-level overview of this technique. So the goal is to profile applications running in data centers and generate, say, a memory access trace. The reason is we want to identify loads that are accessing nearby region, and we do that by analyzing this trace, which is a part of the second phase. So you perform offline analysis to identify fusible load pairs and generate a bunch of proxy parameters that can then be used to guide fusion at runtime. Since the processor front end does not have access to the memory address, we use program counters as a proxy for that. And then this is used to then guide runtime fusion. So this is the high-level overview of our proposed technique. This is an offline-based technique, but we do have results for online-based mechanism as well. Which does not show as much performance benefits as we see through profiling. So here's the last phase, so the evaluation. So I'll be showing two graphs. The first one is performance, like how useful is our proposed technique compared to the ideal fusion that I showed you all. So the x-axis shows applications that I've been showing, and y-axis shows the speed up. It's the same graph that I showed, so showing the teal color is the ideal fusion, the pink one is state of the art, and this lime green is our proposed technique, that's deep fuse. The takeaway here is, so as you can see, the steel bar is around 9% and deep fuse shows around 7-ish% on average across these applications. And just one source of performance benefit here I'm showing is the impact on backend pipeline resources. Here I'm just showing the raw number of L1D cache. So since we're effectively fusing a bunch of loads, so that translates into fewer requests. So on average, we reduce around 30% of requests sent to the cache. Yeah. So yes, so in this talk, I showed a characterization of this cache block offset parameter that we then use to design our profile-guided load fusion mechanism, and then finally talked about how much performance benefit this shows. Yeah, thank you.
Any questions for us? In order to accomplish the fusion, do you have to allocate any registers?
That's a good question, yes. So since we're doing speculative fusion, so when the first load fetches the data required by both loads, it does allocate an additional register, but then during register renaming, we allocate the same register that the first load allocated for the second load. So there isn't any data movement within the registers itself. Yeah. Thank you. Thanks for the question. Yeah.
Our next paper is store or recompute, characterizing the carbon trade-off of page cache retention and LLM influence. Do we have any authors of FastLF4 in the room?
All right, thank you. So it sounds like I'm the last paper for today, so hopefully we can make this fun. We've got one more. I just want to preface that this in general is a talk for work that's in progress. So some of the results that I'm going to show we've gathered, but some of this work is really leading into some future work. So very much open to questions and of course feedback at the end related to that. So my name is Avnash. This work is in partnership with some individuals at Carnegie Mellon University, as well as some folks in Azure Research. And we've been exploring this question surrounding KV caches. As I'm sure we're all aware, there's been a big increase in terms of storage requirements associated with LLM inference. And so we've been exploring this question of when do we choose to store a KV cache or potentially recompute it. And we've been exploring this question from the perspective of looking at carbon emissions. So in general, data center carbon emissions have been growing steadily. This trend is only projected to continue to increase. And as part of this, there's this imperative to reduce data center carbon emissions. Now, data centers emit carbon across a number of different life cycle stages. You can think of this as the embodied phase and then a later operational phase, which is when you're actually using the servers. So this embodied carbon is related to manufacturing, transportation. We can call it scope 3 for those of you that are familiar. And then on the operational side, we have carbon on site. So when we're actually running our servers. And then there's off-site carbon, our scope 2, which is related to the electricity that we're consuming. In our case, to, for example, run our LLM inference. And so LLM inference adds to these carbon emissions within the context of a data center and this overall kind of life cycle. Now, to give a bit of context, LLM inference in general, you have a user, maybe it's you right now, you're sitting in front of ChatGPT or Claude or whatever it is, you send over a query that goes to some server that's located elsewhere in what we might call the cloud. Now that server, as part of this LM inference pipeline, is going to generate a KV cache from this prefill stage, and it's going to use that to eventually give you back a response. Now the next time this user sends over another query, we might decide to reuse this KV cache to be able to send back another response. Now there's this question of, do we decide to accommodate the storage overhead of storing this KV cache somewhere, or do we choose to potentially recompute it the next time that we get another query? So to explore this question, we've been thinking about this from the context of two different kind of hardware server configurations that you might want depending on the scenario that you're interested in. So if you're interested in primarily storing the KV cache, you obviously want more SSDs on your server. However, these SSDs are primarily dominated by large amounts of embodied carbon from that manufacturing process that I mentioned. On the other hand, if you want to recompute, you might want more GPUs or compute in your server. However, that's then dominated by operational carbon associated with the high power consumption of some of these GPUs. This leads us to this overarching question of how can we decide whether or not we want to store or recompute the KV cache based off of carbon, and that also has some implications, which I'm not going to get into heavily in this talk, but that has some implications for what your server configurations might want to look like. So in this talk, I'm going to present our framework to evaluate this KV cache storage versus recompute problem, explain the carbon model that we use within this framework, present some break-even points for when you might want to choose one or the other, and introduce some future work, like I mentioned, of where we're trying to go with this. So I'm going to start out by giving some context on what our framework looks like. So to go through this pretty quickly, we have some parameters related to our large language model that might be things like the model size, and we have some server configuration. So what does our hardware look like? This we feed into performance models, environmental metric models to get metrics like carbon, water is something that we're in progress with, and as well as performance, so specifically latency or time to first token for those that are familiar. Then we have this evaluation portion where we want to feed in a scenario. What is potentially the query length in terms of number of tokens? What is the reuse distance? How often are we expecting another query from the user? And then that then leads us to this decision of do we store or recompute? We call all of this our kind of store versus recompute framework. And ultimately, this gives us some sort of recommendation based off of carbon. So in terms of how we actually calculate the storage versus recompute carbon, as I mentioned before, there's embodied carbon, there's operational carbon. This gives us the overall carbon. And in our framework, we're considering this added carbon that comes from choosing to either recompute or store relative to some baseline. So I'm going to give just some high-level details about our carbon model and the framework. I'm not going to go into too much depth here, but in general, we're looking at power consumption. We're converting that into energy. And then based off of the electricity, the carbon intensity of our electricity grid, we then convert that into some operational carbon. Now for the storage scenario, we want to scale by, for example, the portion of the SSD that's actually used by the KV cache to kind of attribute this fairly. And we want to consider this reuse distance that I mentioned. How long are we actually storing this KV cache for in the SSD? And on the recompute side, we want to consider batch size, and that batching potentially lets us amortize the carbon as we recompute. And on the embodied side, the real difference here is that we're looking at embodied carbon per component, so it might be per SSD, might be per GPU, to get a total embodied carbon. And we're building off of some existing carbon modeling work to be able to generate some of those numbers. Now, once we have some of these carbon numbers, do we store or recompute? In order to answer this with a metric, we've been considering what we call the break-even reuse distance. You can think of this as like a tipping point or break-even point where it's a storage duration where both strategies will give us the same overall added carbon. And then once we can identify this break-even point, this can help recommend what we might want to do. So I'm going to present some of what these break-even points might look like. There are obviously some caveats that this is specific for a certain model. So we've been considering storage versus recompute depending on the storage duration. So on the x-axis here, we have the storage duration in minutes. What this means is this is how long we're storing the KB cache for in the SSD. And on the y-axis here, we're going to have the added carbon for this one query that we're, or this pair of queries that we're considering. And the data that I'm going to show is specifically for Llama 2 with 70 billion parameters. But you can kind of apply the same framework to other models and other configurations that you're interested in. So in general, we end up with this, these two different colors that I'm showing here. So on the left, we have this region where, from a carbon standpoint, it makes sense to continue to store the KB cache. And on the right side here, from a carbon standpoint, it makes sense to recompute the KB cache. Now, where this break-even point lands depends on things like your grid carbon intensity, where you're operating, depends on the number of tokens that maybe you're passing in. And of course, it depends on the large language model that you're considering, as well as the specific hardware components that you're looking at. But this is an example of the kind of trade-off space that you can generate. Now, as I mentioned, carbon intensity is something that impacts this. On the x-axis here, we have the carbon intensity in terms of grams per kilowatt hour. And on the y-axis, we're showing what that break-even point, or that line that I showed previously, would look like. And in general, as you might expect, kind of the dirtier sources of energy that you're using, it makes sense to store the KD cache for longer because you're prioritizing that embodied carbon over some of the carbon that you emit by actually, running your GPUs for longer and emitting more carbon as part of the process. So I've mentioned this kind of very specific framework that's very specific to KV caches. It has a lot of kind of caveats. What if we could generalize this framework to potentially other case studies beyond just KV cache storage or recompute, and also to other environmental metrics? As I'm sure we're all aware, there's a lot of headlines and concerns around water consumption when it comes to AI data centers. So there's a number of other metrics that are being discussed but maybe aren't being explored necessarily in kind of the systems architecture community. So I'm going to leave us with some introduction to some future work that we're exploring, which is a more generalized framework for server design evaluation. And so from earlier, I flashed up this framework that we're using to decide whether or not to store or recompute the KV cache. And I want to identify what this might look like if we were to generalize this framework to other scenarios where we're deciding between either recomputing something or storing something. So that doesn't necessarily need to be the KV cache. And so what this looks like is a more general workload here on the left side that feeds into a framework. In the middle here, we're adding other metrics like water, looking at forever chemicals or PFAS, or electronic waste. And on the left here, we're passing in more general server design changes. And our output is some more general trade-off between metrics, not necessarily, again, just KV cache specific. And we can feed in other case studies to be able to evaluate. So the idea here is to unify some of these disparate models, metrics, and trade-offs between these metrics into one framework that you could then apply for a number of different recompute versus storage type scenarios. So the main premise of this talk is that KV cache retention policies have an environmental impact. And from that, we can then choose to store or recompute this KV cache in an effort to reduce carbon emissions. So again, presented a framework that you can use for KV cache specific scenarios, and leaving you with this idea of moving towards a more generalized framework that we're in the progress of working towards. Yeah, thank you, and open to any questions.
Any questions for the speaker?
Thank you. This is interesting. So, in a way, you're kind of moving competition in time. Have you thought about this like a battery at all? And then beyond that, have you thought about having kind of dynamic hardening
Yeah, that's a great point. So I think two parts to that. The first part of kind of adjusting in time. Yeah, so the idea is this is one very specific decision that could then plug into a bigger scheduler. There's been some recent work looking at that, but plugging this into a scheduler is something that would then let you do that of, do I defer this decision to later? And that trade-off space might look different. So if, for example, there's a time period where there's more solar on the grid, you might want to wait to make this decision then, and then it might make sense to potentially always recompute your KV cache. The second part of your question of kind of treating this as a battery or adjusting, so with the grid in general, you can't necessarily kind of directly control what the carbon intensity looks like. You're almost responding in a sense to what is being generated, what is being put out there. But what you can do is look at historic trends and kind of project what that carbon. So there are models or models that are used to predict what that carbon intensity looks like. So you could use that to then plug into kind of a scheduler, getting to the first part of what you're mentioning. But yeah, so that would be an interesting kind of extension of this one-off case study.
Any other questions? Can you share some intuition behind the slide where you show the cost of storage increasing as the time of the query getting longer, the time between the queries, the multiplier? Why does that blue line keep going up? Is there any intuition behind it?
Yeah, so the general idea with this going up is we're taking some fixed carbon emissions, and when you're storing for longer, you're both operating within our model. You're operating that SSD for longer, so you just have more energy consumption associated with running that SSD. So that's kind of one assumption we're making there. The other assumption that we're making there is that you have some embodied carbon over the lifetime of your device, and we're attributing how much of that embodied carbon is used for this one instance. And so the longer the longer that you what we're assuming is that you could amortize it potentially over more requests, but in terms of looking at this from the cost of just one query, for example, more of that embodied carbon is going into this one query. It's ultimately eating into that lifetime. I do see your point of, at the end of the day, you still have this SSD and it's going to go towards something. But for the sake of making this particular trade-off, it does increase the embodied carbon because you're using it for longer for this one particular purpose.
Another question, let's thank the speaker.
Great, thank you.
Our last paper of the session is a composite infrastructure efficiency index for GPUs.
Hello, everyone. Can you hear me? So this should be not more than 10 minutes. This was a position paper. Thank you, organizer, for allowing the presentation. And so I'm Raj, and we work at a very early stage infra optimizing company. Our goal is to understand infrastructure in a more detailed manner to see where the sources of inefficiencies are and build a platform where it is easy to deploy models as well as a continuous telemetry can self-optimize it, a different aspect of it. So the first thing is before you can optimize something, you have to measure it. And one of the reasons we saw that power is very hard to optimize because it's very hard to measure. It depends on the load, different workload condition. And when you talk about infrastructure at a large scale, it's very opaque. There are so many moving components. You have hardware, software, systems, workload, and imagine everything, AI, non-AI. So the idea is not to get sucked into all this complexity, but try to tease apart simpler details of this, abstract them away, and then tackle them in some kind of a holistic first principle manner. And so what we tried to come up here is a simple metric to actually quantify the inefficiencies, and then different vectors, how to diagnose different bottlenecks. Because at the end of the day, if the the telemetry is a monitoring tool, it does not serve the purpose. It has to be a diagnostic as well as optimizing. But before I go into little detail, I'll just give an example of my own AI uses. So today, I mean, many like you, I'm using, let's say, chatbot like Anthropic, Claude. I used to use ChatGPT, recently switched, and I'm probably not going back. So I pay something like $20 per month, and I looked at the token uses. I asked Anthropic, hey, how am I using the tokens? And it says typically a task which is about you're iterating 5-7 times because you are giving something, and I'm not coding actually at this point. So it says you are like 4 to 8K per task tokens. Basically, you are actually spending enough per month to cost Anthropic, $150 to $200 per month easily. But I'm just paying $20. So where is this? So there is the 6 to 8x investment for every dollar revenue growth. And similar question was asked to Sam Altman a few months back, and they asked, how do you will make sense of this AI investment? How do you going to the return on investment is going to work? So he said, we'll keep investing and build AGI, and then AGI will tell us how to monetize. The bottom line is, at the end of the day, a lot of the companies who are spending $6 for a $1 return have no idea how to actually optimize, and a lot of it goes into the infra. And so therefore, understanding infra at low level is a much needed problem right now. So you as a user, you don't have on the back-end side what is happening on infra. A lot of guys who actually operate those infra also don't have much idea about what, because it's very complex. So it's a very large dashboard. It shows you token per latency, GPU utilization. Just an example, GPU utilization itself is very fuzzy number or compute utilization. You talk to a number of people that they mean different things. Someone thinks about GPU as a resource. Someone thinks about SM. Someone thinks about tensor core. So compute utilization itself is so fuzzy. And they have a lot of these metrics, but they don't sort of kind of go together. This dashboard is really just kind of monitoring from a different perspective. So the problem is, can we actually build something? And so before we build, we want to we are inspired by this one adjacent metric from the economics world, HDI index, you might have heard about it, Human Development Index. And HDI index, if you think about a country as a large infra, different components put together, it's economic, it's education, health. HDI index is a very simple index. It actually gives you a very good idea about a country. For example, if I say, a certain country is 0.8, you would immediately build up sort of a mental image saying that this probably is doing okay. Or if I say 0.5, you would think, okay, 0.5 is actually not that good. So the three metrics on HDI index are education, health, or malnourishment, and employment. And essentially, they actually capture a lot more other things. So if there is a political instability, wars, they're not even accounted. So you can think about for a country, which if you take as a very complex infrastructure, can be actually summarized in a simple index. Why not the data center we have? And of course, they have a lot of pieces. So here we kind of then started looking, what are these independent vectors? The first one is compute. At the end of the day, it's a heterogeneous. I don't want to get too much detail, but let's say there is some compute. Could be GPU, CPU. We'll figure that out at low level. But at the high level, given a compute, I have the workload, I have the compute infra or compute block of it, how efficient it is. And assuming in this case, you're isolating it that all the data is fed from its registers, right? So if that actually achieves 90%, you would say that vector is actually. So the 5 vector we looked at, from technical point of view, they are compute, memory, network. And of course, you can go 5 level deep to say, this particular metric sucks in network and so forth. But at high level, just let's come up with a number between 0 to 1. 1 means you cannot do better. 0 means, or 0.1 is really bad. And 50% means there is a 50% headroom to do better on that aspect. And the next one is the dollar. This actually ends up mattering more because at the end of the day, the companies and businesses have to make a sense of what they're investing. So it is CapEx, OpEx, TCO, everything you can include. And of course, the power and energy as well. So given a workload or given a particular type of use case, given an infra, I can then define on each of these metrics, what is efficiency? And then if I take the sort of the geometric mean of that, I will penalize so equally And then I can think about headroom is 1 minus whatever this IEE. Now, again, this may actually sound simplistic, but if you go inside EC or compute efficiency itself, you can define in different ways. Memory, for example, as you go dig down deeper, there could be multi-level. The first level could be the overall bandwidth utilization. The next level could be the distributions of. So, but then at the end of the day, you do have to kind of combine these metrics such that. Now, this matrix is good. What it can do is, and why it matters is that even though at high level you may have our same scalar matrix 0.7, but depending on where they are and what particular aspect is not optimized, they will bring down that together. But then depending on this bottleneck, you can apply the techniques which are sort of more tailored. So for example, if this is compute limited, I will probably go and optimize and do kernel fusions. Or if it's memory bound, I'll try to compress, or if it's network. And if it is a sort of, let's say, the dollar-wise, I'm kind of, let's say, running something on a much costly GPU, I'll try to go on the trailing edge to see if I can achieve the SLO. And similarly, then finally, I think there's a typo here. This is more of a power. And power-wise as well. So on the other side, when you think about data center as a heterogeneous clusters, or multiple different type of cluster of heterogeneous resources, and the other side, the workloads have so much diversity and so many different kind of use cases. The idea here is to match them in a way so that I don't optimize on one vector or two vector, because right now what happens if you run something on B200 like cluster, you actually saturate one or two matrix of these, and then rest of them and sort of is still underutilized. In many cases, we would say that if you do a training tensor parallel, you are probably running into NVLink bandwidth, and then rest you say, I can't do much better. Yes, you can do. You have to then basically think about what is the right compute size resources. And this imbalance penalty will actually then try to optimize the cost. So we are trying to build, we are very early in our journey, we are trying to build a framework where a telemetry tool which will understand these metrics at different level, tries to then come up with and feed to an optimization engine which is sort of self-driven. And I'll present some anecdotal evidence here. This is a really simple experiment we did. We took H100 and ran on Lambda cloud with a very little control. We were running Llama 4. So what the idea is that if you have a GPU, think about it's running without any optimization. You're generating maybe 100 billion tokens per month, and you are paying $1 million just for example. It could be a cluster, but so here there is no TCO saving. Unless there is there is a on and off switch, this inside activation engine. We don't know, that's TBD, what it is. It's a combination of a bunch of things. But if you turn it on, you say, by the way, I can save you cost, which could be a power, or it could be any combination of more tokens actually. And this is what I do. So what our experiment was this: we took Llama 4 MOE, we ran on A100 and H100. And this we did not even disaggregate, prefill, and decode. We just ran the whole thing into 8 of H100. And when we look at the token per second per watt, we knew that this is decode heavy because the input sequence length was small and output sequence length was long. So I think the input was 256, output was 8K. And if you have something like decode heavy workload, just changing the SM clock and lowering to 70%, you lost performance by a couple of percentage. But the overall efficiency was 30%. So if you look at the token per second per watt, was almost 30% better because you actually scale down the SM clock by 30%. Actually, it's 27 because that's HBM and other clocks are actually still same. But many of these infrastructure level things are actually not allowed if you're using any public cloud. What you need to do is then sort of build your own firmware layer, have more control over it. I think companies are opening up. Same thing on H100. Baseline is we are running Llama 4. And then if we run now, in these two cases, these two settings are, one is I believe is SM is running at 70%, one is running at 50%. And the points are changing because it depends on the overall system. So it cannot be that I can keep lowering to the point where at some point you will start losing the performance as well. So you have to be adaptive. Now this adaptive, again, you cannot profile and do it because the workload will change, the condition will change. So you have to hook up to some autonomous system and typically build a platform which has is agentic in nature, and therefore it monitors and applies these insights. So at a high level, just to sort of leave you away with, I think Professor Josep Torrellas already talked about all these adaptive things. I think to extending that, this adaptiveness has to come in some kind of a autonomous way, so that you are human in the loop, looking into it, understanding, but not necessarily making decisions. And that activation engine now, from simple GPU, if you have racks of GPU, can be much more complex. The important piece is the telemetry and knowledge. And then any of these can change to the point where they actually make sense. And this will adopt. So if the workload change, let's say time of the day where the queries or the increase, the load increases, the system should be actually able to work. So we are working on these ideas. We are looking for collaborations, interns and also academic collaborators in industry as well, to understand the telemetry aspect, which is self-optimizing, give the insight to the point where it becomes very simple for an optimization engine, and then building this whole framework. So we can discuss and collaborate on specific ideas. Thank you.
Any questions for the speaker?
Thank you for the presentation. Very insightful. So my understanding was that one of the gains was suggested by lowering the clock frequency, you're saving on watts, right? And that drives higher margin, I guess. But that does not account for sort of loss of the GPU usage, because like each GPU hour usually costs money. I'd rather even if you buy things that you're underutilizing GPUs. How is that, from your opinion, how is that factors in?
So yeah, power is just one thing. What happens is that if you look at the total TCO for a data center, I mean, you can typically say half is CapEx, half is OpEx. I think if you have high-end GPUs and gears, you will end up spending more. And the power is actually significant budget of your OpEx. So what we're looking at is to prioritize the list. But yes, I mean, power is not the only thing. There are other aspects to look at. Running on different kind of GPUs, which are more. So for example, I mean, NVIDIA announced they are kind of mixing the Raegan with the LPX, Grok LPX core. And so this heterogeneous cluster, what we have actually seen is many low SLO requirement use cases, you can achieve per parity on B200 to H100. And if you see the cost actually is a step function. Running inference, people have started looking at when there's a network bottleneck, you can have a better, don't do tensor parallel in a crazy manner. Don't run into NVLink problem. Open Compute has come up with this, ESUN and these kind of network-based, Ethernet-based. So absolutely, I think the idea is that you really need to look at, that's why the economics, the dollar amount is CapEx, OpEx, both is one of the factor, because when you build a chip, or you, as a company, you have a system, you have a horse in the race. But as a community, you don't. What you do is say, I can aggregate from 5 different cloud providers, and I can really run something like on RTX 5090, if my use case actually is. So it is actually important factor. And these 5 are, we think, are the fundamental, but there could be few more which you need to optimize for.
Any other questions? Not, let's thank our speaker. We take a 30-minute break and be back at 4 o'clock, and we will start with our star-studded panel at 4. So don't go too far. If you're on the panel, please try to be here by 3:55.
No, I can move.
No, this one move. This one.
Oh, this doesn't move.
This is stable.
Okay. I'll talk about the abstract of the panel. Do you want me to give a small introduction about you?
Sure. There's not much to say.
The variable, then you can actually bring it up on
As long as I remember what I said. Can't you do the flash thing?
order or something? Or just sit
We
anywhere?
just have to make sure that you and Joseph don't sit next to each other.
Okay, all right.
Otherwise, we'll team up.
Yeah, okay.
I'm just kidding. You can sit anywhere at all. Okay, so that's the sports team name. Is it Illini or Illini? How do you say it?
Illini.
Illini. Fighting Illini?
Yeah, Illini.
Is this your book?
Yes.
Hello, everyone. Welcome to the last session of the day. We'll be starting with the panel, and I'd like to introduce the panel first. So the title is Architecting an Energy First Stack for the AI Age. As the cumulative demand for AI computing continues to grow, new bottlenecks in technology deployment are emerging. These range from compute capacity to memory supply to cluster reliability to simply finding enough power to supply the infrastructure. Since these aren't easily solved with brute force addition of more chips, potential solutions encompass new model architectures, new computing architectures, high performance cooling designs, robust multi device software stacks, and even orbital data centers. In this panel, we will aim to identify the most pressing requirements for the computing stack of the coming years. We will discuss both the promising technologies and the hype to define a blueprint of the computing architecture where energy is the currency of success. I would first like to invite the panel moderator, Satyam Srivastava. Satyam has a PhD from Purdue University and is currently working as the chief AI software architect at D-Matrix. His work is focused on the architecture and software stacks required to make large-scale AI inference both economically viable and energy efficient. He is the co-founder of this workshop and has served as the co-chair since its inception in 2017.
Thanks, Neil, for the kind introduction. Welcome everyone. And as soon as our sixth panelist comes back, we'll get started. For today's panel, we have a very good mix of industry and academia. We have Zain from Stanford and Gimlet Labs. We have Nishil from UIUC. We have Esha from Microsoft. Josep, also from UIUC. Kennedy from University of Toronto. And Urmish, who's been at Sambanova till recently. Welcome, everyone. And as we start, maybe each of the panelists can take a minute to introduce what is it that they intend to communicate with this audience as part of this discussion. It's an open-ended topic, and the talks today have covered many aspects of it already. So what is it that is most important to you? You can start with Urmish.
Yes, I think during the theme of the panel, the need for compute and for memory is going to keep going up, either because the number of users are going to scale, complexity of applications that they're going to deal with is going to scale. So this need for compute and memory is not going to change. the exponential growth that we're seeing from the macro. What is interesting right now is, and maybe I've been close to Marathon almost a decade or more than that. This might be the first time that I'm seeing slightly exotic accelerators becoming very relevant, where you see mainstream companies trying to adopt it. So you would see a lot of hybrid deployments for efficiency. We put them on one accelerator, we put another accelerator, we drop all another accelerator. With the NVIDIA announcement and sort of within a particular convolution graph that we know. So that is an interesting thing that sort of, even from Sambanova point of view, we have done this kind of deployment and sort of seen success with the data centers in terms of adopting the hardware and success in terms of seeing improved tokenomics, either in terms of models or in terms of power efficiency of the overall system measured after deployment. So I do think that is a consistent thing. But what makes that then sort of extremely hard is then the ecosystem fragmentation in terms of software. How do you program each of them? How do you sort of build APIs that are general purpose? I think that is one place where I see a lot of investment happening, and I know folks from the I have been passionate about having folks to say about that. So that's where I feel a lot of investment is spending, and we see a lot more things here. The other place that I feel a lot more investment is kind of pending is right now every accelerator has a bespoke APIs to program them. It's very painful to sort of program the accelerator using their GPUs. Would love to see a solution that is before in the purpose that can express a lot of different ways of managing data and expressing that so that you can see the peak performance outcome of a single API. Because once you have that, you can imagine a scenario where if you have something like a code generation to couple with that with your single API, you can manage these parameters system.
Okay, so let me build on what was covered already. So I think definitely the need for compute and memory is growing. You can see anecdotally recently growth that not just Hopper, even Ampere GPUs right now raising prices on the market in the cloud because there's not enough compute to solve the agentic workloads that people are using. From the academic perspective, research perspective, the interesting thing is that things become very heterogeneous, even on a single, DDL chip. There's a lot of different sub-pieces that run different parts of the model. The models themselves become disaggregated. It could be called as a classical, example of compute intense versus memory intense workload. And it's only going to get more and more aggressive in this space. One of the challenge that for many years me and my colleagues tried to solve was building machine learning compilers to address the programmability of this chip. And it was always a challenge to match the human written manual code. And luckily, recently with AI, it becomes more and more practical to see that you can actually write kernels quite impressively fast. And it also but it's also at the same time accelerating the building of compilers because a single engineer can build a whole compiler by itself these days. So it's very interesting to see which of these approaches ended up being more mainstream. While spending 9 months of the year, I can see that we didn't reach a consensus which approach is better, but it's really both. We just see which one will be better at the end of the day. It's very exciting and promising. It's not actually very long on the direction. It's still a very important and interesting field. I think overall, there will be a young PhD student selected in the direction we want to work on. It's very exciting also because the actual compilers are all very important and relevant topics and a huge demand right now. And obviously, energy efficiency will be a big factor. Probably first, the people get out of energy everywhere, such as nuclear in the US and Canada, right? Because there's not enough electricity to power all this cloud, deployments.
Okay, so I'm going to repeat some of the stuff that I said during the talk. So I think that in the future, we're looking at the heterogeneous hardware accelerated. When this will happen, it's not clear, but we're moving towards highly heterogeneity, especially eventually sparks accelerators. Accelerators in network switches, smart meters. But this, of course, requires availability of software, so it won't happen just with one. I'm not just talking about compilers, but also all the stack software. In the meantime, I think academia has a great role to play in new methodologies to generate, deploy, and reconfigure accelerators automatically. This is a very fertile area. And new methodologies to automatically generate software, compilers, runtime systems for accelerators automatically. So that as soon as the hardware designers have a notion of what the hardware will be, immediately you get a compiler or a runtime system. In the meantime, I think we should watch for minimizing data movement in data center. As I said, this is the biggest problem. This is the biggest where the energy goes, minimizing data movement, and keep the hardware utilized. It needs to make sure that we don't have lots of hardware that are there really nice. And encourage students to look at developing frameworks for energy management, because this is a very complicated problem with many dimensions, and the gains potentially payoffs are there.
Given everything that's been said, I guess I'd like to add sort of like bookends to this stack. So one is on the power and cooling side, the data center infrastructure. Yes, we are hitting the wall with power availability, prime power available in the regions that we would want to create data centers. It's just not there yet. I think that all the work that we've been doing at the cloud level, whether it's oversubscription, whether it's availability, and trying to figure out how to best use this power, how to create more flexible uses of power and work more closely with utility companies to essentially be able to modulate our load in accordance with the rest of the community that's using that utility. All of these things are currently and in future will play a big role in terms of like the power and energy efficiency aspect. Cooling as well. I think Partha this morning mentioned PUE and the effects of cooling on it. I think with microfluidics being the very realistic option in near future, we might be able to sort of get a lot of efficiency out of that. The other bookends that I want to talk about, which might sound like a broken record after my talk, is to make things a little more declarative, right? So I don't think that if you ask the user, do you want good accuracy, the answer is always going to be yes. So we really need to do more things under the hood and be able to choose the model that needs to run this particular query rather than leave it to the customer, because if we just look at the order of effect that this would have in energy efficiency, like running a small model versus large model is like a straight up 50x energy efficiency gain. So yeah, we need more and more solutions in that space.
So I want to share some thoughts on the following question, right? It's systems architect or researcher from architect, and what do I do with the head of AI? Right? And I think the simple answer, again, I'm not saying anything new yet, probably, is co-design, right? We all know co-design is not an academic word anymore. But one aspect of co-design is that we know how to understand workloads and applications, their characteristics, and maybe design software stacks and hardware architectures that are optimized for that. And that is super important, and of course, we keep doing that, no doubt. But there's another aspect of co-design that I'm particularly excited about, which is how do we take ideas that we use every day in systems architectures and put them back into algorithms. So the systems people are not just defining what runs or sort of how things run, but actually what runs as well. To a certain extent, we're already doing that, right? And I'll give you very concrete examples. Think about KV cache or prefix cache, right? Caching is a very simple fundamental concept we've used in architecture systems a lot of times, and now we see that to avoid recomputation in LLMs. Speculative decoding is another one, right? Speculation is something we know in architecture how to do very well, but now we are actually changing the way algorithm works, the way LLM runs that way, or paging and page attention. There are lots of examples like that, but I actually think that this is just the tip of the iceberg. There are many, many open opportunities that we can take on, which is to say that how can we take ideas from systems and architecture that we use every day and inform algorithm design.
I'm not sure how much you want to have after the great list of items over here, so it's tough to last. But I guess the thing I'll share is that, the argument about heterogeneity is a very interesting one for me, because when I went to grad school a very long time ago, that was all the computer architecture being defined that, right? There's like dark silicon's going to happen, we're going to have to go build all these like special accelerators, et cetera, et cetera, et cetera. And it seems like it was never going to take off. Anyone you ever spoke to in the industry will be like, hey, this is never going to go anywhere because it's way too complicated to manage and run at scale. I think interestingly, this time with AI, it's actually different for a few reasons. One is it's actually beneficial in the ways that are very important to AI. So things like energy efficiency. No one's actually ever cared about energy efficiency before. They always tell you about it, but the reality is, they can if you can get more performance, whatever, it's not been like a primary consideration for people. I think with AI, it's actually becoming a primary consideration because of the shortages on how much power is available to just get deployed. A lot of the people we work with literally ask us, like, what is the efficiency per megawatt? It's like not a metric that I really considered before, because I'm like, don't you care about how much it costs? It's like, energy is the critical bottleneck. So I think that part of it actually drives you towards building more energy efficient architectures. And if you go back to all the computer architecture things, one of the ways to get better energy efficiency is to use like the right tools for the right job, which ultimately means you'll start thinking about how to do your computation better and start optimizing for specific pieces of the workload. And I think the third thing you end up with is that even within the realm of like executing a single model, there's several different phases and things that optimize differently, which can give you like fundamentally different performance and energy efficiency things if you use different hardware for it, or segment it out differently. So I think this time it's different, and you're actually going to start seeing a lot more heterogeneity. It's something you're already seeing, like people starting to talk about how we're deploying this. It'll probably happen a lot slower than anybody would want to, because the challenges range all the way from the physical deployment of the systems, how you're going to cool systems that have never been cooled together. Like we're working on these things. I can tell you, like sometimes even deploying two liquid cool systems is different because they both use like different water temperatures, have different cooling requirements. And it's problems that like we as like computer scientists are not like very used to thinking about. But when you start like actually deploying these systems, you start running into all these issues. So there's challenges all the way from the physical layer all the way to the application side where you're trying to interface with the software. So there's a lot of work to be done. But I think right now we're kind of in the realm where computing is getting redefined. And as with any big wave, I know everyone is like, oh, AI is a big wave, but it's more than just AI. We're actually just fundamentally changing how software is written in the future and how it's going to work. And we're actually also rebuilding the entire substrate that it runs on.
Right. Thank you all. So let's tee off of that last point. As part of this workshop over the last 7 or 8 years, we have seen interest in energy efficiency go through cycles. And right now we are at a high cycle. Like you rightly said, people are realizing that energy efficiency is one of the key metrics in large-scale deployments as well. So when we look at it more holistically at the whole infrastructure, what are some of the metrics or some of the invariants of the stack that don't change with the evolution of workloads, and some of the other ones which will very likely be more fluid? Anybody?
What do you mean by metrics?
Well, cost, for example, is not going to be something that changes, right? Everybody is going to be cost conscious. Whereas latency might be something that people are willing to make a trade-off on. So examples of those in a more general sense for AI computing.
Okay, so I guess I have some thoughts on this. So one of the ways I think about this is that when people use AI, there's actually a few different paradigms that you fit into, right? And one of the ways I think about like any AI system is like a data flow system. And the most extreme case of this is that the human is actually part of the data flow loop, right? And you're actually responsible for making all the decisions. And to some degree,
to be the bottleneck, or rather, you want to be the bottleneck because you're the one whose time is critical, and then you want the machine to be as fast as possible. So I think that's going to give you a particular realm where you want to make things as interactive as possible because you don't want to slow yourself over, right? Like if I have a new database idea or something, I want to instantly get the answer. Right? I'd rather not wait for it to write over the next day and get the results. Then I think the next realm is kind of this like agentic realm where basically agents are interacting with each other. And over there, you actually, I think counterintuitively, you actually care about, you actually do care about performance because you care about the task latency that they're getting done. And agents can talk to each other very quickly, so you might as well make that more efficient. Now, there's obviously some room over there to like innovate on how these things can talk to each other to actually improve efficiency. But you do care about latency, but maybe not as much as like a live interaction with humans. And kind of the third place to think about is just like a long-running task. I think those all have very different like KPIs and will require different optimizations. And potentially you could layer this onto a similar system that can then optimize at different levels based on what hardware you have in your system.
Anyone else on the panel? Anything to add? I know, Esha, you talked about trading of accuracy, which was a bit of an unheard of thing before, but now people are willing to make trade-offs even on accuracy. Are there other such areas where trade-offs which were previously not quite practical appear as low-hanging fruits in the new world?
Yeah, I guess like latency is definitely one that really, I don't think that we have explicit cost tiers for performance at an API level ever before, but now we're starting to see that happen for even API level, right? So like there were tons of research papers that have been written wanting this interface, and now this is finally becoming a reality. So that allows us to do a lot of interesting optimizations. You use different type of hardware under the hood where you're only using like the very fast decoders where you need that kind of performance. Right? So I think that is definitely one where the interface with the customer is changing. And then again, sort of a lot of stuff is becoming, I think the stack of what a cloud provider can control is increasing. So I talked about accuracy in terms of model, but like I said in the talk as well, right? It's really the whole workflow, if you think about it. So it's all the way from the orchestrator, planner, LLM to what exactly happens, and yeah, all of it is under the control of the provider, essentially. Of course, like it depends on what service you're running, but like if you're running OpenAI on Azure, then Azure does not have full visibility into the stack. But if you're running like a data Copilot or just Copilot, it's really like the full stack. That's the way to go for optimization. So I think that is a very different
So pretty much every talk today, except perhaps Brandon's, talked about heterogeneity. And I know, Joseph, you have some opinion about what kind of infrastructure is needed. So are there some initiatives needed? You mentioned academia has a role to play. But in order to allow interoperability to be achievable in a heterogeneous world, what are the kind of initiatives are needed? Is it standardization, new libraries, new interfaces? What is it that we should be aiming for as a community?
Well, you know, there has been in the past efforts to have consortiums that deal with heterogeneity. I'm not sure how far they go. This time, however, I think it's going to be an important problem in that different startups and different companies will come up with accelerators. And there'll be intense competition to use them potentially in the same package, chiplets from different companies. How do we make sure that they can operate together, right? So, you know, there's an effort in the communication protocols, the connection between the chiplets that's going on. I suspect there'll be more and more efforts on trying to make sure that the APs are consistent with each other. So we will see more of that.
Anyone else on the panel wants to add?
Yeah, if you of this and talk about the issue of mental hardware, the other place where you can sort of see people come together is talking about the videos, right? So we sort of have certain sort of security place, security because of the idea, models of, for example, without doing people equal disaggregation or disaggregation in the layer. Every accelerator might have their own thoughts about the metadata, how they want it in the meeting, or how they want it. And it might seem trivial to say, okay, I've done this here, I've done that there, but if the sort of memory fragments that we expect out of different formats, you suddenly add a single transfer operation and all of them are replaced. So some kind of sort of layout that is more defined, uniformly defined across all aspects would be quite useful. I think right now the reason that does not happen is because everybody is developing independently, everybody is thinking about this equivalent provider, and then everybody shows up for that or most definitely at that point for that point. Let's go beyond simple cases of the
Actually, like that's an interesting point you brought up, Ramesh, right? Like it's almost as if like every hardware startup chose their own interface because that became their mode pretty much. So do you really think that there is room for like a single interface across all of these neo hardware, like not the different hardware that NVIDIA itself is producing? Of course, they have an interface across those, but like, do you really think that there's enough meat in the game for like all the startups to kind of adhere to a single type of
Yeah, so I think sometimes the choices are a function of this engineering taking decision because they have to move forward, right? And we can consider that they have to operate. Sometimes these decisions are specifically about one, but I think right now a lot of these decisions are about ad hoc. If you even simple things, if you choose where versus SGI, things change in terms of how you're accepting memory layouts and how the metadata looks like. So all of these things are just, a lot of these are just engineering decisions taken in chaos. There may be a more aspect I haven't really thought about this, but my hope is that we can have it. Please, right now there is a lot of incentive for those.
Yeah, I can add to that. So you probably remember a few years ago, people were maybe like 6, 7 years ago, a lot of startups come out of Apple, and everyone was building essentially their own software stack to run this solution, and they're all very diverse. And it seems to be further direction and really thought of moving the market. It was clear within 2 years that it's not going to happen, so you need to find some level of uniformity, and things emerged, right? Because people not going to leave without that solution in the vacuum, and they get VLM, and they get SGLN, and those are Python. So we get part of the stack that they need for. And like it or not, that all the startups and non-startup players all have to make that part of your business decision and engineering decision. We now hopefully can go beyond that and go into kernels and try to get some, maybe not an API, but at least some programming model that it makes things read so you read. Even for single companies, NVIDIA where it's in, it's like every chip is changing quite substantially. Programming model changes, and just even writing a single kernel from Thakker to Blackwell to Rubin is a very challenging task. It's not sustainable. So we need some mechanism there, and the chip, it's not even between the chip, within a single chip is already a lot of engineering, right? And it's only going to get happening more and more. So we definitely need some level of abstraction there that becomes uniform for people's software.
I just want to also add sort of to the interfacing that's needed. It's not just at the software level. I'll just kind of give an example. So in OCP, which is the Open Compute project, where all the hyperscalers come together to try and define the data center level interfaces. There was this motion, right, where we all sort of agreed that 30C lot, right? Because that requires our chillers to run at a much more efficient point. But that then creates this, again, heterogeneity in the cooling that you need to create in the same data center where you want to put different types of hardware. So yeah, the impact of heterogeneity and latencies is really very cross-stack.
I know one thing I want to add about this heterogeneity angle is that I do have some concerns that all the heterogeneous systems are actually becoming one of things homogeneous, where it's basically here it says, homogeneous like, NVIDIA system or homogeneous AMD system. That's actually internally very heterogeneous. Because part of the problem with all these AI workloads is there's so much dependency on bridging some of the layers of abstraction to get performance that even if you take a look at a lot of the accelerator companies, like they're like, hey, we're Ethernet compatible, but we're sort of Ethernet compatible, right? And when you start hearing stuff like that, interoperability gets like really, really difficult because they've made sure that their chips work with their other chips, but they haven't made sure that their chips work with anyone else's chips. And I think things like Ethernet and everything move really slow, and everyone's doing this because they actually want to get performance, right? They're trying to eliminate the parts of the stack that are actually ruining their performance. But ultimately, it's setting up the industry to a point where everyone will just start replacing all the standard interfaces. And I don't know if they'll do it because it's a moat, but they'll do it because they need to do it because of performance. And then that in itself will become a moat, which will make it very hard to get out.
One last thing, I guess, I feel a lot of this, we can talk about unifying things and so on, but sometimes that might actually go against the business model of the company. Right? So then the question is, given that the economic interest that a company has, whether it's NVIDIA or anybody else, right? Where is the right balance that lies so that people or as a community can have a common set of rules without actually taking the economic interest? And I don't know the good answer to that.
Thanks. Well, the gate to the walled garden for one is an entry point for the other. Right? Along those lines, we've seen emergence of architectures, as was previously noted. There is an appetite in the community in trying out exotic architectures. Not all of them fall into the same spectrum of exoticness, but we have chips which are basically burned down LLMs into the silicon, each model requiring a different tape out. Neuromorphic designs, in-memory, near-memory, analog computing. When we look at the pros and cons of each other, and we kind of try to relate it back to what are the invariants of the computing stack, how do we architect solutions which not only have the performance benefits that we can reap today, but they also maintain the longevity, that they won't be obsolete next year when the model changes. Anyone?
I guess one lesson I learned by running not just an academic research lab, but running a company is that the customers that have demands and you want to be successful to satisfy those demands. So the first thing that we like to do is we like to try different ideas, but there is a trend that you can see that happens in the undeniable trend. So for example, the number of models that keep growing, the ratios of models that keep growing, things are not just critical, yes, everyone's using attention and transformers, but it's actually quite diverse even under the hood. So if that happens, some of those ideas might be more practical or less practical, and I think that's the reality we need to face. It doesn't mean that any particular idea is bad. Let's say FC and the SFU startup that tried to really put like llama model into the silicon, and they were showing amazing on paper numbers improvements you can get, but like I look at it and say, nobody's already using llama, but by the time you ship this thing, nobody needs it, right? So you need to make sure that any ideas you try to deploy goes versus that check of reality against what people will use. And this is not happening not only in academia, it's dependent in the industry, because people who build silicon are not too happy to talk to customers. And they think, oh, well, just like whatever I see right now is a good representative sample that was going to be 3 years from now. That's actually very fast moving fields, right? So we shouldn't be restricted in trying out different ideas, but that reality check is very important, especially if you want to commercialize.
Yeah, so I agree, because we are in a in an era of discontinuity. Right? There's a lot of activity, and people are looking at all sorts of things. Right? Exhibition in memory or whatnot, wafer scale and all that. Some of them will survive, others will not. What be nice is it was not so expensive to build each of these things. Somehow we have a way of experimenting that doesn't require the teams of engineers working for a long time. One hopes that AI is going to help us with this, right? If we came out with some automation for all this, it would be much easier to experiment with many agents. In the meantime, we start with what we have.
One key challenge I see is that, I think it's important to actually agree upon a common set of metrics that are really important when you are a customer or something, right? So you see a lot of the ideas that, or many papers that are kind of like too exhaustive, and they will come up with their own set of metrics, and they'll show that, we get a GPU metrics X. And that might or might not be, the metric that the end user actually cares about, or something that can sell on the market. So I think, and of course, we have metrics like improvements per second, and accuracy, and power, and all of that, right? But, are there common set of metrics, or how can we actually weigh between these metrics to actually understand a full story? Is an important question to answer.
I want to add one thing to this. This is also another area that reminds me of grad school again, because when I was in grad school, I wrote a ton of English. I was like hardware, software, co-design work, and kind of build a very, very application-specific test for various tasks, right? And I think it comes back to like, what is the marginal benefit of doing this versus keeping some level of flexibility? Because as Joseph mentioned, we're in this space of discontinuity right now where things are changing very, very rapidly. And I think it's extremely risky from a business perspective to invest in something that you need to run for the next 3 to 5 years if it can only run like 1 or 2 models. And to be fair, like if you take a look at a lot of the silicon companies right now, they actually started in the age of CNNs. And if you take a look at them as they ported themselves to LLMs, they went from very high efficiency to not so great efficiency, and ended up being not much better, or maybe even worse than running this on a GPU. So I think trying to optimize architectures for like specific instructions and things, I actually don't know if it's that important. I think the biggest benefit you're going to get is actually trying to figure out what the proper memory systems and what the trade-offs are over there, so that you can capture most of the benefits of moving data around. I think that's where most of the cost and performance is lost.
I am not an expert in FPGAs, but I just want to put it out there, given what Joseph said. I think one of the biggest challenges with FPGAs in the past in production has been the cycle of reprogramming it and just the software stack that's available for it. And I wonder if like AI can play a role in sort of increasing the frequency of that loop to an extent that they become useful.
I wanted to touch upon something, Janity, you said a bit ago, that every startup a while ago, they had their own software stack at the entry point, and then PyTorch, VLLM, and SGLang, they came and kind of put a standardization on top of it, and we have more to do there. My concern is that they're still built upon the fundamental assumptions of a GPU architecture underneath. For example, they assume a unified memory model. Not everybody will have the same. In fact, there is a conflict of optimizations that you cannot get a certain kind of bandwidth advantage if you have a unified addressing or unified memory model. So not only do we need to standardize, but we also need to detach from some of the prior assumptions about the computing models. What's your view on that?
I would say that the LLM is all open source, right? And there's a reason why one appeared and another appeared. If certain assumptions made there were wrong, and it turns out they're critical to address other things, either they had to go through a cycle of evolution, or the new product will appear in the open source market and will address that. That's unavoidable. The question is how critical it is, how big of an issue it is, because there's a lot of pain, there's always a trade-off between general and specialization, how big of an issue it is, right? Whether it can be addressed or not. Like a lot of lot of the things done were originally supporting certain things that spectrum coding, but we were able to extend that, right? One team has started that spectrum coding supporting the LLM. It was extended. At some point, it turns out architecturally, there are wrong decisions that doesn't allow us to extend it to something new. It's just it's an evolution of software. Luckily, software is in principle much easier to try out in years, and we're using now hopefully we're using AI agents. Silicon is still harder to try out 8 years, and there's a side that it would be great to to use it PGAs and be more programmable. Debugging got a little bit straight. Say that if an agent is going to make a mistake, I don't want to be part of that one. So it's just really tricky. But anyway, I think that's what the normal thing would happen. We think that we critically need to have unified memories or short primitive with the LLM and species. First of all, we tell them to see how they can extend it. If they can, something else will emerge. Right? We do things that keep being emerged. Like for reinforcement learning, there was no good product available, something that grow happen, and everyone is using right now, so indeed it has to support it. Because it becomes a de facto standard, right? And that's the most popular. Yeah, I think that also the compelling argument you are making perhaps is that is what I mentioned. Whenever students have a culture was Sambanova to all the one thing that we realized is Zurich was not good for giant TV graphs. Right? It was still a really good so for AP and Sambanova and power processing, and it's a nice assumption that your sampling operator is different from the rest of the graph. And how the process because you have a communication with your host and device drops out 200 at that point, when you start having these conversations, it's really hard to have these conversations because of them, speed was not still there. Now people care about speed, so when you have these conversations, you have those conversations. Whenever they started, they had that from the speed of at least supporting speed for so I do think once you make a very case and put up a Zillion now, they are very much willing to be confident about the in fact, to keep actively asking for feedback for how do I change my interfaces and all of these things. So once you make comparing argument, open source is willing to do, but it takes a while to make a comparing argument. So there is going to be a pain point in terms of making your case as to why you need to do it and you need to do things very deep.
I think maybe one thing I'd like to add to that is, there's also another layer of interface. Actually, I actually think there's 2 layers of interface to think about. The first thing is the interface for the LLM itself, which is basically the OpenAI API interface, right? And that's also what SG language is. So to some degree, the language behind complexity behind that notion there is. And people basically have to forfeit that layer. The other thing I'd like to add is, as with any open source project, right, you can either use pieces of it, you can use all of it, or you can use none of it. And everyone will make engineering trade-offs based on what the right thing to do is, and new frameworks can emerge, right? Like, it wasn't that long ago that TensorFlow was going to be the only framework that will AI, right? And then PyTorch came along and became that thing. And PyTorch itself has actually evolved a lot since the early days, and that's why it stayed relevant. So the question really will be is how much can they evolve to the new weeks, versus how much people view extending it as a separate project or eventually forking it off into a different project as a project. The last thing I want to add is, I actually think one of the complexities of dealing with multiple different hardware is that there's no easy way to write kernel or any kind of compute graph across all these different systems. And even if you take a look at something like VLM, they basically end up having n implementations, right, with their pieces of hardware. And at some point, it's not really trackable, right? And it's literally n different pieces of hardware, right? Like using the kernels on Hopper does not work on Blackwell unless you don't care about performance. And presumably, you do, so you're going to keep rewriting all these kernels and spend all your effort doing that. So there has to be some scheme that allow you to easily do this. Otherwise, you're going to be in this n by n matrix.
Anyone else? Okay. We talked about improving the energy infrastructure or the infrastructure for running AI. But we also are looking at how AI is influencing the whole infrastructure design, whether it is chip design, software design, kernel generation, optimizing a closed loop system. So as the capability of these systems improves, what advice would you give to someone who's, say, early in their career looking for a job which is not going to vanish in 2 years? How to better utilize themselves, how to equip themselves with the ability to use these tools to become more efficient engineers rather than getting on the path of obsolescence?
I'll start with this. So I guess to some degree, I'm actually a huge believer in Jones paradox, where the easier the stuff gets, the more it'll become, or cheaper it gets, the more popular it'll become. So I'm one of those people who doesn't actually think software engineering is going to go away. Now, I view software engineering as a different exercise than just writing code. If you take a look at most like senior engineers, you actually probably spend very little time, relatively speaking, writing code. We're just figuring out what to do, what problems is actually important to solve, and coming up with a framework for how to solve that problem. And while AI will probably continue to assist and maybe even make some of these decisions, we're ultimately building systems for ourselves, and we probably will need to understand what trade-offs to make. The second aspect I would say for people who are just starting this is actually to understand how this stuff works. There's a tendency when you use LLMs to be like, oh, I understand how this code is being written. And I kind of view this as like, the times when you're in lecture, having a math professor go through solving math problems with you, and you go home and you're like, oh, it was easy. I learned this like 3 hours ago, and you try to do it yourself, and it's actually very difficult. So I think actually understanding like how to write the code, do the stuff is very important because that helps you figure out how to make the system better. Not necessarily just for like, it's not just about getting the task done faster. It's like understanding the problem so you can actually frame the problem.
The students in the room just gave a sigh of relief. Thank you.
Well, so I think that the students who are here are very ambitious and they know what they want. They are taking courses and they are learning about this technology because they know something will come. The question is more for the masses, right? For the undergraduates who are starting in state schools, many, what do you teach? So that's something that we still don't know what is the right way. Certainly teach them the fundamentals and also the use of this technology. But things change so quickly that it's going to be an iterative process. I'm not worried about the students who are
So I guess trigger warning, I'm going to compare humans and AI, but it's the way I feel about it is sort of how when you come to an advisor or professor stage, you've gone through the PhD journey yourself and you've learned how to build systems, and then you become an advisor and you have some students working on different problems, and you're not in the nitty-gritty of building systems anymore, but you're still advising them. And I feel like that's how the education in agentic work needs to be, where you still understand how the systems are built, but then you also are good at the advising the agents aspect and using the agent aspect.
Okay, one fun question before we open it up to the general audience. So we talked about energy being a constraint, cooling being a constraint, space being a constraint. Well, space meaning real estate. Why not send the data centers to space? Right? Unlimited energy, unlimited cooling, end of the world, end of the problem, right?
It's not unlimited cooling. If you build a 1 megawatt data center, 1 megawatt colo in the data center, in the space, the amount of area that you need for the radiator to actually get that heat out is really large, right? Because yeah.
Sure. So, well, that was a leading line, but at what point does the technology actually start to get practical? That's the more important question. So it may not be solve everything, but is it actually part of the mix of solutions?
I think before that happens, you'll need a serious amount of robotics to be able to do all these things automatically, right? Because otherwise, who's going to go maintain it? Your maintenance missions are going to turn into millions of dollars of work working in a zero gravity environment. And not to mention, like, I think the entire cooling thing itself, like, this makes good PR, but I'm not sure it makes good engineering sense.
Anyone else? All right, let's open it up to the floor. Any questions from the audience?
So nowadays, the way a lot of people are kind of building AI applications and use cases, it's kind of equivalent to in CPU world, you have IPC instructions as a unit. Now they're taking token as a unit. Do you think this is tokenomics is the right way to look at it? This is the more some model? Because what if the two different models are generating vastly different number of tokens, the usefulness of the token? We saw that ChatGPT many times says please and thank you, and those are wasteless. They cost a lot of money. And my personal experience is ChatGPT to provide a prompt, it tries to scale itself, it's not helpful. And Robert basically on the other end says directly goes to the bottom line is if you're spending too much on token. So to think about what is that really, and that ties to a little bit of resource topic. Yeah, user, they should not be allowing to, we should not be allowing them to say what accuracy they want, so long as it helps their use case, so that it returns ROI. And I just feel like this tokenomics has taken it too far, because as a company, I can charge you very cheap token, but I can generate 10 times more token. And basically, it's like a Bitcoin mining at that point. So how do we think about from the use case point of view? What's your thought?
So this is an important part that will increase the efficiency of the system if we focus on the important tokens. So we need new ways of understanding this problem. Not all the tokens are equally important, right? Think about grouping the tokens in important clusters. Other things are less important, and build the algorithm as this. I think this is another frontier to improve the efficiency of analysis.
Yeah, I think the interface has to be something relating to whether the task is done or not, or the accuracy was. It has to be the quality rather than the tokens, because otherwise, you're right, it will always be at odds with what the company is wanting to do, right? It's a product cost. Although I do want to say that most of the, like, yes, that's true for API usage, right? Subscription costs no longer. So when it comes to subscription costs, it's still every company is trying to reduce the cost.
I think maybe one thing I want to add is I actually do agree that the tokens or whatever is like very similar to looking at like IPC, where it's basically not a useful metric because you don't actually know like how many instructions you need to get work done. And I actually like this framing by I think Chris Racer at Stanford, where they basically have like intelligence from what, and it's basically trying to take a look at like solving a bunch of tasks and seeing how much energy it takes you or how much power it'll take you to like run through those things. I think the challenge over there is that just like the CPU people build spec and all those things to measure performance, and then everyone then builds CPUs to gain that performance, you'll probably see that much more on the AI side because you'll be able to then start training models for specific things. So it'll have to be something that keeps evolving and has new data sets you can keep measuring the intelligence. But ultimately, I think it will lead to some task completion and how much energy did it take you to complete that task. Or dollars, whichever way.
One of the reasons people still look at tokens as a metric for is because right now people don't really know there are two topics. One is from a product point of view, most people don't know how to sort of price outcome-based products. It's new for AI world, being a profile is new for us, right? So we don't really know how much we value, right? So how much I really, I don't know, so I charge token adoption now. We like to understand. So at some point people are going to figure that out. At some point, pricing from an external point of view for a user is going to change from token-based to outcome-based. But as a data center provider, you're always going to be token is what we look at to understand how much you are utilizing your hardware and how much you're going to take up. Right? So tokens will move from being sort of public facing to maybe a bit more sort of behind the scenes for the data center. And what we start seeing is what we're going to do. You see that change now, like cloud code being priced at whatever $200 or whatever. I'm not sure that's the right price right now, like you can really get any cost, but eventually they'll figure out what that is, how the price is.
or not. I have a very maybe weird question, but my question is, as architects and systems designers, are we at some points also over provisioning? Because one thing we're losing out is reuse. Back in the day, we would write a book, it would be a blog post, that would be a common source of knowledge which is ranked and received by users. But with LLM inputs, there are billions of people who might be actually asking similar or the same problem or same question, and it's a independent inference task, and it is a lot of kind of duplicated computation, and we are provisioning for high throughput and all of that, but we are losing out on videos. So I know in virtualized environments we cannot really share cross-user content and so forth, but can we think of how LLMs will progress? Like, how can we gain this aspect of just common knowledge that we probably can avoid computation?
So I think reuse is already incorporated in a lot of politics of the set of services. Prompt caching is one of them. A lot of sort of queries being reused, and we use sort of hierarchy reuse also. So if you're going to use data set, you're going to make one sort of within a state, whatever. So reuse is something that most these cloud vendors are talking about using money. Do they get very granular or I don't know what kind of expertise is very level I can see what that's why you see and you look at the same case if you get your contract as I would say you actually save on money and a lot of vendors encourage it.
I want to say something similar. So this is not really a problem, but Google has to face the same problems that search, right? People do search online, and there's many layers of caching hierarchy where they make sure they don't send the same requests on where the queue requests actually go deeper into the hierarchy and search the actual content. I'm pretty sure it's either done or partially done or will be done because that's an important course of the concern that needs to be addressed. Where exactly the hierarchy will be how we handle the regional aspects, language aspects, and some other things, but it's definitely will be how that at least some of that is already done.
I think there is a tension between reuse and security. So we will see this appearing as AI systems become more complicated with more layers. There will be a push to reuse more, say, users, and then there's a security aspect.
So add to that, I think there is a paper from Stanford about they actually tried to reverse engineer. It was Mario was maybe different, but for Anthropic as well as OpenAI, how does prefix caching help you uncover prompts from other users? So you might want to check it out.
Hi, my name is Satyam. I'm from India. And when I was a young engineer, I got lucky and I'm lucky to get senior architect review code line by line. It was painful, but all that is learning. And now I'm helping lead my team. I have a question that I didn't possibly answer. Before, people used to do PRs line by line, nitpick on everything. Now it's impossible. Your senior people in the teams are essentially becoming a bottleneck for reviewing work for like the more junior engineers. And as Esha mentioned, you start out being mentored, and then you kind of like start mentoring the models or the agents. How do young engineers, how do young people like should, in this day and age, learn when tokens achieve amount of work is just enormous. Senior people have much less time to review work. Feedback is less. How does all of that work? How do we keep young people, in the system, in the pipeline, economy, learning, growing, and just, not getting swamped by useless LLM outputs?
In the last year, been multiple different panels and not just science only, and this question comes up almost every single time, one form or another, like what we should do with our kids, we should teach them in the AI era in different forms. So think there's no like easy answer to this obviously, but like in the times of big revolution or big crisis, there is problems but also great opportunities. So everyone should be open-minded and looking at this not like a killer for their future job, but more like a big amplifier for their own skill set. And always ask the very, very basic questions. What are the things that I'm trying to do can be automated, and what is the creative parts that I need to make me better and better at, right? So yes, like you cannot review every single line. In fact, like I recently, use a lot of code myself and talk to friends about it. There is no way to review this line of code. Most of this programming languages code is using, I don't even know, right? And I never use this technology, but nevertheless, I can give you like treat it more like a manager in the sense that you tell it what it needs to achieve, what are the right metric, what is the proper guidelines and unit tests it should generate, and with that proper attitude, actually convert it. And you check the critical parts of the code, but the rest things you eventually maybe be able to check the critical things with formal verification, right? Critical. But otherwise, you need to accept this new reality. I don't think it will be able to verify every line of code. It doesn't replace the formal education you have, as but we need to keep being focused on fundamentals and educating people on how to use this tool. But I think that would be, but education needs to change dramatically. Right? There is no question about it. It cannot stay the way it was for many generations.
I think just the PR review process part of your question, I think that we are already going in the direction. So to set some context here, like bugs are automated, bug generation is automated these days in most companies. So a lot of bugs are being generated by AI, sort of creating new tests and running them. But adding new code is still bottleneck than humans today. And so this, I've talked to at least like two other friends at two other companies, and it's the same thing everywhere, right? Where essentially production software engineers are complaining about how frequent the bug generation is. And so I think two things need to happen for that. One, the bug generation should be more sort of filtered. So instead of having the AI just generate bug for each part of the code, it needs to have like a realistic trace that can trigger that particular bug. So that's filtering the bugs themselves, and then the PR process is the review process as well. I think we need to use more AI there as well. Okay? So instead of having everybody sort of read every line of code that is generated by AI, a Q&A process, which is again similar to like this advisor PhD student kind of relationship. The advisor is not going to go through and read the code that the student has written, but it's more of a Q&A process. How did you do this? How did you do that? Right? And that's where again, like the systems building knowledge will come into play, which is you have to identify the critical places where things can go wrong and make sure that you ask for that. And then for the most important critical use cases, like I said, it has to be formal verification, which is now way cheaper than it used to be, right? Because we don't need PhDs to formal verification.
No, I was going to say last, maybe this is funny, but I mean, you're talking about a senior engineer going through code, right? And that person can also be built by AI. And I don't know if it's already done, but I don't see that as a very far-fetched goal. But if you want to train an AI model to actually just check some specific metrics of code or whatever, I think it's not far-fetched.
Yeah, I mean, most coding agents already do have like a coder verifier loop under the hood, so some of that is already happening. But I think as a community, we're not past that barrier of letting AI-generated code directly into production.
I think coding was an example. I think the question is more about how do you keep the junior engineers who are starting now get to that place when the path is so difficult because it's so easy to do the low-level work. But your points are well made. We are a few minutes over. Let's thank our panel for their wisdom and to the audience for participating.
Oh,
no, just a small. Can you hold on?
So we'll get started with our next invited talk by Professor Charith Mendis. Dr. Mendis is an assistant professor at the Department of Computer Science at University of Illinois Urbana-Champaign. His research focuses on the intersection of compilers, computer architecture, and machine learning, with a particular emphasis on using data-driven methods to automate code optimization for modern high-performance hardware. Dr. Mendis has earned his PhD from MIT CSAIL, where he pioneered techniques for learned compiler heuristics. His work is frequently featured in top-tier venues, and he's a leading voice in developing robust toolchains required for next-generation AI accelerators and solutions.
I'm not sure why it's coming. Okay, so it's very late, but let's go ahead. So I'm Charith Mendis, and I'm a professor at University of Illinois, and I'll be talking about how to build agile and evolvable software targeting rapidly evolving accelerated designs. And as you may know, deep learning has instigated a lot of research in both software as well as in hardware. From the software side, there's many training and inference systems being built, from systems like SGLang, VLLM, to quantization libraries like Google Quakes, to machine learning compilers such as TVM, XLA, and so on. And in the hardware landscape as well, there's been a lot of research being done. There have been very successful chip designs such as Google TPU, Amazon Trainium, IBM Spire, to early stage chip startups like Sambanova, Furiosa AI, D-Matrix, and so on. And also the academic research community has been very active. They have been coming up with new accelerator designs, each micro and ISCA. But however, we notice a subtle disconnect between the software research community and the hardware research community. Software research community mainly perform innovations and target and evaluate them on commodity hardware platforms such as CPUs and GPUs. And only a handful of papers from the software research community actually evaluate on new accelerator designs. And this is true in generality. Like if you look at the latest ASPLOS conferences, 2024 and 2025, there's a big discrepancy in the number of papers being published by the software research community targeting CPUs and GPUs versus the AI accelerators. And in spite of this, however, the hardware research community keeps on coming up with new accelerator designs. So clearly there's a disconnect between the software research community and the hardware research community. And this is where I'm trying to bridge this gap. So more nuancedly, I want to ask the question, how do you integrate new hardware accelerators to existing software development ecosystems? To answer this question, we need to first find the reasons behind this disconnect. And to do that, I'm going to ask three simple questions that anybody would ask if you are developing software. First one is, can you write custom software targeting these AI accelerators? So for comparison purposes, I have included the other platforms as well, like CPUs and GPUs. So if you consider CPUs and GPUs, the answer is yes, because we have a well-documented hardware-software interface, be it ISA, virtual ISA, or so on. But for commercial accelerators, there is no public low-level ISA available. And we may have some kernel-level programming interface sometimes. And for early-stage chip startups and academic accelerators, most of the time we do not have well-documented hardware-software interfaces. So because of these low-level developers as well as compiler designers cannot target these devices. They don't have an interface. The second thing is, say that you can write the software for the targeting these devices. You need to ascertain that it's correct. So is there a good correctness testing infrastructures available? For chips, for platforms with physical chips, the answer is inherently yes, because you can run it on the chip itself and get an answer back.
But for early stage chip startups as well as academic accelerators, you will have to rely on simulations. So once the RTL is developed, you may have access to functional simulator. But what we notice is most of the time, pre-silicon designs don't have fast and scalable test oracles. And this also acts as an entry barrier for software researchers. The third question is actually targeted at high-level developers, like AI researchers. Can you program these chips, or can you write program at high-level programming languages and still target these chips? For CPUs and GPUs, there is a well-oiled infrastructure that's maintained in open source. For commercial accelerators, people employ hundreds of compiler engineers to actually build these compilation platforms where you can actually write code in JAX and PyTorch and still target these devices. But for early stage chip startups and academic accelerators, mostly you will have kernel programming libraries. You cannot write like a PyTorch level model and in generality assume it to be compiled down into code. And this actually acts as an entry barrier for AI researchers who want to develop new models. It's one thing that whether you can run existing models, but for AI researchers, there's like 10,000 odd papers being published in AI conferences, so you want to develop new models. So with all of these problems, we already know how to solve it in the traditional way. Say that you have a new accelerator concept, you first design ISA or a hardware software abstraction, and then once the RTL is being developed, you can develop correctness testing tools like test oracles manually. And then once these correctness testing tools are there, you can manually construct the compiler backends. And you can go on doing this over and over again, and we know this works. But however, this doesn't have the necessary agility in the accelerator landscape. First, there's going to be a lot of repeated effort for each accelerator because accelerator ecosystems are siloed. Google has its own ecosystem, Amazon has its own ecosystem, and so on. There is no retargetability. And also the hardware is moving too fast. Say that you build a compiler, your next chip is already up. So your hardware is too stale. And also, in order to keep the speed, you need to be a hyperscaler where you can employ hundreds of compiler engineers. So this will act as an entry barrier for early stage chip startups. And some of them are realizing this and moving the compiler development effort to outsource companies. So with all of these problems, I suggest we need to rethink how we develop software targeting AI accelerator. It needs to be agile. So this is where the accelerator compiler toolkit ecosystem comes in. So here, rather than developing software manually, we suggest that we can automatically generate the necessary tooling that requires to develop more advanced software. So at the heart of the ACT ecosystem is an ISA definition language known as Tidal, which standardizes defining ISA semantics for a large class of tensor accelerators. And given these Tidal definitions, we have technology to automatically generate test oracles, kernel programming libraries, compiler backends, even fast transfer learn cost models. And as you can see, this automation brings agility and it requires minimal engineering effort. And most importantly, now the accelerator software ecosystem becomes as fast as the hardware. And surprisingly, some of the automatically generated tools can be orders of magnitude better than the handwritten ones. And since the compiler backends that we develop can be directly hooked into existing production level compilers such as XLA or PyTorch, we can build future research on top of it. And we already did some work like the virtual term compilation work that's going to appear pretty soon. So with this Tidal language, we have defined ISAs for very simple Google TPU version 1 accelerator, to CGRA-based accelerators, to Intel AMX, and very recently we formalized the Amazon Nikki virtual ISA. So now we can target Trainium devices for any given computational graph. It's not for 1 or 2 kernels. So here are some highlight results. With minimal engineering effort, we were able to develop compiler backends for 6 different accelerator platforms. And also the automatically generated test oracles can be up orders of magnitude faster than the handwritten versions. Both the academic tools as well as commercially released tools like AWS Trainium Nikki Simulator. And also we recently tested out our compiler backend against the Neuron XCC compiler commercially released by AWS Trainium to target their Trainium accelerator. And since we use more programming languages techniques, we can guarantee completeness So these are not AI-based techniques. These are programming languages techniques. We can guarantee completeness. So because of that, we get 2.1x better compilation coverage compared to the manually written compiler. Okay, now I'll briefly go through the various components of this ecosystem, starting out with title. So the goal of the title or the tensor accelerated ISA definition language was to precisely and concisely specify the ISA semantics of a large class of tensor accelerators. So here the word semantics is very important. Semantics is the intent of an instruction, not how it's implemented. There can be multiple microarchitectural implementations, and I like it. For us, we only want to model the intent that will be available to the software developer. And the key observation we saw was that most of the tensor accelerated ISAs can be actually modeled using high-level tensor IRs themselves. So some of these tensor IRs are like XLHLO or PyTorch A10 or what. So title has two main specifications. First one is we need to specify programmable memory units. So this is what we refer as data model. And in the title specification, these are like just tensor buffers. More correctly, these are tensors of tensors. And then we need to define operations to modify these memories. And this is modeled as a computation graph or arbitrary composition of tensor IR operators. So let's look at a very simple example. Here I show you the canonical Google TP version 1 load weights instruction. So it has many different tensor buffers, but if I focus on one, you have this FIFO buffer, 4 of them, where each base element is of 256 by 256. So this is why I said it's a tensor of tensors, because you have multi-dimensional accessing with multi-dimensional base elements, meaning you can access a single element and that single element can itself be a tensor. And in this instruction, you are essentially loading HBM values to a 2D memory. So you need to model the 1 to the 2D conversion. And that can be easily represented using this reshape operator in the XLHLOI. So this is very simple, but we can also model complex instructions like the Intel AMX dot product instruction. So here it's essentially doing matrix multiplication, but it has 7 main stages. So in order to get the semantics bitwise precise, we need to model all of this. So the title definition is a little bit complicated, but it's still loop-free and a straight line piece of code. And this is very important, right? So I said that we are going to automatically generate the compiler backends. So in order to make this problem decidable, we need to keep certain things uninterpreted. I mean, I'm not going to keep going to details on exactly why, but you can see this loop-free way of writing the semantics allows us to build like novel technology. So here some complications are that we need to model this data layout transformations, and this can be easily modeled as a reshape transpose reshape composition of tensor IR. And also you can model this bit this multi-precision arithmetic, and that can be done through this bitcast convert operator that we can find in the XLHL. It supports different quantized formats as well, so we can get bit precise results. Okay, so that's the foundation, right? Now we need to use that to automatically generate this tool. So let's look at that. So from the architect's point of view, the only thing we want is these title definitions, the instructions and their semantics written in title. And given that, we will automatically generate a title test oracle library. This is nothing but a Python wrapper around this semantic. So if you have instructions, say load weights, you will have api.load weights Python wrapper. So now the low-level programmer can go in and use these Python wrappers to develop their kernels. And here is a kernel written for the Intel AMX instruction set. For it, so the kernel is doing matrix multiplication, and it uses instructions like tile 0, tile load, dot product, and so on. And once you have written this kernel, you need to see whether it's correct. You need to simulate it, right? If you don't have the hardware, you need to simulate it. And this is where the decision of modeling every instruction as a small computation graph comes into picture. Now, in order to simulate it, either you can execute each computation graph in isolation, or you can fuse everything together into one gigantic HLO graph and give it to the XLA compiler to compile it for you. And this compilation can happen in both CPU and GPU. So the functional simulator can run either in your CPU or in the GPU. And that has effects. For instance, here we tested out these automatically generated functional simulators with both academic products as well as commercial products. Here I show you results for the compared with the Gemini Spike functional simulator. So Gemini is a UC Berkeley system for accelerator, academic accelerator, and they provide a functional simulator known as Spike. So in y-axis you have the simulation times, so lower the better, and in x-axis you have the kernel size. And this is for a simple gem kernel, right? So the Gemini Spike simulator is in blue, and tidal generated simulators were running on GPU and CPU are in both green and red respectively. And as you can see, we can get up to 5,600x performance improvement by going through our run. So rather than handwriting C++ code, if you write it as computational graphs and let the tidal automatically generate the fuse simulation, it's going to be much faster. But now the problem is like, as a software developer, I don't really care if a gem kernel runs in 0.1 milliseconds versus 100 milliseconds, right? I mean, as a software developer, it's not, you can tolerate that. But however, when you want to the difference comes when you want to simulate end-to-end models, not kernels, not operators, end-to-end models. So here we tested out one of the models supported by this Spike simulator known as integer quantized BERT model. And it took us 58 minutes to functionally simulate. So this is not RPL simulation. It's functionally simulating this model took 58 minutes. Whereas the tidal generated automatically generated functional simulators in the best case simulated this in 0.1 second. This makes a difference. Now you can build software tooling on top of this, fast testing tooling, right? You can now like write like really good fast testers to actually find out bugs in your accelerator and so on. And this is not only this kind of speed up we don't only see in academic platforms. So we recently tested it out on AWS Nikki Simulate platforms. So this is the functional simulator released for AWS Trainium platform. So we tested everything in AWS publicly available cloud, and we get up to 18.2x, 27x faster simulations. And also it's cheaper as well. So commercially, it's maybe better to just run the tidal generated simulators rather than running the handwritten AWS Nikki simulation software. And as I said, like these fast simulations allow us to uncover new bugs. We have reported many different bugs for different kernel libraries, academic as well as commercial ones, because these were not fast tested properly. And also with other projects, we inherit formal semantics for the ISA. So I'll talk about that very briefly. And also in the next part of the talk, I'm going to talk about how we can automatically generate compiler backends that can be integrated into production quality compilers on there. So if you look at the ML compilation infrastructure for tensor accelerators, most of the early stage tensor accelerators do not have good support going from TensorFlow, JAX, or PyTorch, right? And for commercial tensor accelerators with established toolchains like Google TPU, Amazon Trainium, they do have good compilation support. However, they are not retargetable. They are proprietary. You cannot take Google TPU compiler and expect it to generate Trainium code, right? So there is no LLVM for accelerators. So what we wanted to build was like, how can you unify this, right? How can you build, make compiler construction evolvable so that you can target multiple different accelerators, not just one, right? And our answer was to go towards more automated means of compiler construction. And this has a recipe, right? So if you want to generate a compiler backend, you need guarantees about correctness and you need good performance. So how do you get guarantees about correctness? The generation algorithm needs to consume some formal model of the IR that you are consuming and some formal model of the ISA. And given these two, you can now guarantee correctness. The generation algorithms can guarantee correctness if you do it correctly. And then if you have a proxy cost model, it can even generate performant code. But the problem is for tensor compilers that like PyTorch, XL8, there doesn't exist a formal model of the IR. LLVM, there exists a formal model of IR, but what's the formal model for these tensor IRs? What about ISAs? Most of these ISAs don't even exist. What about formalisms for them? And how do you generate cost models? So these are all questions we need to answer. And this creates an opportunity for us to develop novel, evolvable compiler construction methodology. And this is exactly what we did in the Act ecosystem. We filled these holes, right? We came up with the formal semantics for XLHLO, and we came up with formal semantics for different ISA specifications. And we also came up with like fast transfer learning cost models. And given this, we can automatically generate backends that can be hooked into existing production quality compilers. So this methodology is evolvable as hardware evolves because it's push button based, right? So if you have a title specification of your ISA, you get a compiler backend for free. I mean, there's one caveat: you need some data for the transfer learning cost models, but other than that, almost everything is for free. And also, since we use some of our techniques are grounded on programming languages theory, so we can actually prove that the generated compiler is correct or sound. So let me go through some of these bits and pieces very quickly. So the first work we did was formalizing the XLHLO IR, right? And we did this work in a way, we formalized it in a way that it can be used for downstream tasks. So for instance, the XLHLO IR is rank polymorphic IR, meaning it can take up tensors of arbitrary rank. So we need a formalism that can work for tensors of arbitrary rank as well. And we use that formalism to formally verify that some of the tensor rewrite rules that's used in the XLA compiler is correct. So I'm not going into detail on this work. You can take a look at the paper if you're interested. And the next is we need a formal semantics for the ISA. Here's where the decision that we took of modeling the ISA using IR operators themselves comes into picture. Because now we get a formal model of the ISA for free. Because once you have modeled the IR semantics, if you use the IR as part of your ISA semantics, then you get it for free. And given these two, then we use programming languages techniques to automatically generate the compiler backend, which I'll go through in a cartoonish manner in the next few slides. So it has two main components. One is an ISA parameterized generic compiler backend. You can think of it as like a scaffolding with a lot of holes, and then given the title specified ISA semantics, we will fill those holes using ISA specific component generation phase. And if I go a little bit deep into the ISA parameterized backend, it has two main stages. First one is the equality saturation based instruction selection phase that uses a novel intermediary known as pie graphs, and then it has a memory allocation stage based on constraint satisfaction, and both these stages are parameterized. The first one is parameterized based on rewrites, the second one is parameterized based on constraints. And these holes are filled once the title specification is given. So the first hole is filled by generating rewrites automatically that converts from IR to IR. So these are tensor graph rewrites that were already verified by the TensorWrite system. So that's how we get formal guarantees from. So the TensorWrite system already verified these rewrites, so we get guarantees as a transitive argument. And the second thing is we formulate the memory allocation problem as a constraint satisfaction problem, and that's how you get the constraint for the second piece of the puzzle. And once you concretize these holes, you get an ACT generated ISA specific backend. So how can you use this? Say that you have a title specification for your favorite accelerator, you push a button and you get a compiler backend. And you can do this for any different accelerator out there, as long as you can specify it in title. And then the good thing is these backends can be directly hooked into existing XLA compilers. So now you can program using JAX, PyTorch, rather than programming in a kernel level programming. So this is important for AI researchers because AI researchers won't be programming at low level. They want to program at a high level. So what are the properties of ACT-generated compiler backends? First thing is we can have like some theoretical guarantees that the generated compiler backends are both sound and complete. So what I mean by sound is they are provably correct. So it's not going to miscompile. The second one is tricky, like it guarantees completeness, meaning that if there exists a
lowering to the accelerator, we will definitely find it. And in other words, there will be minimal force fallback. And this has practical ramifications. So we actually tested out the act-generated compiler backend against the commercial Neuron XCC compiler that targets Tranium. And we stress tested this on thousands of kernels, not just one or two kernels, thousands of kernels. And we found out that Neuron XCC can only generate Niki code for half of the kernels. So we get almost 2.1x better compilation coverage by having the completeness guarantee. So in practically what this means is, like, say that the accelerator compiler cannot lower this or doesn't have the mechanisms to lower the code into the accelerator assembly, it will just emit RISC-V or like CPU code that can run on the host. Right? So this is always a fail stop for accelerator compilers. But that's not the best, because if there exists a lowering, we should find it, better find it, because running things on the accelerator is better. That's what it's supposed to be. And also with proper integration of cost models, we can actually generate performance code across many different kernels, not just one. And here I will show you results for the Gemini accelerator across multiple different kernels, comparing against the EXO standard library as well as Gemini standard library. Yep. So this is, so what we have developed here is the foundation for the evolvable accelerator software infrastructure. So title is the specification. You can think of it as a specification of the hardware software boundary. Given that, we have developed programming tools, automatically generated test auditors, kernel programming libraries, and so on. And we have built exploration tools. Compiler is an exploration tool that's used by AI researchers, because if you want to develop new models, you cannot rely on existing kernels or existing software build. You need to be able to develop new software that's lowerable to your hardware. And we have also shown, I didn't touch the cost model part, so I have a talk tomorrow on just on cost model. So if you're interested, you can come. So we can actually build really fast cost models as well. But not only that, this is the foundation. We can build a lot of tooling on top of that. We have done some of the work so far, building new ISAs, new specialized middle lane passes, and most of these accelerators have asynchronous units these days. So you need to build like guarantees on whether these asynchronous, where to put synchronizations and so on. And there can be a lot of bugs there. So you need to think about it. Yeah, with that, the accelerator, we have a tutorial as well as the ecosystem is mostly public now. And I would like to thank all the students who are involved in this project and the funding sources. And I would like to take any questions here.
Any questions from the audience? Okay, thanks for one. I'll ask a question. So what do you think is the performance ceiling for Tidal? And is there a point where the abstraction of the language can come in the way to squeeze the maximum performance out of it?
Right. So it's one thing I want to clarify. It's a simulation times we are talking about, right? So accelerator, the bare metal will of course be better than running on the simulator. So we observe a 10x gap between running on the bare metal and the Tidal. So I think that gap will be there, but it's much better than running the handwritten versions.
Thank you very much. The next talk will be given by Urmish Thakker. Urmish is the former head of AI at Sambanova systems, where he built and led a machine learning organization driving hardware software co-design for large-scale foundational model training and high-throughput inference on data flow architectures. His work bridges research and production, spanning pre-training, post-training, and efficient LLM inference, alongside innovations in embedded systems and hardware.
He has published at a bunch of top-tier venues like ICML, ICLR, US, Islam Micro, Supercompute, MSS, and contributed to widely adopted open source efforts and releases, data set tooling, context engineering, and
Thank you for the introduction. So thank you everybody for being here. I know we are at the tail end of the workshop, so thank you so much for still staying back. The topic for my talk today is making long context LLM inference practical. So these are case studies and algorithms that we have used during deployments for data centers and enterprises who are sort of in a spot of bother when they're doing long context LLM inference and seeing a lot of money being burned serving LLM traffic for long context inference. This work is kind of a lot of work sort of been done jointly with folks from Sambanova Systems, but also a company that I advise, CodeThink.ai. Right, so a background. So why am I talking about long context inference? So this is a snapshot that I've taken from OpenRouter. OpenRouter is an LLM provider aggregator. So effectively all open source models providers, a lot of closed source model providers, they route, all of their traffic sometimes get routed through OpenRouter. And one of the interesting things that they've observed over the last 1 year is that the programming and agentic application use case is kind of standing out amongst all other use cases in the sense that these are use cases that consume the most number of tokens input plus output. And the sequence lengths are growing. So if you look at some of the internal data center numbers, these numbers are far larger. Right? Now you couple that fact with the fact that the amount of tokens per sort of processed by agents is sort of significantly increasing and sort of accounting for most of the tokens that you consume from an LLM point of view, then you start realizing that this is a very massive problem that you need to solve, right? Now, not all of these tokens are going to be long context, but again, agentic long context sometimes go hand in hand because of the context that you provide to an agent before a use case is completed. So that is the reason kind of we are looking into this problem, because most data centers were kind of struggling with the problem. At least the data centers that we were talking to were struggling with this particular problem. To understand why long context inference is bad from a tokenomics point of view, maybe I'll quickly start with a primer. Hopefully most of the people are aware with it. So when you're doing LLM inference, so LLM inference is divided into two parts. One is prefill, the other is decode. Prefill is where you take in your prompt, in this case, the quick brown fox. You take in your prompt, you process that prompt, and you save the cache into a KV cache. During decode, you're generating output token by token. In this case, the tokens that you're generating is jumps and over. And for each decode stage, you sort of read in those cache entirely, act on that cache, generate the next token, update the cache with the new updated token, write it back, and do it in a repeated loop, right? So there are three things when it comes to LLM inference: prefill, decode, KV cache, and associated with it is time to prefill, which is TTFT, decode latency, which in this case will be time between two decode tokens, and the size of the KV cache. Now, long context inference is interesting because it really challenges your compute and your memory simultaneously, right? So on the left, you see a graph where it shows how much of your context KV cache has taken up when compared to the model weights, sort of percentage background, when you sort of increase the context length. This is a Llama 3 8B model or Llama 2 7B model. So as you can see, as you're increasing context, then the amount of memory that your KV cache is using is increasing. On the right, you see is the latency, total time taken to process a long context query. And again, you see this fact that as your time is increasing, as the context length is increasing, so is your time increasing, and most of this time is being spent in the attention layers. This is another graph that I borrowed from one of the papers that was published, where you kind of see the KV cache problem associated with long context in a bit more detail. Here you see two different batch sizes, 1 and 4 in the top and bottom table across 4 different model families. And as you can see, long context is always a problem, but as you start increasing the batch size, it becomes an even more acute problem to deal with. In this case, you are seeing the decode latency as a function of context length, right? So not the prefill, the decode latency. And again, even for some of the most state-of-the-art models, as you're increasing the size of the context length, the decode speed is kind of decreasing. It takes more time to decode. And lastly, what you see here is the time to first token associated with long context prompt. In this case, you are looking at different sequence lengths for a 6P model. The second column talks about the time to first token, that is what prefill takes, and the last two column talks about how much percent of that time is spent in full attention. So if you can clearly see that from say 32K to 128K, you are increasing the sequence length by 4x, but your time to first token is going from 1.2 seconds to 77 seconds, much larger than kind of 4x, with 50 to 60% of that time being spent into full attention. So if I summarize the long context challenge, the right two graphs kind of talk about the biggest challenge of long context, your decode latency increasing, your prefill latency increasing, the third challenge is KV cache, and all of that, if you kind of summarize into one graph, the most painful graph that for most data center vendors is the leftmost one, which is the concurrency decreases significantly, right? And the only way to make money in a sort of in the LLM tokenomics world is to serve multiple customers or increase your batch size that you're sort of using on a single GPU. So as you're increasing your context length, all of these challenges effectively imply the amount of number of concurrent users you can serve using a single deployment of a GPU significantly reduces. Now, one of the interesting things about tokenomics today is that as you are increasing your context length, the price that it takes to generate that token is increasing from a vendor point of view, right? And it's increasing at a curve that is more than sort of different from linear, sort of trending towards more than linear. But the pricing doesn't change. Each token, irrespective of the position that it sort of is in, is priced the same. So effectively, those two trends will always hit a knee sort of a point where it's more or less what's happening is that the LLM vendor is effectively serving that token at a loss. Right now, what that knee point will be, I mean, these numbers are a bit more hypothetical based on certain H100 sort of spot pricing, but you'll always find a particular point of a sequence length where it's sort of not profitable for a LLM provider to actually serve long context traffic, right? And that particular point will be a function of how they're accounting for depreciation cost, how they're accounting for operating expenditure and things like that. But the story doesn't change. As sequence length increases, as you're generating more tokens, it gets less and less profitable, and even sort of sometimes, sort of in a manner, you're losing money when you're generating tokens at a certain context length. So the question that we are trying to ask ourselves is, how do we solve this problem? And we really need to really think about this problem extremely hard, because if we are moving towards an agentic world where context length matters, this problem will become more and more acute sort of as time progresses. Right. So we looked at this problem and sort of tried to solve this problem in two ways. One is improving the decoding efficiency. Second is improving the prefill efficiency. I'll start off with talking about the decoding efficiency work that we did. So there are multiple ways to sort of improve your decode throughput. There is KV cache quantization, there is speculative decoding, and then there is sparsity. I'll be talking about the work around sparse KV cache, but this work is very much orthogonal to KV cache quantization or speculative decoding, meaning you can sort of deploy them all together with these other techniques also. But the overall gist of the sparse KV cache work for decoding is that if your KV cache is sparse, during decode, effectively you access a smaller sequence length, and because you're effectively accessing a smaller sequence length, your memory requirement can reduce, and you can technically, or possibly if you implement it correctly, support higher concurrency and faster decode. So again, if you have a higher concurrency, that effectively improves your tokenomics. Now, the reason we are looking at KV cache sparsity is because one of the fundamental observations across all the papers around KV cache compression that have been published over the last 2-3 years is that there is a lot of sparsity in KV cache. On the left-hand side graph, I think this was taken from the heavy hitters paper, you see 5-6 different model families, and they looked at how much can they prune attention within each layer without actually losing accuracy, and what they found is attention is very sparse. On the right-hand side, I think this was taken from the N-inference paper, where the folks looked at how much attention mass do the top K tokens collect if my K is equal to 4096. So when you have calculated attention, after that is your sort of attention into value calculation. So if you have collected most of the attention mass in the top K tokens, then the other sort of tail attention probability mask don't matter because they don't influence your final value vector that much, right? That right-hand graph was, I think, for a Llama 2 AP. The left-hand side is for older generation of models. But these are not the only models that show sparsity patterns in attention. I mean, we looked at 6, 7 other different families, even large families, and there was this constant theme of attention is actually sparse, and there is ways to compress it. Now, this is not something that is unknown, right? I think there have been enough papers published around sparse attention, and yet kind of what you see is that you don't really see these sparse KV cache compression methods show up in, say, SGLang or VLLM, right? Maybe streaming LLM does show up, but I think that's one of the more weaker forms of KV cache compression. But effectively, there should be a reason to keep exploring this, right? Given that this sparsity is model agnostic, and if you're able to sort of sparsify KV cache, you can get a lot of speed benefits. Now, the reason I feel a lot of these work don't really show up in deployments, or at least in SGLang, VLLM, or other kind of infrastructure, is that a lot of these sparse KV cache methods are not really tuned to modern day deployment scenarios, right? So if you look at torch.compile, you expect static graphs. A lot of these sparse methods are very dynamic in the way they are sort of created, or in the way they do compression. That makes it a bit more incompatible with static graphs. These methods sometimes are not thinking about simple things like continuous batching, right? Do you feel decode separate graphs? How do you sort of account? Where do you do sparsity? How do you account for all of those things? And then a lot of these methods have mostly shown results on smaller models. If you are looking at a large scale MOE model like DeepSeek, unclear whether these methods work there or not, right? So maybe our speculation was maybe these were the reasons we kind of don't see these methods as commonly adopted. So I'll just touch upon one particular example, which is kind of compression methods and sort of not being compatible with continuous batching. One way a lot of these KV cache compression methods work is that they always compress once you hit a certain threshold. So you compress, if you hit a threshold, you compress, you keep generating tokens, you hit that threshold again, you compress again. So it's not a one-time compression. The way they maintain this accuracy after compression is to allow token generations to a certain degree and compress back again after a certain point. And how much you allow, etc., is the sweet spot that they find to balance out the accuracy loss that you might see with KV cache compression and things like that. But then modern day deployments are different. You have a separate prefill server, you also have a separate decode graph. You can't really have this dynamic sort of behavior where you generate enough tokens and decide to compress, switch graphs, and do things like that, right? That just kills efficiency. You're doing a lot of context switching and might not be good from a purely throughput point of view, right? And then there are other issues around data structures that they use, etc., that also makes them incompatible with static graphs. So we looked into this problem and came up with a methodology to enable KV cache compressions using these modern day deployment strategies. That work is called Snapstream. It's going to be published at Supercomputing this year. It works seamlessly with continuous batching, works with static graph, and we show that these techniques also work at scale with DeepSeek V3 and R1, the 671B model, not the distal ones, without significant loss in accuracy. Right, so from a purely methodology point of view, the methodology for compression is very much similar to SnapKV, just few tweaks made based on data analysis that we did for large models. But effectively, you do compression during prefill. So you have your context and query. You do your prefill. You don't complete your you do your prefill. You're doing a prefill layer by layer. At each layer, once you finish your prefill, you take an aggregate of what your attention weights look like for the last M tokens. Aggregation can be a function of pooling and averaging that you are doing. And based on that aggregate mass, you determine what attention tokens are important and what they are not, and what are not, and only sort of save important attention tokens. So after your prefill for that entire layer is completed, you don't end up saving the entire KV cache for that layer, you just save the compressed version of that layer. So as you are doing prefill, you add this additional flop computation on top, which is quite trivial, couple of percentage on top of sort of the entire prefill graph, and then you get a compressed KV cache out of it. Now, when you're sort of, so this kind of basically allows you to be a bit more compatible with the modern day deployment scenarios like continuous batching. So in this case, sort of, you have your standard prefill and decode. We replace this prefill with the compression technique that is called Sage KV. We replace this with Sage KV compression, and then during decode, we still maintain the same buffer size that we have used for prefill, and then for that we use streaming LLM. And effectively, this combined sort of deployed system allows you to be compatible with continuous batching. And then from a data structure point of view, we end up using a variation of ring buffers where you have certain sort of, where the ring buffer is divided between sync tokens, streaming tokens, and top K tokens. Sync tokens and streaming and the top K tokens remain static. And then the streaming token has a rotation aspect to it, so that as new tokens are generated, the older ones are kicked out from the recency buffer. So effectively, that entire structure allows you to be compatible with sort of modern day deployment scenarios, and also allow you to sort of ensure that you get that high throughput once you do KV cache compression. Now, this is all good, but then does this all add up in terms of accuracy? So the answer to that question is also yes. So in this case, kind of, we are looking at Llama 3.18b at 128K. We are looking at needle in a haystack benchmark, and we are compressing the 128K KV cache to 16K KV cache. So that's almost 8x compression. And effectively, you can see you're able to preserve almost most of the accuracy if you look at the average across all different benchmarks within needle in a haystack. Now, 8B is a small model. Does this technique work at a larger scale? And again, the answer to that question is yes. In this case, what you're seeing is results for DeepSeek. We are looking at 3 different benchmarks: long bench, AMI, live code bench. So we are looking both at benchmarks which have large prefill, but also benchmarks which have smaller prefill but a lot of longer generation. So in the large prefill, KV cache becomes important. In the smaller case, how you set up your streaming LLM buffer becomes important. So you're seeing all of those benchmarks simultaneously. You see 3 columns: full accuracy is when the model is doing full sequence length. The last accuracy is the compression method that we call SnapStream. And the middle column is basically best of vanilla way of doing streaming LLM versus other techniques, whatever best got you to 32K. And what you can sort of see is that Sage KV plus Straps, sort of Sage KV compression algorithm that we use, effectively preserves most of the accuracy that you see during your full model execution. In fact, surprisingly, you see some accuracy bump also. And when you looked at sort of live code bench and why we are seeing this accuracy bump, I think we are able to sort of figure that out. Sometimes having too much attention is also spread across too many different tokens is also a bad thing. Cool. Okay, this is all good. Accuracy problem solved, but then do you really kind of see any benefit of this method? So these are some deployment numbers that we measured. We also, I don't show the GPU numbers here, but this is also true for GPU. So when we deployed SnapStream on actual workloads within a data center, we do see the benefits that we sort of wanted SnapStream to create. From a purely throughput point of view, that's the last column, your throughput increases by a factor of 4. But I think the throughput increases by a factor of 4. The reason for that is the middle column, which is the batch size. Now, effectively at longer sequence length, because you are doing that KV cache compression, you are able to support a much larger batch sizes. So effectively, your tokenomics as an LLM provider or a data center provider improves significantly. So that's one part of the problem, right? You have made your decode extremely fast. Now, if you're doing continuous batching, if you're decoding extremely fast, then you now need to provide more prefill nodes to feed that decode engine. So even though you're saving costs on the decode side, now your prefill cost increases, and then sometimes the math might not add up that well. So then how do you sort of deal with prefill optimization? So this last part of the talk we'll be talking about how do we sort of improve prefill in terms of reducing its TTFT. And by reducing this TTFT using some form of compression method, you also improve concurrency if you want to. Now, prefill is a bit more trickier problem than decode. There is a lot of work around decode optimization. Prefill optimization, I would still say, is kind of early days in terms of how you optimize. Prefill, as we talked about,